The replacement of hydrogen atom S in an aliphatic or aromatic hydrocarbon by halogen atom S results in the formation of alkyl halide haloalkane and aryl halide haloarene, respectively. Haloalkanes contain halogen atom S attached to the sp3 hybridized carbon atom of an alkyl group, whereas haloarenes contain halogen atom S attached to sp2 hybridized carbon atom S of an aryl group. Many halogen-containing organic compounds occur in nature, and some of these are clinically useful. These classes of compounds find wide applications in industry as well as in day-to-day life. They are used as solvents for relatively nonpolar compounds and as starting materials for the synthesis of wide range of organic compounds. Chlorine-containing antibiotic, chloramphenicol, produced by microorganisms, is very effective for the treatment of typhoid fever. Our body produces iodine-containing hormone, thyroxine, the deficiency of which causes a disease called goiter. Synthetic halogen compounds. Bischloroquine is used for the treatment of malaria. Halothane is used as an anesthetic during surgery. Certain fully fluorinated compounds are being considered as potential blood substitutes in surgery. In this unit, you will study the important methods of preparation, physical and chemical properties and uses of organohalogen compounds. After studying this unit, you will be able to name haloalkanes and haloarenes according to the IUPAC system of nomenclature from their given structures, describe the reactions involved in the preparation of haloalkanes and haloarenes and understand various reactions that they undergo, correlate the structures of haloalkanes and haloarenes with various types of reactions, use stereochemistry as a tool for understanding the reaction mechanism, appreciate the applications of organometallic compounds, highlight the environmental effects of polyhalogen compounds. Objectives 10 Unit 10 Haloalkanes and haloalkanes and haloalkanes and haloalkanes and haloalkanes and capital H A L O A R 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 Enazines haloalkanes and haloalkanes and haloalkanes and haloalkanes and haloalkanes and haloarenes enazines halogenated compounds persist in the environment due to their resistance to breakdown by soil bacteria. 290 Chemistry. Haloalkanes and haloarenes may be classified as follows. These may be classified as mono, D, or polyhalogen tri, tetra, etc. compounds depending on whether they contain 1, 2 or more halogen atoms in their structures. For example, monohalo compounds may further be classified according to the hybridization of the carbon atom to which the halogen is bonded, as discussed below. This class includes alkyl halides or haloalkanes Rx and alkyl halides. The halogen atom is bonded to an alkyl group R. They form a homologous series represented by CnH2n1X. They are further classified as primary, secondary or tertiary according to the nature of carbon to which halogen is attached. If halogen is attached to a primary carbon atom in an alkyl halide, the alkyl halide is called primary alkyl halide or X31° alkyl halide. Similarly, if halogen is attached to secondary or tertiary carbon atom, the alkyl halide is called secondary alkyl halide 2° and tertiary 3° alkyl halide, respectively. Biomolecules halides. These are the compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom adjacent to carbon-carbon double bond CC, that is, to an allylic carbon C. Benzoic halides. These are the compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom attached to an aromatic ring. 10.110, 110, 110, 110, 1. Capital C L A S S I F I C A T I O N capital C L A S S I F I C A T I O N capital C L 10 1 1 on the basis of number of halogen atoms 10 1 2 compounds containing sp3 CX bond XF Cl Br allylic carbon allylic carbon. 291 Haloalkanes and haloarenes. This class includes vinylic halides. These are the compounds in which the halogen atom is bonded to sp2 hybridized carbon atom of a carbon-carbon double bond CC. Aryl halides. These are the compounds in which the halogen atom is directly bonded to the sp2 hybridized carbon atom of an aromatic ring. Having learned the classification of halogenated compounds, let us now learn how these are named. The common names of alkyl halides are derived by naming the alkyl group followed by the name of halide. In the IUPAC system of nomenclature, alkyl halides are named as halosubstituted hydrocarbons. For monohalogen substituted derivatives of benzene, common and IUPAC names are the same. For dihalogen derivatives, the prefixes O, M, P are used in common system but in IUPAC system, as you have learned in Class I, Unit 12, the numerals 1, 2, 1, 3 and 1, 4 are used. 101. 3 compounds containing sp2CX bonded to haloalkanes having the same type of halogen atoms are named as alkylidene or alkaline dihalides. The dihalo compounds having both the halogen atoms are further classified as geminal halides or gemdihalides when both the halogen atoms are present on the same carbon atom of the 10.2 nomenclature 10.2 nomenclature 10.2 nomenclature 10.2 nomenclature 10.2 nomenclature. 292 chemistry chain and vicinal halides or victihalides when halogen atoms are present on adjacent carbon atoms. In common name system, gemdihalides are named as alkylidene halides and victihalides are named as alkaline dihalides. In IUPAC system, they are named as dihaloalkanes. Structure common name IUPAC name CH3CH2CHClCH3 seconds butyl chloride 2 chlorobutane CH3 3CCH2Br neopentyl bromide 1 bromo 2. 2-dimethylpropane CH3 Turk butyl bromide 2 bromo 2-methylpropane CH2CHCl vinyl chloride chloroethene CH2CHCH2Br allobromide 3 bromopropene CH2Cl2 methylene chloride dichloromethane CHCl3 chloroform terchloromethane CHBr3 bromoform tribromomethanes CCl4 carbon tetrachloride tetrachloromethane CH3CH2CH2FN propyl fluoride 1 fluoropropanol chlorotoluene 1 chloro 2 methylbenzene or 2 chlorotoluene benzyl chloride chlorophenylmethane table 10.1 common and IUPAC names of some halides example 10.1 example 10.1 example 10.1 example 10.1 example 10.1 solution draw the structures of all the 8 structural isomers that have the molecular formula C5H11Br. Name each isomer according to IUPAC system and classify them as primary, secondary or tertiary bromide. CH3CH2CH2CH2CH2Br1 bromopentane 1 OCH3CH2CH2CHBr CH3 2 bromopentane 2 OCH3CH2CHBr CH2CH3 3 bromopentane 2 OCH3 2 CHCH2CH2Br1 bromo 3 methylbutane 1 O. Some common examples of halal compounds are mentioned in table 10.1. In text question 10.1 write structures of the following compounds: I2 chloro 3 methylpentane 2 1 chloro 4 ethylcyclohexane 3 4 tert. Butyl 3 iodiheptane IV1 4 dibromide 2 ENEV 1 bromo 4 seconds butyl 2 methylbenzene. Halogen atoms are more electronegative than carbon. Therefore, carbon-halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge whereas the halogen atom bears a partial negative charge. As we go down the group in the periodic table, the size of halogen atom increases. Fluorine atom is the smallest and iodine atom is the largest. Consequently, the carbon-halogen bond length also increases from CF to Ci. Some typical bond lengths. Bond enthalpies and dipole moments are given in table 10.2. Alkyl halides are best prepared from alcohols, which are easily accessible. 10.310, 310, 310, 310. 3 Nature of CX bond CH3 2 CHCHBr CH3 2 bromo 3 methylbutane 2 OCH3 2 CBr CH2 CH3 2 bromo 2 methylbutane 3 OCH3 CH2 CHCH3 CH2 Br1 bromo 2 methylbutane 1 O CH3 3 CCH2 Br1 bromo 2 2-dimethylpropane 1 O. Write IUPAC names of the following: I4 bromopent 2 ENE 2 3 bromo 2 methylbut 1 ENE 3 4 bromo 3 methylpent 2 ENE IV 1 bromo 2 methylbut 2 ENEV 1 bromobut 2 ENEV 3 bromo 2 methylpropene. Example 10.2 example 10.2 example 10.2 example 10.2 example 10.2 Solution 294 Chemistry 104 2 from hydrocarbons bond length PMCX bond enthalpies Kj mol 1 dipole moment to bi CH3F 139 452 1.847 CH3Cl 178 351 1.860 CH3Br 193 293 1.830 CH3I 214 234 1.636 Table 10.2 Carbon halogen CX bond lengths, bond enthalpies and dipole moments. The preparation of alkyl chloride is carried out either by passing dry hydrogen chloride gas through a solution of alcohol or by heating a mixture of alcohol and concentrated aqueous halogen acid. The above methods are not applicable for the preparation of aryl halides because the carbon-oxygen bond in phenols has a partial double bond character and is difficult to break, being stronger than a single bond unit. 11. Class Di. I from alkanes by free radical halogenation. Free radical chlorination or bromination of alkanes gives a complex mixture of isomeric mono and polyhaloalkanes, which is difficult to the hydroxyl group of an alcohol is replaced by halogen on reaction with concentrated halogen acids, phosphorus halides or thionyl chloride. Thionyl chloride is preferred because in this reaction alkyl halide is formed along with gases SO2 and HCl. The two gaseous products are escapable, hence, the reaction gives pure alkyl halides. The reactions of primary and secondary alcohols with HCl require the presence of a catalyst, ZnCl2. With tertiary alcohols, the reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature. Constant boiling with HBr48 is used for preparing alkyl bromide. Good yields of Ri may be obtained by heating alcohols with sodium or potassium iodide and 95-orthophosphoric acid. The order of reactivity of alcohols with a given halosite is 3 degrees, 2 degrees, x 31 degree. Phosphorus tribromide and triiodide are usually generated in C2 produced in the reaction mixture by the reaction of red phosphorus with bromine and iodine respectively. 10.410, 410, 410, 410. 4 methods of preparation of haloalkanes 1 from alcohols. 295 haloalkanes and haloarenes separate as pure compounds. Consequently, the yield of any single compound is low. Unit 13, Class I. Identify all the possible monochlorostructural isomers expected to be formed on free radical monochlorination of CH3 2CH2CH2CH3. In the given molecule, there are 4 different types of hydrogen atoms. Replacement of these hydrogen atoms will give the following CH3 2CH2CH2CH2Cl CH3 2CHCHCl CH3 CH3 2CCl CH2CH3 CH3CHCH2Cl CH2CH3. Example 10.3 Example 10.3 Example 10.3 Example 10.3 Example 10.3 Solution 2 from alkenes. Addition of hydrogen halides. An alkene is converted to corresponding alkyl halide by reaction with hydrogen chloride, hydrogen bromide or hydrogen iodide. Propene yields 2 products, however only one predominates as per Markovnikov's rule. Unit 13, Class Psi2. Addition of halogens, in the laboratory. Addition of bromine and CCl4 to an alkene resulting in discharge of reddish-brown color of bromine constitutes an important method for the detection of double bond in a molecule. The addition results in the synthesis of victobromides, which are colorless. Unit 13, Class I. Alkyl iodides are often prepared by the reaction of alkyl chlorides bromides with Ni and triacetone. This reaction is known as Finkelstein reaction. NaCl or NaBr are thus formed as precipitated in triacetone. It facilitates the forward reaction according to Le Chatelier's principle. The synthesis of alkyl fluorides is best accomplished by heating an alkyl chloride bromide in the presence of a metallic fluoride such as 1,0,4,3 halogen exchange. 296 Chemistry AgF, Hg2F2, COF2 or SbF3. The reaction is termed as Swartz reaction. I from hydrocarbons by electrophilic substitution. Aryl chlorides and bromides can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalysts like iron or iron chloride. The ortho and pada isomers can be easily separated due to large difference in their melting points. Reactions with iodine are reversible in nature and require the presence of an oxidizing agent HNO3, HeO4 to oxidize the high formed during iodination. Fluorocompounds are not prepared by this method due to high reactivity of fluorine 2 from amines by Sand-Meyer's reaction when a primary aromatic amine, dissolved or suspended in cold aqueous mineral acid, is treated with sodium nitrite. A diazonium salt is formed. Unit 13, Class 12. Mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide results in the replacement of the diazonium group by Cl or Br. Replacement of the diazonium group by iodine does not require the presence of cuprous halide and is done simply by shaking the diazonium salt with potassium iodide. 10.510, 510, 510, 510, 5 Preparation of haloarenes 297 haloalkanes and haloarenes. Alkyl halides are colorless when pure, however, bromides and iodides develop color when exposed to light. Many volatile halogen compounds have sweet smell. 10.2 is sulfuric acid not used during the reaction of alcohols with key. 10.3 Write structures of different halogen derivatives of propane. 10.4 Among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination yields a single monochloride. 2-3 isomeric monochlorides 3-4 isomeric monochlorides. 10.5 Draw the structures of major monohalo products in each of the following reactions. In text questions write the products of the following reactions. Example 10.4 Example 10.4 Example 10.4 Example 10.4 Example 10.4 Solution 10.610 610 6 Physical properties. Melting and boiling points: methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes are gases at room temperature. Higher members are liquids or solids. As we have already learned, molecules of organic halogen compounds are generally polar. Due to greater polarity as well as higher molecular mass as compared to the parent hydrocarbon, the intermolecular forces of attraction dipole and van der Waals are stronger in the halogen derivatives. That is why the boiling points of chlorides, bromides and iodides are considerably higher than those of the hydrocarbons of comparable molecular mass. The attractions get stronger as the molecules get bigger in size and have more electrons. The pattern of variation of boiling points of different halides is depicted in Fig. 10.1. For the same alkyl group, the boiling points of alkyl halides decrease in the order Ri, Rbr, Rcl, Rf. This is because with the increase in size and mass of halogen atom, the magnitude of van der Waals forces increases. The boiling points of isomeric haloalkanes decrease with increase in branching unit 12, class Xi. For example, 2-bromo-2-methylpropane has the lowest boiling point among the three isomers. Boiling points of isomeric dihalobenzenes are very nearly the same. However, the PADA isomers are high melting as compared to their ortho and meta isomers. It is due to symmetry of PADA isomers that fits in crystal lattice better as compared to ortho and meta isomers. Figure 10.1. Comparison of boiling points of some alkyl halides. Solubility: the haloalkanes are very slightly soluble in water. In order to dissolve haloalkane in water, energy is required to overcome the attractions between the haloalkane molecules and break the hydrogen bonds between water molecules. Less energy is released when new attractions are set up between the haloalkane and the water molecules, as these are not as strong as the original hydrogen bonds in water. As a result, the solubility of haloalkanes in water is low. However, haloalkanes tend to dissolve in organic solvents because the new intermolecular attractions between haloalkanes and solvent molecules have much the same strength as the ones being broken in the separate haloalkane and solvent molecules. Table 10.3. Density of some haloalkanes. Density: bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms, halogen atoms and atomic mass of the halogen atoms. Table 10.3. The reactions of haloalkanes may be divided into the following categories. 1. Nucleophilic substitution. 2. Elimination reactions. 3. Reaction with metals. 1. Nucleophilic substitution reactions. You have learned in class Sci that nucleophiles are an electron-rich species. Therefore, they attack at that part of the substrate molecule which is electron deficient. The reaction in which a nucleophile replaces 10.6 arrange each set of compounds in order of increasing boiling points. Ibromomethane, bromoform, chloromethane, dibromomethane. 2. 1-chloropropane, isopropyl chloride, 1-chlorobutane. In text question 10.710 710 7 Chemical reactions Compound density GML NC3H7Cl 0.89 CH2Cl2 1.336 NC3H7 Br 1.335 CHCl3 1.489 NC3H7I 1.747 CCl4 1 595 10 1 Reactions of haloalkanes. 300 Chemistry. Already existing nucleophile in a molecule is called nucleophilic substitution reaction. Haloalkanes are substrate in these reactions. In this type of reaction, a nucleophile reacts with haloalkane, the substrate having a partial positive charge on the carbon atom bonded to halogen. A substitution reaction takes place in halogen atom, called leaving group departs as halide ion. Since the substitution reaction is initiated by a nucleophile, it is called nucleophilic substitution reaction. It is one of the most useful classes of organic reactions of alkyl halides in which halogen is bonded to sp3 hybridized carbon. The products formed by the reaction of haloalkanes with some common nucleophiles are given in Table 10.4. Groups like cyanides and nitrites possess two nucleophilic centers and are called ambident nucleophiles. Actually, cyanide group is a hybrid of two contributing structures and therefore can act as a nucleophile in two different ways: VCN left-right arrow, CNV. That is, linking through Table 10.4, nucleophilic substitution of alkyl halides Rx reagent nucleophile substitution class of main new product R new product NeoCO HO alcohol H2O H2O alcohol nor RO ether NiIRI alkyl iodide NH3 NH3 RNH2 primary amine, RNH2 RNH2 RNHR sec. Amine RRNHRRNHRNRR tert. Amine KCN RCN nitryl cyanide AgNAgCN, RNCI sonitrile isocyanide No2ONO alkyl nitrite OGNO2 agodiarosis NOR number 2 nitrylcane RCOO AgRCOO ester LH4HRH hydrocarbon RMRRR alkane. 301 haloalkanes and haloarenes carbon atom resulting in alkyl cyanides and through nitrogen atom leading to isocyanides. Similarly, nitrite ion also represents an ambident nucleophile with two different points of linkage O-NiO. The linkage through oxygen results in alkyl nitrites while through a nitrogen atom, it leads to nitrylcanes. Mechanism: this reaction has been found to proceed by two different mechanisms which are described below. A substitution nucleophilic bimolecular SN2. The reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows a second-order kinetics, that is, the rate depends upon the concentration of both the reactants. Haloalkanes react with KCN to form alkyl cyanides as main product while AgN forms isocyanides as the chief product. Explain: KCN is predominantly ionic and provides cyanide ions in solution, although both carbon and nitrogen atoms are in a position to donate electron pairs. The attack takes place mainly through carbon atom and not through nitrogen atom since CC bond is more stable than CN bond. However, AgN is mainly covalent in nature and nitrogen is free to donate electron pair forming isocyanide as the main product. Example 10.5 Example 10.5 Example 10.5 Example 10.5 Example 10.5 Solution. The above reaction can be represented diagrammatically as shown in Fig. 10.2. It depicts a bimolecular nucleophilic substitution SN2 reaction. The incoming nucleophile interacts with alkyl halide causing the carbon halide bond to break and a new bond is formed between carbon and attacking nucleophile. Here it is CO bond formed between C and O. These two processes take place simultaneously in a Fig. 10.2. Red ball represents the incoming hydroxide ion and green ball represents the outgoing halide ion. In the year 1937. Edward Davies Hughes and Sir Christopher Ingold proposed a mechanism for an SN2 reaction. You have already learned in section 1.2.3.2 of Class I. The solid wedge represents the bond coming out of the paper, dashed line going down the paper and a straight line representing bond in the plane of the paper. Single step and no intermediate is formed. As the reaction progresses and the bond between the incoming nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. As this happens, the three carbon-hydrogen bonds of the substrate start moving away from the attacking nucleophile. In transition state, all the three CH bonds are in the same plane and the attacking and leaving nucleophiles are partially attached to the carbon. As the attacking nucleophile approaches closer to the carbon, CH bonds still keep on moving in the same direction till the attacking nucleophile attaches to carbon and leaving group leaves the carbon. As a result, configuration is inverted. The configuration C box of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind. This process is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. Hughes worked under Ingold and earned a DSc degree from the University of London, since this reaction requires the approach of the nucleophile to the carbon bearing the leaving group. The presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect. Of the simple alkyl halides, methyl halides react most rapidly in SN2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching configuration. Spatial arrangement of functional groups around carbon is called its configuration. See the structures A and B given below carefully. These are the 2 structures of the same compound. They differ in spatial arrangement of functional groups attached to carbon. Structure A is mirror image of structure B. We say configuration of carbon in structure A is mirror image of the configuration of carbon in structure B. 303 Haloalkanes and Haloarenes nucleophiles. Thus the order of reactivity followed is primary halide, secondary halide, tertiary halide. B. Substitution nucleophilic unimolecular SN1 reactions are generally carried out in polar product solvents like water, alcohol, acetic acid, etc. The reaction between tert-butyl bromide and hydroxide ion yields tert-butyl alcohol and follows the first-order kinetics. That is, the rate of reaction depends upon the concentration of only one reactant, which is tert-butyl bromide. It occurs in two steps. In step I, the polarized CBr bond undergoes slow cleavage to produce a carbocation and a bromide ion. The carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. Figure 10.3, steric effects in SN2 reaction. The relative rate of SN2 reaction is given in parenthesis. 304 Chemistry step I is the slowest and reversible. It involves the CBr bond breaking, for which the energy is obtained through solvation of halide ion with the proton of product solvent. Since the rate of reaction depends upon the slowest step, the rate of reaction depends only on the concentration of alkyl halide and not on the concentration of hydroxide ion. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide and faster will be the rate of reaction. In case of alkyl halides, 30 alkyl halides undergo SN1 reaction very fast because of the high stability of 30 carbocations. We can sum up the order of reactivity of alkyl halides towards SN1 and SN2 reactions as follows. For the same reasons, allylic and benzylic halides show high reactivity towards the SN1 reaction. The carbocation thus formed gets stabilized through resonance unit 12, class psi as shown below, in the following pairs of halogen compounds, which would undergo SN2 reaction faster. Example 10.6 Example 10.6 Example 10.6 Example 10.6 Example 10.6 H2C2CCHHH2C2CHCH Solution. It is primary halide and therefore undergoes SN2 reaction faster. As iodine is a better leaving group because of its large size, it will be released at a faster rate in the presence of incoming nucleophile. Example 10.7 Example 10.7 Example 10.7 Example 10.7 Example 10.7 Predict the order of reactivity of the following compounds in SN1 and SN2 reactions. I. The 4-isomeric bromobutanes 2C6H5CH2Br, C6H5CH C6H5Br, C6H5CH CH3Br, C6H5CCH3 C6H5Br for a given alkyl group. The reactivity of the halide Rx follows the same order in both the mechanisms Ri, Rbr, Rcl, Rf. 305 Haloalkanes and Haloarenes. See stereochemical aspects of nucleophilic substitution reactions in order to understand the stereochemical aspects of substitution reactions. We need to learn some basic stereochemical principles and notations: optical activity, chirality, retention, inversion, racemization, etc. I. Optical activity. Plane of plane polarized light produced by passing ordinary light through Nicoll prism is rotated when it is passed through the solutions of certain compounds. Such compounds are called optically active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. If the compound rotates the plane of plane polarized light to the right, that is, clockwise direction, it is called dextrorotatory, Greek for right rotating, or the D form, and is indicated by placing a positive sign before the degree of rotation. If the light is rotated towards left anti-clockwise direction, the compound is said to be levorotatory, or the L form, and a negative sign is placed before the degree of rotation. Such isomers of a compound are called optical isomers, and the phenomenon is termed as optical isomerism. 2. Molecular asymmetry, chirality and enantiomers. The observation of Louis Pasteur 1848 that crystals of certain compounds exist in the form of mirror images laid the foundation of modern stereochemistry. He demonstrated that aqueous solutions of both types of crystals showed optical rotation, equal in magnitude for solution of equal concentration but opposite in direction. He believed that this difference in optical activity was associated with the three-dimensional arrangements of atoms in the molecules configurations of ICH3CH2CH2CH2Br, CH32CHCH2Br, CH3CH2CHBr, CH3, CH33CBr, SN1CH3CH2CH2CH2Br, CH3, 2CHCH2Br, CH3CH2CHBr, CH3, CH33CBr, SN2 of the two primary bromides. The carbocation intermediate derived from CH3-2CHCH2Br is more stable than derived from CH3CH2CH2CH2Br because of greater electron donating inductive effect of CH3-2CH group. Therefore, CH3-2CH-CH2Br is more reactive than CH3-CH2-CH2-CH2Br in SN1 reactions. CH3-CH2-CHBr-CH3 is a secondary bromide and CH3-3CBr is a tertiary bromide. Hence the above order is followed in SN1. The reactivity in SN2 reactions follows the reverse order as the steric hindrance around the electrophilic carbon increases in that order. 2C6H5CCH3C6H5Br, C6H5CH6H5Br, C6H5CH3Br, C6H5CH2Br-SN1 C6H5CCH3C6H5Br C6H5CH6H5Br C6H5CH3Br C6H5CH2Br-SN2 of the two secondary bromides. The carbocation intermediate obtained from C6H5CH6H5Br is more stable than obtained from C6H5CH3Br because it is stabilized by two phenyl groups due to resonance. Therefore, the former bromide is more reactive than the latter in SN1 reactions. A phenyl group is bulkier than a methyl group. Therefore, C6H5CH6H5Br is less reactive than C6H5CH3Br in SN2 reactions. Solution William Nicol 1768-1851 developed the first prism that produced plane polarized light. 306 Chemistry. Two types of crystals. Dutch scientist, J. van 't Hoff, French scientist, C. Labelle in the same year 1874. Independently argued that the spatial arrangement of four groups valencies around a central carbon is tetrahedral and if all the substituents attached to the carbon are different. The mirror image of the molecule is not superimposed overlapped on the molecule. Such a carbon is called asymmetric carbon or stereocenter. The resulting molecule would lack symmetry and is referred to as asymmetric molecule. The asymmetry of the molecule along with non-superimposability of mirror images is responsible for the optical activity in such organic compounds. The symmetry and asymmetry are also observed in many day-to-day objects. A sphere, a cube, a cone, are all identical to their mirror images and can be superimposed. However, many objects are non-superimposable on their mirror images. For example, your left and right hand look similar, but if you put your left hand on your right hand by moving them in the same plane, they do not coincide. The objects which are non-superimposable on their mirror image like a pair of hands are said to be chiral, and this property is known as chirality. Chiral molecules are optically active, while the objects, which are superimposable on their mirror images, are called achiral. These molecules are optically inactive. The above test of molecular chirality can be applied to organic molecules by constructing models and its mirror images or by drawing three-dimensional structures and attempting to superimpose them in our minds. There are other aids, however, that can assist us in recognizing chiral molecules. One such aid is the presence of, as you can see very clearly, propan-2-ol A does not contain an asymmetric carbon, as all the four groups attached to the tetrahedral carbon are not different. We rotate the mirror image B of the molecule by 180 degrees structure C and try to overlap the structure C with the structure A. These structures completely overlap. Thus propan-2-ol is an achiral molecule. Jacobus Hendrikus van 't Hoff 1852-1911 received the first Nobel Prize in Chemistry in 1901 for his work on solutions. Figure 10.4. Some common examples of chiral and achiral objects. A single asymmetric carbon atom. Let us consider two simple molecules, propan-2-ol Figure 10.5 and butan-2-ol Figure 10.6 and their mirror images. Figure 10.5. B is mirror image of A. B is rotated by 180 O and C is obtained. C is superimposable on A. 307 Haloalkanes and Haloarenes. Butan-2-ol has four different groups attached to the tetrahedral carbon and as expected is chiral. Some common examples of chiral molecules such as 2-chlorobutane, 2,3-dihydroxypropanol, OHCCHOH, CH2O, bromochloroiodamethane Br-chlorchi, 2-bromopropanoic acid H3CH-Br-Cu, etc. Figure 10.7. A chiral molecule and its mirror image. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. Fig. 10.7. A and B in Figure 10.5 and D in Figure 10.6 are enantiomers. Enantiomers possess identical physical properties, namely, melting point, boiling point, refractive index, etc. They only differ with respect to the rotation of plane polarized light. If one of the enantiomers is dextro-rotatory, the other will be levo-rotatory. A mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation due to the other isomer. Such a mixture is known as racemic mixture or racemic modification. A racemic mixture is represented by prefixing DL or plus or minus before the name, for example plus or minus butan-2-al. The process of conversion of an enantiomer into a racemic mixture is known as racemization. Example 10.8 Example 10.8 Example 10.8 Example 10.8 Example 10.8 Identify chiral and achiral molecules in each of the following pair of compounds. Wedge and dash representations according to class Xi. Figure 12.1. Figure 10.6. E is mirror image of D. E is rotated by 180 O to get F, and F is non-superimposable on its mirror image D. However, the sign of optical rotation is not necessarily related to the absolute actual configuration of the molecule. 308 Chemistry 3 Retention. Retention of configuration is the preservation of the spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation. In general, if during a reaction, no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of reactant. Such a reaction is said to proceed with retention of the configuration. Consider as an example, the reaction that takes place when 2-methylbutan-1-al is heated with concentrated hydrochloric acid. Solution. It is important to note that configuration at a symmetric center in the reactant and product is same, but the sign of optical rotation has changed in the product. This is so because two different compounds with same configuration at asymmetric center may have different optical rotation. One may be dextrorotatory plus sign of optical rotation, while other may be levorotatory negative sign of optical rotation. IV inversion, retention and racemization. There are three outcomes for a reaction at an asymmetric carbon atom, when a bond directly linked to an asymmetric carbon atom is broken. Consider the replacement of a group X by Y in the following reaction. If A is the only compound obtained, the process is called retention of configuration. Note that configuration has been rotated in A. If B is the only compound obtained, the process is called inversion of configuration. Configuration has been inverted in B. If a 50 hours and 50 minutes mixture of A and B is obtained, then the process is called racemization and the product is optically inactive, as one isomer will rotate the plane polarized light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanisms by taking examples of optically active alkyl halides. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. When 2-bromoctane is allowed to react with sodium hydroxide, octan-2-al is formed with the O group occupying the position opposite to what bromide had occupied. Thus, SN2 reactions of optically active halides are accompanied by inversion of configuration. In case of optically active alkyl halides, SN1 reactions are accompanied by racemization. Can you think of the reason why it happens? Actually, the carbocation formed in the slow step being sp2 hybridized is planar achiral. The attack of the nucleophile may be accomplished from either side of the plane of carbocation, resulting in a mixture of products. One having the same configuration, the O attaching on the same position as halide ion, and the other having opposite configuration, the O attaching on the side opposite to halide ion. This may be illustrated by hydrolysis of optically active 2-bromobutane, which results in the formation of plus or minus butan-2-al. 2. Elimination reactions. When a haloalkane with Greek letter beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from Greek letter beta carbon and a halogen atom from the Greek letter alpha carbon atom. Location of Greek letter alpha, 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 and Greek letter beta, Greek letter beta, Greek letter beta, Greek letter beta, Greek letter beta carbon in a molecule. Carbon on which halogen atom is directly attached is called Greek letter alpha carbon, and the carbon atom adjacent to this carbon is called Greek letter beta carbon. As a result, an alkene is formed as a product. Since Greek letter beta hydrogen atom is involved in elimination, it is often called Greek letter beta, Greek letter beta, Greek letter beta, Greek letter beta, Greek letter beta elimination. If there is possibility of formation of more than one alkene due to the availability of more than one Greek letter beta hydrogen atoms, usually one alkene is formed as the major product. These form part of a pattern first observed by Russian chemist Alexander Zaitsev, also pronounced as Zaitsev, who in 1875 formulated a rule which can be summarized as into hydrohalogenation reactions. The preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Thus, 2-bromopentane gives pent-2-ene as the major product. 3. Reaction with metals. Most organic chlorides, bromides and iodides react with certain metals to give compounds containing carbon-metal bonds. Such compounds are known as organometallic compounds. An important class of organometallic compounds discovered by Victor Grignard in 1900 is alkyl magnesium halide, RMGX, referred as Grignard reagents. These reagents are obtained by the reaction of haloalkanes with magnesium metal and dry ether. A chemical reaction is the result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do, by and large, what is easiest for them. An alkyl halide with Greek letter beta hydrogen atoms when reacted with a base or a nucleophile has two competing routes, substitution SN1 and SN2 and elimination. Which route will be taken up depends upon the nature of alkyl halide, strength and size of base nucleophile and reaction conditions. Thus, a bulkier nucleophile will prefer to act as a base and abstracts a proton rather than approach a tetravalent carbon atom steric reasons and vice versa. Similarly, a primary alkyl halide will prefer a SN2 reaction. A secondary halide SN2 or elimination depending upon the strength of base nucleophile and a tertiary halide SN1 or elimination depending upon the stability of carbocation or the more substituted alkene. Elimination versus substitution, elimination versus substitution, elimination versus substitution, elimination versus substitution, elimination versus substitution. 311 Haloalkanes and Haloarenes. Victor Grignard had a strange start in academic life. For a chemist, he took a maths degree. When he eventually switched to chemistry, it was not to the mathematical province of physical chemistry but to organic chemistry. While attempting to find an efficient catalyst for the process of methylation, he noted that ZN and diethyl ether had been used for this purpose and wondered whether the Mg ether combination might be successful. Grignard reagents were first reported in 1900 and Grignard used this work for his doctoral thesis in 1901. In 1910, Grignard obtained a professorship at the University of Nancy and in 1912, he was awarded the Nobel Prize for Chemistry which he shared with Paul Sabatier who had made advances in nickel-catalyzed hydrogenation. In the Grignard reagent, the carbon-magnesium bond is covalent but highly polar, with carbon pulling electrons from electropositive magnesium. The magnesium-halogen bond is essentially ionic. Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. It is therefore necessary to avoid even traces of moisture from a Grignard reagent. That is why reaction is carried out in dry ether. On the other hand, this could be considered as one of the methods for converting halides to hydrocarbons. Wurtz reaction. Alkyl halides react with sodium and dry ether to give hydrocarbons containing double the number of carbon atoms present in the halide. This reaction is known as Wurtz reaction. Unit 13, Class Psi1, nucleophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitution reactions due to the following reasons. I resonance effect, in haloarenes. The electron pairs on halogen atom are in conjugation with Greek letter pi electrons of the ring and the following resonating structures are possible. CCl bond acquires a partial double bond character due to resonance. As a result, the bond cleavage in haloarene is difficult than haloalkane and therefore, they are less reactive towards nucleophilic substitution reaction. 107. Two reactions of haloarenes. 312 Chemistry. Two difference in hybridization of carbon atom in CX bond. In haloalkane, the carbon atom attached to halogen is sp3 hybridized while in case of haloarene, the carbon atom attached to halogen is sp2 hybridized. The sp2 hybridized carbon with a greater s character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkane with less s character. Thus, CCl bond length in haloalkane is 177 pm while in haloarene is 169 pm, since it is difficult to break a shorter bond than a longer bond. Therefore, haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. 3. Instability of phenyl cation. In case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance and therefore, SN1 mechanism is ruled out. Because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. Replacement by hydroxyl group chlorobenzene can be converted into phenol by heating an aqueous sodium hydroxide solution at a temperature of 623 K and a pressure of 300 atmospheres. The presence of an electron withdrawing group number 2 at ortho and pod oppositions increases the reactivity of haloarenes. 313 Haloalkanes and haloarenes. The effect is pronounced when number 2 group is introduced at ortho and pod oppositions. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Mechanism of the reaction is as depicted. Can you think why does number 2 group show its effect only at ortho and pod oppositions and not at meta position as shown? The presence of nitro group at ortho and pod oppositions withdraws the electron density from the benzene ring and thus facilitates the attack of the nucleophile on halorene. The carbanion thus formed is stabilized through resonance. The negative charge appeared at ortho and pod oppositions with respect to the halogen substituent is stabilized by number 2 group, while in case of metanitrobenzene, none of the resonating structures bear the negative charge on carbon atom bearing the number 2 group. Therefore, the presence of nitro group at meta position does not stabilize the negative charge and no effect on reactivity is observed by the presence of number 2 group at meta position. 314 Chemistry 2. Electrophilic substitution reactions. Haloarenes undergo the usual electrophilic reactions of the benzene ring such as halogenation, nitration, sulfonation and Friedel-Crafts reactions. Halogen atom besides being slightly deactivating is p-directing, therefore, further substitution occurs at ortho and pod oppositions with respect to the halogen atom. The p-directing influence of halogen atom can be easily understood if we consider the resonating structures of halobenzene as shown, due to resonance. The electron density increases more at ortho and pod oppositions than at meta positions. Further, the halogen atom because of its Psi effect has some tendency to withdraw electrons from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene and hence the electrophilic substitution reactions in haloarenes occur slowly and require more drastic conditions as compared to those in benzene. I-halogenation 2 nitration 3 sulfonation. I-Friedel-Crafts reaction. Although chlorine is in electron withdrawing group, yet it is ortho-pod directing in electrophilic aromatic substitution reactions. Why chlorine withdraws electrons through inductive effect and releases electrons through resonance. Through inductive effect, chlorine destabilizes the intermediate carbocation formed during the electrophilic substitution. Through resonance, halogen tends to stabilize the carbocation and the effect is more pronounced at ortho and pod oppositions. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. The resonance effect tends to oppose the inductive effect for the attack at ortho and pod oppositions and hence makes the deactivation less for ortho and pod attack. Reactivity is thus controlled by the stronger inductive effect and orientation is controlled by resonance effect. Example 10.9 Example 10.9 Example 10.9 Example 10.9 Example 10.9 Solution 316 Chemistry in text questions 3. Reaction with metals. Wurtzbittig reaction. A mixture of an alkyl halide and aryl halide gives an alkylorene when treated with sodium and dry ether and is called Wurtzbittig reaction. Fittig reaction. Aryl halides also give analogous compounds when treated with sodium and dry ether, in which two aryl groups are joined together. It is called Fittig reaction. 10.7 Which alkyl halide from the following pairs would you expect to react more rapidly by an SN2 mechanism? Explain your answer. 10.8 In the following pairs of halogen compounds, which compound undergoes faster SN1 reaction? 10.9 Identify A, B, C, D, E, R and R1 in the following. 317 Haloalkanes and haloarenes. Carbon compounds containing more than one halogen atom are usually referred to as polyhalogen compounds. Many of these compounds are useful in industry and agriculture. Some polyhalogen compounds are described in this section. Dichloromethane is widely used as a solvent, as a paint remover, as a propellant in aerosols, and as a process solvent in the manufacture of drugs. It is also used as a metal cleaning and finishing solvent. Methylene chloride harms the human central nervous system. Exposure to lower levels of methylene chloride in air can lead to slightly impaired hearing and vision. Higher levels of methylene chloride in air cause dizziness, nausea, tingling and numbness in the fingers and toes. In humans, direct skin contact with methylene chloride causes intense burning and mild redness of the skin. Direct contact with the eyes can burn the cornea. Chemically, chloroform is employed as a solvent for fats, alkaloids, iodine and other substances. The major use of chloroform today is in the production of the Freon refrigerant R22. It was once used as a general anesthetic in surgery but has been replaced by less toxic, safer anesthetics, such as ether. As might be expected from its use as an anesthetic, inhaling chloroform vapors depresses the central nervous system. Breathing about 900 parts of chloroform per million parts of air 900 parts per million for a short time can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the liver where chloroform is metabolized to phosgene and to the kidneys, and some people develop sores when the skin is immersed in chloroform. Chloroform is slowly oxidized by air in the presence of light to an extremely poisonous gas, carbonyl chloride, also known as phosgene. It is therefore stored in closed dark-colored bottles completely filled so that air is kept out. It was used earlier as an antiseptic, but the antiseptic properties are due to the liberation of free iodine and not due to iodoform itself. Due to its objectionable smell, it has been replaced by other formulations containing iodine. It is produced in large quantities for use in the manufacture of refrigerants and propellants for aerosol cans. It is also used as feedstock in the synthesis of chlorofluorocarbons and other chemicals, pharmaceutical manufacturing, and general solvent use. Until the mid-1960s, it was also widely used as a cleaning fluid, both in industry, as a degreasing agent, and in the home, as a spot remover and as fire extinguisher. There is some evidence that exposure to carbon tetrachloride causes liver cancer in humans. The most common effects are dizziness, lightheadedness, nausea and vomiting, which can cause permanent damage to nerve cells. In severe cases, these effects can lead rapidly to stupor, coma, unconsciousness or death. Exposure to CCl4 can make the heart beat irregularly or stop. The chemical may irritate the eyes on contact. When carbon tetrachloride is released into the air, it rises to the atmosphere and depletes the ozone layer. Depletion of the 10.710, 710, 710, 710, 7 polyhalogen compounds 10, 7, 1 dichloromethane methylene chloride 10, 7, 3 triiodomethane iodoform 10, 7, 4 tetrachlo, rhomothane carbon tetrachloride 10, 7, 2 trichloromethane chloroform. 318 Chemistry. Ozone layer is believed to increase human exposure to ultraviolet rays, leading to increased skin cancer, eye diseases and disorders, and possible disruption of the immune system. The chlorofluorocarbon compounds of methane and ethane are collectively known as freons. They are extremely stable, unreactive, non-toxic, non-corrosive and easily liquefiable gases. Freon 12CCl2F2 is one of the most common freons in industrial use. It is manufactured from tetrachloromethane by Schwartz reaction. These are usually produced for aerosol propellants, refrigeration and air conditioning purposes. By 1974, total freon production in the world was about 2 billion pounds annually. Most freon, even that used in refrigeration, eventually makes its way into the atmosphere where it diffuses unchanged into the stratosphere. In stratosphere, freon is able to initiate radical chain reactions that can upset the natural ozone balance. Unit 14, Class I. DDT, the first chlorinated organic insecticides, was originally prepared in 1873, but it was not until 1939 that Paul Muller of Geigy Pharmaceuticals in Switzerland discovered the effectiveness of DDT as an insecticide. Paul Muller was awarded the Nobel Prize in Medicine and Physiology in 1948 for this discovery. The use of DDT increased enormously on a worldwide basis after World War II, primarily because of its effectiveness against the mosquito that spreads malaria and lice that carry typhus. However, problems related to extensive use of DDT began to appear in the late 1940s. Many species of insects developed resistance to DDT, and it was also discovered to have a high toxicity towards fish. The chemical stability of DDT and its fat solubility compounded the problem. DDT is not metabolized very rapidly by animals. Instead, it is deposited and stored in the fatty tissues. If ingestion continues at a steady rate, DDT builds up within the animal over time. The use of DDT was banned in the United States in 1973, although it is still in use in some other parts of the world. 107, 5 freons 107, 6p, p-dichlorodephanyl trichloroethane DDT. Summary alkyl aryl halides may be classified as mono, D, or polyhalogen tri, tetra, etc. compounds depending on whether they contain 1, 2 or more halogen atoms in their structures. Since halogen atoms are more electronegative than carbon, the carbon-halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge, and the halogen atom bears a partial negative charge. Alkyl halides are prepared by the free radical halogenation of alkanes, addition of halogen acids to alkenes. Replacement of a group of alcohols with halogens using 319 haloalkanes and haloarenes. Phosphorus halides, thionyl chloride are halogen acids. Aryl halides are prepared by electrophilic substitution to arenes. Fluorides and iodides are best prepared by halogen exchange method. The boiling points of organohalogen compounds are comparatively higher than the corresponding hydrocarbons because of strong dipole-dipole and van der Waals forces of attraction. These are slightly soluble in water but completely soluble in organic solvents. The polarity of carbon-halogen bond of alkyl halides is responsible for their nucleophilic substitution, elimination and their reaction with metal atoms to form organometallic compounds. Nucleophilic substitution reactions are categorized into SN1 and SN2 on the basis of their kinetic properties. Chirality has a profound role in understanding the reaction mechanisms of SN1 and SN2 reactions. SN2 reactions of chiral alkyl halides are characterized by the inversion of configuration, while SN1 reactions are characterized by racemization. A number of polyhalogen compounds, e.g., dichloromethane, chloroform, iodoform, carbon tetrachloride, freon and DDT, have many industrial applications. However, some of these compounds cannot be easily decomposed and even cause depletion of ozone layer and are proving environmental hazards. 10.1 Name the following halides according to IUPAC system and classify them as alkyl, allyl, benzyl primary, secondary, tertiary. Vinyl or aryl halides: ICH32CHCHCl,
CH2CH4CH2CH3CH2CH3CH3CH3CH3CH4CH2CH3CH3CH3CH3CH3CH3CH3CH4CH2CH3CH3CH3CH3CH3CH3CH3CH3CH3CH3CH3CH3CH3 OBRC6H4CH3CH2CH3 10.2 Give the IUPAC names of the following compounds: ICH3CHCl, CHBrCl3CCHF2CBrCl3CCL, CH2CCHCl, page 10.3 Write the structures of the following organic halogen compounds: I2-chloro-3-methylpentane 2-p-bromochlorobenzene 3,1-chloro-4-ethylcyclohexane IV 2,2-chlorophenol 1-iodoctane V2-bromobutane V4 Turk-butyl 3-iodiheptane 7,1-bromo 4 butyl 2-methylbenzene 8,1,4-dibromobut 2-ene 10.4 Which one of the following has the highest dipole moment? ICH2Cl2 2CH2CL3 3CCl4 10.5 A hydrocarbon C5H10 does not react with chlorine in dark but gives a single monochloro compound C5H9Cl in bright sunlight. Identify the hydrocarbon 10.6 Write the isomers of the compound having formula C4H9Br 10.7 Write the equations for the preparation of 1-iodobutane from I1-butanol 2,1-chlorobutane 3-but-1-ene. 10.8 What are ambient nucleophiles? Explain with an example. Exercises. 320 Chemistry 10.9 Which compound in each of the following pairs will react faster in SN2 reaction with O? ICH3Br or CH3I2CH33CCl or CH3Cl 10.10 Predict all the alkenes that would be formed by dehydrohalogenation of the following halides with sodium ethoxide and ethanol and identify the major alkene. I1-bromo 1-methylcyclohexane 2,2-chloro-2-methylbutane 3,2,2,3-trimethyl-3-bromopentane. 10.11 How will you bring about the following conversions? I-ethanol to but-1 2-ethane to bromothene 3-propene to 1-nitropropane I-toluene to benzyl alcohol V-propene to propine V-ethanol to ethyl fluoride 7-bromomethane to propanone 8-but-1-ene to but-2-ene 9-1-chlorobutane to N-octane X-benzene to biphenyl. 10.12 Explain why I the dipole moment of chlorobenzene is lower than that of cyclohexyl chloride 2 alkyl halides. The polar are immiscible with water. 3 Grignard reagents should be prepared under anhydrous conditions. 10.13 Give the uses of freon 12, DDT, carbon tetrachloride and iodoform. 10.14 Write the structure of the major organic product in each of the following reactions. ICH3CH2CH2Cl Ni2CH33CBrCO3CH3CHBrCH2CH3 NaOIV CH3CH2BrKCNVC6H5 and AC2H5ClVCH3CH2CH2O Cyclo2 7CH3CH2CH3CH2CH3CH3 2HBr 10.15 Write the mechanism of the following reaction. N-BRKCN Buck 10.16 Arrange the compounds of each set in order of reactivity towards SN2 displacement. I2-bromo 2-methylbutane, 1-bromopentane, 2-bromopentane 2,1-bromo 3-methylbutane, 2-bromo 2-methylbutane, 2-bromo 3-methylbutane 3,1-bromobutane, 1-bromo 2,2-dimethylpropane, 1-bromo 2-methylbutane, 1-bromo 3-methylbutane. 10.17 Out of C6H5CH2Cl and C6H5CHCl C6H5, which is more easily hydrolyzed by aqueous Co. 10.18p dichlorobenzene has higher MP than those of O and M isomers. Discuss 10.19 how the following conversions can be carried out. I-propene to propan 1 al 2 ethanol to but1 1 bromopropane to 2 bromopropane. 321 haloalkanes and haloarenes I-toluene to benzyl alcohol V benzene to 4 bromonitrobenzene V benzyl alcohol to 2 phenylethanoic acid 7 ethanol to propanenitriol 8 aniline to chlorobenzene 9 2 chlorobutane to 3 4 dimethylhexane x 2 methyl 1 propene to 2 chloro 2 methylpropane xyethyl chloride to propanoic acid 12 but 1 iani to n-butyliodide 13 2 chloropropane to 1 propanol 14 isopropyl alcohol to iodoform 15 chlorobenzene to p-nitrophenol 16 2 bromopropane to 1 bromopropane 17 chlorothane to butane 18 benzene to diphenyl 19 tert-butyl bromide to isobutyl bromide XX aniline to phenylacylcyanide 10.20 The treatment of alkyl chlorides with aqueous Co leads to the formation of alcohols but in the presence of alcoholic Co, alkenes are major products. Explain 10.21 Primary alkyl halide C4H9Br are reacted with alcoholic Co to give compound B. Compound B is reacted with HBr to give C which is an isomer of A. When A is reacted with sodium metal it gives compound D, C8H18 which is different from the compound formed when N-butyl bromide is reacted with sodium. Give the structural formula of A and write the equations for all the reactions 10.22 What happens when N-butyl chloride is treated with alcoholic Co? 2-bromobenzene is treated with Mg in the presence of dry ether, 3-chlorobenzene is subjected to hydrolysis. 5-ethyl chloride is treated with aqueous Co, V-methyl bromide is treated with sodium in the presence of dry ether. V-methyl chloride is treated with KCN. Answers to some in-text questions 10.1 10.2 IH2 SO4 cannot be used along with Ke in the conversion of an alcohol to an alkyl iodide as it converts Ke to corresponding acid. I which is then oxidized by it to I2. 10.3 ICl-CH2CH2CH2CL2CL CH2CH3 3CL2CH3 ICH3CCl2CH3 322 Chemistry 10.4 10.5 10.6 I-chloromethane, bromomethane, dibromomethane, bromoform, boiling point increases with increase in molecular mass. 2 isopropyl chloride, 1 chloropropane, 1 chlorobutane, isopropyl chloride being branched has lower BP than 1 chloropropane 10.7 ICH3CH2CH2CH2Br being primary halide, there won't be any steric hindrance. 2 secondary halide reacts faster than tertiary halide 3 The presence of methyl group closer to the halide group will increase the steric hindrance and decrease the rate. The equivalent hydrogens are grouped as A, B and C. The replacement of equivalent hydrogens will give the same product. All the hydrogen atoms are equivalent and replacement of any hydrogen will give the same product. Similarly the equivalent hydrogens are grouped as A, B, C and D. Thus, 4 isomeric products are possible. 10.8 I tertiary halide reacts faster than secondary halide because of the greater stability of tert carbocation. 2 because of greater stability of secondary carbocation than primary 10.9. After studying this unit, you will be able to name alcohols, phenols and ethers according to the IUPAC system of nomenclature, discuss the reactions involved in the preparation of alcohols from alkenes, aldehydes, ketones and carboxylic acids, discuss the reactions involved in the preparation of phenols from haloarenes, benzene sulfonic acids, diazonium salts and cumene, discuss the reactions for preparation of ethers from I-alcohols and 2-alkyl halides and sodium alkoxides aryl oxides, correlate physical properties of alcohols, phenols and ethers with their structures, discuss chemical reactions of the 3 classes of compounds on the basis of their functional groups. Objectives Alcohols, phenols and ethers are the basic compounds for the formation of detergents, antiseptics and fragrances, respectively. 11 Unit 11, capital A, L, C, O, H, O, L, S, capital A, L, C, O, H, O, L, S, capital A, L, C, O, H, O, L, S, capital A, L, C, O, H, O, phenols and ether there's SSSS alcohols, comma. Phenols and ether there's SSSS. You have learnt that substitution of one or more hydrogen atoms from a hydrocarbon by another atom or a group of atoms result in the formation of an entirely new compound having altogether different properties and applications. Alcohols and phenols are formed when a hydrogen atom in a hydrocarbon, aliphatic and aromatic respectively, is replaced by a group These classes of compounds find wide applications in industry as well as in day-to-day life. For instance, have you ever noticed that ordinary spirit used for polishing wooden furniture is chiefly a compound containing hydroxyl group, ethanol? The sugar we eat, the cotton used for fabrics, the paper we use for writing, are all made up of compounds containing O groups. Just think of life without paper. No notebooks, books, newspapers, currency notes, checks, certificates, etc. The magazines carrying beautiful photographs and interesting stories would disappear from our life. It would have been really a different world. An alcohol contains one or more hydroxyl O group S directly attached to carbon atom S. Of an aliphatic system CH3O, while a phenol contains O group S directly attached to carbon atom S of an aromatic system C6H5O. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryloxy group RORO yields another class of compounds known as ethers, for example, CH3OC3 ether. You may also visualize ethers as compounds formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this unit, we shall discuss the chemistry of three classes of compounds, namely alcohols, phenols and ethers. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. I compounds containing 3 COsP bond. In this class of alcohols, the O group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified as follows: primary, secondary and tertiary alcohols. In these three types of alcohols, the O group is attached to primary, secondary and tertiary carbon atom, respectively, as depicted below. Allylic alcohols. In these alcohols, the O group is attached to a sp3 hybridized carbon adjacent to the carbon-carbon double bond, that is to an allylic carbon. For example, benzylic alcohols. In these alcohols, the O group is attached to a sp3 hybridized carbon atom next to an aromatic ring. For example, the classification of compounds makes their study systematic and hence simpler. Therefore, let us first learn how are alcohols, phenols and ethers classified. Alcohols and phenols may be classified as mono, D, tri or polyhydric compounds depending on whether they contain 1, 2, 3 or many hydroxyl groups respectively, and their structures as given below. 11.1 11.1 11.1 11.111.1 Capital C L A S S I F I C A T I O N Capital C L A S S I F I C A T I O N Capital C L 1 alcohols mono, D, tri or polyhydric alcohols monohydric dihydric trihydric. 325 alcohols, phenols and ethers. Allylic and benzylic alcohols may be primary, secondary or tertiary. 2 compounds containing 2 COsP bond. These alcohols contain O group bonded to a carbon-carbon double bond, that is, to a vinylic carbon or to an aryl carbon. These alcohols are also known as vinylic alcohols. Vinylic alcohol, CH2CH, O11, 3 ethers CH3CCHO2CH3CH3IHC2CHCHO2 2CH3CH2CHO2 3CHO2CH3CH3VCHOHCHCH3VCH3 11.1 Classify the following as primary, secondary and tertiary alcohols. 11.2 Identify allylic alcohols in the above examples. In text questions 11.2 Nomenclature 11.2 Nomenclature 11.2 Nomenclature 11.2 Nomenclature 11.2 Nomenclature Alcohols. The common name of an alcohol is derived from the common name of the alkyl group and adding the word alcohol to it. For example, CH3O is methyl alcohol 1,1,1, 2 phenols mono, D and trihydric phenols. Ethers are classified as simple or symmetrical if the alkyl or aryl groups attached to the oxygen atom are the same, and mixed or unsymmetrical if the two groups are different. Diethyl ether, C2H5O, is a symmetrical ether, whereas C2H5OC3 and C2H5OC6H5 are unsymmetrical ethers. Monohydric. 326 Chemistry according to IUPAC System Unit 12, Class Xi. The name of an alcohol is derived from the name of the alkane from which the alcohol is derived, by substituting E of alkane with the suffix ol. The position of substituents are indicated by numerals. For this, the longest carbon chain parent chain is numbered starting at the end nearest to the hydroxyl group. The positions of the O group and other substituents are indicated by using the numbers of carbon atoms to which these are attached. For naming polyhydric alcohols, the E of alkane is retained and the ending ol is added. The number of O groups is indicated by adding the multiplicative prefix, di, tri, etc., before ol. The positions of O groups are indicated by appropriate lockants, e.g., HO, CH2, CH2O is named as ethane 1,2-diol. Table 11.1 gives common and IUPAC names of a few alcohols as examples. Table 11.1, common and IUPAC names of some alcohols: CH3O methyl alcohol, methanol, CH3CH2CH2O, and propyl alcohol, propan-1-ol, isopropyl alcohol, propan-2-ol, CH3CH2CH2CH2O, and butyl alcohol, butan-1-ol, sec-butyl alcohol, butan-2-ol, isobutyl alcohol, 2-methylpropan-1-ol, turk-butyl alcohol, 2-methylpropan-2-ol, HO, H2C, CH2O, ethylene glycol, ethane 1,2-diol, glycerol, propane 1,2,3-triol compound. Common name IUPAC name cyclic alcohols are named using the prefix cyclo and considering the O group attached to C1. OOCH3-cyclohexanol, 2-methylcyclopentanol, B-phenols. The simplest hydroxy derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. A structure of phenol involves a benzene ring. In its substituted compounds, the terms ortho 1, 2 desubstituted, meta 1, 3 desubstituted, and pada 1, 4 desubstituted are often used in the common names. Common name phenol, cresol and cresol, p-cresol, IUPAC name phenol, 2-methylphenol, 3-methylphenol, 4-methylphenol. Dihydroxy derivatives of benzene are known as 1, 2, 1, 3 and 1, 4 benzenidyl. OCH3OCH3OCH3OOOOOO. Common name catechol, benzene diol 1, 2 resorcinol, benzene diol 1, 3 hydroquinone or quinol, benzene diol 1, 4 IUPAC name C ethers. Common names of ethers are derived from the names of alkyl aryl groups written as separate words in alphabetical order and adding the word ether at the end. For example, CH3OC2H5 is ethylmethyl ether. Table 11.2. Common and IUPAC names of some ethers compound. Common name IUPAC name CH3OC3-dimethyl ether, methoxymethane, C2H5OC2H5-diethyl ether, ethoxyethane, CH3OC2CH2CH3-methyl and propyl ether, 1-methoxypropane, C6H5OC3-methyl phenyl ether, methoxybenzene, anisole, C6H5OC2CH3-ethylphenyl ether, ethoxybenzene, phenidol, C6H5OCH2,6CH3-heptyl phenyl ether, 1-phenoxyhetane, CH3CHO3CH3-methyl isopropyl ether, 2-methoxypropane phenyl isopentyl ether, 3-methylbutoxybenzene, CH3O, CH2, CH2OC3 2-dimethoxyethane, 2-ethoxy 1-dimethylcyclohexane. 328 Chemistry. If both the alkyl groups are the same, the prefix D is added before the alkyl group. For example, C2H5OC2H5 is diethyl ether. According to IUPAC system of nomenclature, ethers are regarded as hydrocarbon derivatives in which a hydrogen atom is replaced by an or group, where R and R represent alkyl and aryl groups, respectively. The larger R group is chosen as the parent hydrocarbon. The names of a few ethers are given as examples in Table 11.2. I4-chloro 2,3-dimethylpentan-1-ol 2,2-ethoxypropane 3,2. 6-dimethylphenolide 1-ethoxy-2-nitrocyclohexane number 2-OCH25. Example 11.1. Example 11.1. Example 11.1. Example 11.1. Example 11.1. Solution OCH3H3CI3 2CH3CH3CH3CH3CH2CH3CH3CH3CH3CH3CH3I. IV 11.3. Name the following compounds according to IUPAC system. In text question, I2 3 IV and alcohols. The oxygen of the O group is attached to carbon by a sigma Greek letter sigma bond formed by the overlap of sp3 hybridized orbital of carbon with the sp3 hybridized orbital of oxygen. Figure 11.1 depicts structural aspects of methanol, phenol and methoxymethane. 11.311, 311, 311, 311, 3. Structures of functional groups. Fig. 11.1. Structures of methanol, phenol and methoxymethane. Give IUPAC names of the following compounds. 329 alcohols, phenols and ethers. The bond angle in alcohols is slightly less than the tetrahedral angle of 109 degrees 28. It is due to the repulsion between the unshared electron pairs of oxygen. In phenols, the O group is attached to sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length 136 pm in phenol is slightly less than that in methanol. This is due to a partial double bond character on account of the conjugation of unshared electron pair of oxygen with the aromatic ring section 1,1,4, 4 and 2 sp2 hybridized state of carbon to which oxygen is attached. In ethers, the 4 electron pairs, that is, the 2 bond pairs and 2 lone pairs of electrons on oxygen are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the 2 bulky R groups. The CO bond length 141 pm is almost the same as in alcohols 1,1,4, 1 preparation of alcohols. Alcohols are prepared by the following methods. 1. From alkenes I by acid catalyzed hydration, alkenes react with water in the presence of acid as catalyst to form alcohols. In case of unsymmetrical alkenes, the addition reaction takes place in accordance with Markovnikov's rule Unit 13, Class I. Mechanism. The mechanism of the reaction involves the following 3 steps. Step 1. Protonation of alkene to form carbocation by electrophilic attack of H3O. H2OH-H3O. Step 2. Nucleophilic attack of water on carbocation. Step 3. Deprotonation to form an alcohol. 11.411, 411, 4, 11, 411, 4. Alcohols and alcohols and alcohols and alcohols and alcohols and phenols. 330 Chemistry 2 by hydroboration oxidation. Diborane BH32 reacts with alkenes to give trialkyl boranes as addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. The addition of borane to the double bond takes place in such a manner that the boron atom gets attached to the sp2 carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in a way opposite to the Markovnikov's rule. In this reaction, alcohol is obtained in excellent yield too. From carbonyl compounds I by reduction of aldehydes and ketones, aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalyst catalytic hydrogenation. The usual catalyst is a finely divided metal such as platinum, palladium or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydride NAD4 or lithium aluminium hydride LiAlH4. Aldehydes yield primary alcohols whereas ketones give secondary alcohols too by reduction of carboxylic acids and esters. Carboxylic acids are reduced to primary alcohols in excellent yield by lithium aluminium hydride, a strong reducing agent. RCOOH-LiAlH4 2HO2RCHO2 However, LiAlH4 is an expensive reagent, and therefore, used for preparing special chemicals only. Commercially, acids are reduced to alcohols by converting them to the ester section 1,1,4, followed by their reduction using hydrogen in the presence of catalyst catalytic hydrogenation. Rho-H hydroboration oxidation was first reported by H. C. Brown in 1959, for his studies on boron-containing organic compounds. Brown shared the 1979 Nobel Prize in Chemistry with G. Wittig. The numbers in front of the reagents along the arrow indicate that the second reagent is added only when the reaction with first is complete. 331 Alcohols, phenols and ethers 3. From Grignard reagents. Alcohols are produced by the reaction of Grignard reagents Unit 10, Class 12 with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of the adduct yields an alcohol I. The overall reactions using different aldehydes and ketones are as follows. You will notice that the reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehydes and tertiary alcohol with ketones. Give the structures and IUPAC names of the products expected from the following reactions. A catalytic reduction of butanol. B. Hydration of propane in the presence of dilute sulfuric acid. C. Reaction of propanone with methyl magnesium bromide followed by hydrolysis. Example 11.2 Example 11.2 Example 11.2 Example 11.2 Example 11.2 Solution of B-phenol, also known as carbolic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivatives by any of the following methods. 1,1,4,2 Preparation of phenols. The reaction of Grignard reagents with methanol produces a primary alcohol. With other aldehydes, secondary alcohols and with ketones, tertiary alcohols. C. 332 Chemistry 1. From haloarenes. Chlorobenzene is fused with NaO at 623 K and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide. So produced Unit 10, Class 12 2. From benzenesulfonic acid. Benzene is sulfonated with oleum and benzene sulfonic acid so formed is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of the sodium salt gives phenol 3. From diazonium salts, a diazonium salt is formed by treating an aromatic primary amine with nitrous acid non-O2HCl at 273-278 K. Diazonium salts are hydrolyzed to phenols by warming with water or by treating with dilute acid. Unit 13, Class 12. HOOHNH2 non-O2HCl aniline NCl22NHCl2 benzene diazonium chloride warm 4. From cumene, phenol is manufactured from the hydrocarbon, cumene. Cumene isopropylbenzene is oxidized in the presence of air to cumene hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. Most of the worldwide production of phenol is from cumene. Alcohols and phenols consist of two parts, an alkyl aryl group and a hydroxyl group. The properties of alcohols and phenols are chiefly due to the hydroxyl group. The nature of alkyl and aryl groups simply modify these properties. Boiling points. The boiling points of alcohols and phenols increase with increase in the number of carbon atoms, increase in van der Waals forces. In alcohols, the boiling points decrease with increase of branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The L group in alcohols and phenols is involved in intermolecular hydrogen bonding as shown below. It is interesting to note that boiling points of alcohols and phenols are higher in comparison to other classes of compounds, namely hydrocarbons, ethers, haloalkanes and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling points differ widely. The boiling point of methoxymethane is intermediate of the two boiling points 1, 1, 4. 3 physical properties. 11.4 show how are the following alcohols prepared by the reaction of a suitable Grignard reagent on methanol. 11.5 write structures of the products of the following reactions. In text questions. In text questions. In text questions. In text questions. In text questions 2-3I. The high boiling points of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbons. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds with water molecules as shown. The solubility decreases with increase in size of alkyl aryl hydrophobic groups. Several of the lower molecular mass alcohols are miscible with water in all proportions. Arrange the following sets of compounds in order of their increasing boiling points: a pentan 1-ol, butan 1-ol, butan 2-ol, ethanol, propan 1-ol, methanol. B-pentan 1-ol, N-butane, pentanol, ethoxyethane or methanol, ethanol, propan 1-ol, butan 2-ol, butan 1-ol, pentan 1-ol. B-N-butane, ethoxyethane, pentanol and pentan 1-ol. Example 11.3. Example 11.3. Example 11.3. Example 11.3. Example 11.3. Solution. Alcohols are versatile compounds. They react both as nucleophiles and electrophiles. The bond between OH is broken when alcohols react as nucleophiles. 1-1-4. 4 chemical reactions. Alcohols as nucleophiles. I2. The bond between CO is broken when they react as electrophiles. Protonated alcohols react in this manner. Protonated alcohols as electrophiles based on the cleavage of OH and CO bonds. The reactions of alcohols and phenols may be divided into two groups. 335 alcohols, phenols and ethers are reactions involving cleavage of OH bond 1. Acidity of alcohols and phenols. I reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium and aluminium to yield corresponding alkoxides, phenoxides and hydrogen. In addition to this, phenols react with aqueous sodium hydroxide to form sodium phenoxides. Sodium phenoxide HO2O and O. Now the above reactions show that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are Bronsted acids, that is, they can donate a proton to a stronger base B. 2. Acidity of alcohols. The acidic character of alcohols is due to the polar nature of OH bond. An electron-releasing group CH3, C2H5 increases electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acid strength. For this reason, the acid strength of alcohols decreases in the following order. 336 Chemistry. Alcohols are, however, weaker acids than water. This can be illustrated by the reaction of water with an alkoxide. This reaction shows that water is a better proton donor, that is, stronger acid than alcohol. Also, in the above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxides are stronger base, as sodium ethoxide is a stronger base than sodium hydroxide. Alcohols act as Bronsted bases as well. It is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptors. 3. Acidity of phenols. The reactions of phenol with metals e.g., sodium, aluminium and sodium hydroxide indicate its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule, as depicted in its resonance structures, causes the oxygen of O group to be positive. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acids than alcohols and water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than the one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and a phenol takes place as follows, due to the higher electronegativity of sp2 hybridized carbon of phenol to which O is attached. Electron density decreases on oxygen. This increases the polarity of OH bond and results in an increase in ionization of phenols than that of alcohols. Now let us examine the stabilities of alkoxide and phenoxide ions. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge structures IV makes 337 alcohols, phenols and ethers. Phenoxide ion more stable and favors the ionization of phenol. Although there is also charge delocalization in phenol, its resonance structures have charge separation, due to which the phenol molecule is less stable than phenoxide ion. O-nitrophenol O2N, C6H4O7.2 meters. Nitrophenol MO2N, C6H4O8.3 P. Nitrophenol page O2N, C6H4O7.1 Phenol C6H5O10.0 Cresol OCH3, C6H4O10.2 meters. Cresol MCH3 C6H4O10.1 P. Cresol page CH3, C6H4O10.2 Ethanol C2H5O15.9 Table 11.3. pK values of some phenols and ethanol compound formula. pK from the above data, you will note that phenol is million times more acidic than ethanol. Arrange the following compounds in increasing order of their acid strength: propan 1O, 2, 4, 6 trinitrophenol, 3 nitrophenol, 3, 5-dinitrophenol, phenol, 4-methylphenol. Propan 1O, 4-methylphenol, phenol, 3 nitrophenol, 3, 5-dinitrophenol, 2, 4, 6 trinitrophenol. Example 11.4 Example 11.4 Example 11.4 Example 11.4 Example 11.4 Solution 2. Esterification. Alcohols and phenols react with carboxylic acids, acid chlorides and acid anhydrides to form esters. In substituted phenols, the presence of electron withdrawing groups such as nitro group enhances the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho and pot oppositions. It is due to the effective delocalization of negative charge in phenoxide ion when substituent is at ortho or pot opposition. On the other hand, electron-releasing groups, such as alkyl groups, in general, do not favor the formation of phenoxide ion, resulting in decrease in acid strength. Cresols, for example, are less acidic than phenol. The greater the pK value, the weaker the acid. Pyridine RRR low COCr Ericer HCl. The reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible, and therefore, water is removed as soon as it is formed. The reaction with acid chloride is carried out in the presence of a base pyridine so as to neutralize HCl, which is formed during the reaction. It shifts the equilibrium to the right-hand side. The introduction of acetyl CH3CO group in alcohols or phenols is known as acetylation. Acetylation of salicylic acid produces aspirin B reactions involving cleavage of carbon-oxygen CO bond in alcohols. The reactions involving cleavage of CO bond take place only in alcohols. Phenols show this type of reaction only with zinc 1. Reaction with hydrogen halides. Alcohols react with hydrogen halides to form alkyl halides. Refer Unit 10, Class 12. Rho HXRXH2O. The difference in reactivity of three classes of alcohols with HCl distinguishes them from one another. Lucas test. Alcohols are soluble in Lucas reagent conc, HCl and ZnCl2, while their halides are immiscible and produce turbidity in solution. In case of tertiary alcohols, turbidity is produced immediately as they form the halides easily. Primary alcohols do not produce turbidity at room temperature. 2. Reaction with phosphorus trihalides. Alcohols are converted to alkyl bromides by reaction with phosphorus tribromide. Refer Unit 10, Class 12. 3. Dehydration. Alcohols undergo dehydration, removal of a molecule of water to form alkenes on treating with the product acid, e.g. concentrated H2SO4 or H3PO4, or catalysts such as anhydrous zinc chloride or alumina. Unit 13, Class I. Ethanol undergoes dehydration by heating it with concentrated H2SO4 at 443 K. Aspirin possesses analgesic, anti-inflammatory and antipyretic properties. Secondary and tertiary alcohols are dehydrated under milder conditions, for example thus. The relative ease of dehydration of alcohols follows the following order: tertiary, secondary, primary. The mechanism of dehydration of ethanol involves the following steps. Mechanism: Step 1, formation of protonated alcohol. Step 2, formation of carbocation. It is the slowest step and hence, the rate-determining step of the reaction. Step 3, formation of ethene by elimination of a proton. The acid used in Step 1 is released in Step 3. To drive the equilibrium to the right, ethene is removed as it is formed for oxidation. Oxidation of alcohols involves the formation of a carbon-oxygen double bond with cleavage of an OH and CH bonds. Such a cleavage and formation of bonds occur in oxidation reactions. These are also known as dehydrogenation reactions, as these involve loss of dihydrogen from an alcohol molecule. Depending on the oxidizing agent used, a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. Tertiary carbocations are more stable and therefore are easier to form than secondary and primary carbocations. Tertiary alcohols are the easiest to dehydrate. 340 Chemistry. Strong oxidizing agents such as acidified potassium permanganate are used for getting carboxylic acids from alcohols directly. Cro3 an anhydrous medium is used as the oxidizing agent for the isolation of aldehydes. 3,2-CHRCO2. A better reagent for oxidation of primary alcohols to aldehydes in good yield is pyridinium chlorotrimate PCC. A complex of chromium trioxide with pyridine and HCl. 3,2,3-PCC-OxCH-CH-CH-CH. Secondary alcohols are oxidized to ketones by chromic anhydride Cro3. Tertiary alcohols do not undergo oxidation reaction. Under strong reaction conditions such as strong oxidizing agents KMNO4 and elevated temperatures, cleavage of various CC bonds takes place and a mixture of carboxylic acids containing lesser number of carbon atoms is formed. When the vapors of a primary or a secondary alcohol are passed over heated copper at 573 K, dehydrogenation takes place and an aldehyde or a ketone is formed while tertiary alcohols undergo dehydration. Biological oxidation of methanol and ethanol in the body produces the corresponding aldehyde followed by the acid. At times the alcoholics, by mistake, drink ethanol, mixed with methanol, also called denatured alcohol. In the body, methanol is oxidized first to methanal and then to methanoic acid, which may cause blindness and death. A methanol poison patient is treated by giving intravenous infusions of diluted ethanol. The enzyme responsible for oxidation of aldehyde HCHO2 acid is swamped, allowing time for kidneys to excrete methanol. See reactions of phenols. Following reactions are shown by phenols only. 341 Alcohols, phenols and ethers. 1. Electrophilic aromatic substitution in phenols. The reactions that take place on the aromatic ring are electrophilic substitution reactions. Unit 13, Class I. The L group attached to the benzene ring activates it towards electrophilic substitution. Also, it directs the incoming group to ortho and pod positions in the ring as these positions become electron-rich due to the resonance effect caused by L group. The resonance structures are shown under acidity of phenols. Common electrophilic aromatic substitution reactions taking place in phenol are as follows. I nitration, with dilute nitric acid at low temperature 298 K. Phenol yields a mixture of ortho and pod nitrophenols. The ortho and pod isomers can be separated by steam distillation. O-nitrophenol is steam volatile due to intermolecular hydrogen bonding, while P-nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as picric acid. The yield of the reaction product is poor. Nowadays picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it to phenol 2,4-disulfonic acid, and then with concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equations of the reactions involved? 2,4,6-trinitrophenol is a strong acid due to the presence of 3 electron withdrawing number 2 groups which facilitate the release of hydrogen ion. 342 Chemistry. 2. Halogenation. On treating phenol with bromine, different reaction products are formed under different experimental conditions. When the reaction is carried out in solvents of low polarity such as CHCl3 or CS2 and at low temperature, monobromophenols are formed. The usual halogenation of benzene takes place in the presence of a Lewis acid, such as FeBr3 Unit 10, Class 12, which polarizes the halogen molecule. In case of phenol, The polarization of bromine molecule takes place even in the absence of Lewis acid. It is due to the highly activating effect of O group attached to the benzene ring B when phenol is treated with bromine water. 2,4,6-tribromophenols is formed as white precipitate. Write the structures of the major products expected from the following reactions: a mononitration of 3-methylphenol, beta-nitration of 3-methylphenol, C mononitration of phenylmethanoate. The combined influence of O and CH3 groups determine the position of the incoming group. Example 11.5 Example 11.5 Example 11.5 Example 11.5 Example 11.5 Solution 2. Kolbe's reaction: phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Orthohydroxybenzoic acid is formed as the main reaction product. 343 Alcohols, phenols and ethers. 3. Reimer-Tiemann reaction on treating phenol with chloroform in the presence of sodium hydroxide. A CHO group is introduced at ortho position of benzene ring. This reaction is known as Reimer-Tiemann reaction. The intermediate substituted benzoyl chloride is hydrolyzed in the presence of alkali to produce salicylaldehyde. 4. Reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. 5. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone. In the presence of air, phenols are slowly oxidized to dark-colored mixtures containing quinones. 11.6 Give structures of the products you would expect when each of the following alcohol reacts with HCl, NCl2, BHBr and C-Socyl2. Ibuten 1-ol 2,2-methylbutene 2-ol 11.7 Predict the major product of acid-catalyzed dehydration of I1-methylcyclohexanol and 2-butene 1-ol 11.8 Ortho and POD on the trophenols are more acidic than phenol. Draw the resonance structures of the corresponding phenoxide ions. 11.9 Write the equations involved in the following reactions. I. Reimer-Tiemann reaction. 2. Kolbe's reaction. In text questions. 344 Chemistry. Methanol and ethanol are among the two commercially important alcohols. 1. Methanol. CH3O, also known as wood spirit, was produced by destructive distillation of wood. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature and in the presence of CNO, Cr2O3 catalyst. Methanol is a colorless liquid and boils at 337 K. It is highly poisonous in nature. Ingestion of even small quantities of methanol can cause blindness and large quantities causes even death. Methanol is used as a solvent in paints, varnishes and chiefly for making formaldehyde. 2. Ethanol, C2H5O, is obtained commercially by fermentation. The oldest method is from sugars. The sugar in molasses, sugarcane or fruit such as grapes is converted to glucose and fructose, both of which have the formula C6H12O6, in the presence of an enzyme, invertase. Glucose and fructose undergo fermentation in the presence of another enzyme, zymase, which is found in yeast. In winemaking, grapes are the source of sugars and yeast. As grapes ripen, the quantity of sugar increases and yeast grows on the outer skin. When grapes are crushed, sugar and the enzyme come in contact and fermentation starts. Fermentation takes place in anaerobic conditions, that is, in absence of air. Carbon dioxide is released during fermentation. The action of zymase is inhibited once the percentage of alcohol formed exceeds 14%. If air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. Ethanol is a colorless liquid with boiling point 351 K. It is used as a solvent in paint industry and in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate to give it a color and purity in a foul-smelling liquid. It is known as denaturation of alcohol. Nowadays, large quantities of ethanol are obtained by hydration of ethene. Section 11.4. 11.511, 511, 5. Some. Capital C O M M E R C I A L L Y. Capital C O M M E R C I A L L Y. Capital C O M M E R. Important alcohols. Ingestion of ethanol acts on the central nervous system. In moderate amounts, it affects judgment and lowers inhibitions. Higher concentrations cause nausea and loss of consciousness. Even at higher concentrations, it interferes with spontaneous respiration and can be fatal. 345 Alcohols, phenols and ethers. 1. By dehydration of alcohols. Alcohols undergo dehydration in the presence of protic acids H2SO4, H3PO4. The formation of the reaction product, alkene or ether, depends on the reaction conditions. For example, ethanol is dehydrated to ethene in the presence of sulfuric acid at 443 K at 413 K. Ethoxyethane is the main product. The formation of ether is a nucleophilic bimolecular reaction SN2 involving the attack of alcohol molecule on a protonated alcohol. As indicated below, 11.611, 611, 6, 11, 611, 6, ethers 11, 6, 1 preparation of ethers acidic dehydration of alcohols. To give an alkene is also associated with substitution reaction to give an ether. The method is suitable for the preparation of ethers having primary alkyl groups only. The alkyl group should be unhindered and the temperature be kept low, otherwise the reaction favors the formation of alkene. The reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in higher classes. However, the dehydration of secondary and tertiary alcohols to give corresponding ethers is unsuccessful as elimination competes over substitution, and as a consequence, alkenes are easily formed. Can you explain why is bimolecular dehydration not appropriate for the preparation of ethyl methyl ether 2? Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide, RX-NaROR-NIX. Ethers containing substituted alkyl groups secondary or tertiary may also be prepared by this method. The reaction involves SN2 attack of an alkoxide ion on primary alkyl halide. Diethyl ether has been used widely as an inhalation anesthetic. But due to its slow effect and an unpleasant recovery period, it has been replaced, as an anesthetic, by other compounds. Alexander William Williamson 1824-1904, was born in London of Scottish parents. In 1849, he became professor of chemistry at University College, London. 346 Chemistry OCHBr3. Na better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3NO with CH33CBr gives exclusively to methylpropene. It is because alkoxides are not only nucleophiles but strong bases as well. They react with alkyl halides leading to elimination reactions. The following is not an appropriate reaction for the preparation of T-butyl ethyl ether. What would be the major product of this reaction? To write a suitable reaction for the preparation of T-butyl ethyl ether. The major product of the given reaction is 2-methylprop-1-ene. It is because sodium ethoxide is a strong nucleophile as well as a strong base. Thus elimination reaction predominates over substitution. Example 11.6 Example 11.6 Example 11.6 Example 11.6 Example 11.6 Solution 2 phenols are also converted to ethers by this method. In this, phenol is used as the phenoxide moiety. 347 Alcohols, phenols and ethers. The CO bonds in ethers are polar and thus, ethers have a net dipole moment. The weak polarity of ethers do not appreciably affect their boiling points, which are comparable to those of the alkanes of comparable molecular masses but are much lower than the boiling points of alcohols as shown in the following cases. Formula CH3CH2 3CH3C2H5OC2H5CH3CH2 pentane ethoxyethane butane 1 all BPK 309, 1, 307, 6, 390. The large difference in boiling points of alcohols and ethers is due to the presence of hydrogen bonding in alcohols. The miscibility of ethers with water resembles those of alcohols of the same molecular mass. Both ethoxyethane and butane 1 all are miscible to almost the same extent, that is, 7.5 and 9 grams per 100 milliliters water, respectively, while pentane is essentially immiscible with water. Can you explain this observation? This is due to the fact that just like alcohols, oxygen of ether can also form hydrogen bonds with water molecule as shown. 1. Cleavage of CO bond in ethers. Ethers are the least reactive of the functional groups. The cleavage of CO bond in ethers takes place under drastic conditions with excessive hydrogen halides. The reaction of dialkyl ether gives 2 alkyl halide molecules. Alkyl aryl ethers are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yields phenol and alkyl halide. Ethers with 2 different alkyl groups are also cleaved in the same manner. The order of reactivity of hydrogen halides is as follows. High, HBr HCl. The cleavage of ethers takes place with concentrated high or HBr at high temperature. 1,1,6. 2 physical properties. 1,1,6. 3 chemical reactions. 348 Chemistry. The reaction of an ether with concentrated high starts with protonation of ether molecule. Step 1. The reaction takes place with HBr or high because these reagents are sufficiently acidic. Step 2. Iodide is a good nucleophile. It attacks the least substituted carbon of the oxonium ion formed in step 1 and displaces an alcohol molecule by SN2 mechanism. Thus, in the cleavage of mixed ethers with two different alkyl groups, the alcohol and alkyl iodide formed depend on the nature of alkyl groups. When primary or secondary alkyl groups are present, it is the lower alkyl group that forms alkyl iodide SN2 reaction. When high is in excess then the reaction is carried out at high temperature, ethanol reacts with another molecule of high and is converted to ethyl iodide. Step 3. Mechanism. Capital M, E, C, H, A, N, I, S, M. Capital M, E, C, H, A, N, I, S, M. Capital M, E, C, H, A, N, I, S, M. Capital M, E, C. However, when one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. CHCCH high CHOCH3333CH3CH3CH3CH3O. It is because in step 2 of the reaction, the departure of leaving group HO, CH3 creates a more stable carbocation CH33C, and the reaction follows SN1 mechanism. In case of anisole, methylphenyloxonium ion is formed by protonation of ether. The bond between O, CH3 is weaker than the bond between O, C6H5 because the carbon of phenyl group is sp2 hybridized and there is a partial double bond character. CH3CCH3CH3OH slow CH3CCH3CH3CHO3 fast CH3CCH3CH3CH3CH3  349 alcohols, phenols and ethers. Therefore the attack by I ion breaks O, CH3 bond to form CH3I. Phenols do not react further to give halides because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to the halide. Give the major products that are formed by heating each of the following ethers with high. Example 11.7 Example 11.7 Example 11.7 Example 11.7 Example 11.7 Solution 3I2 Electrophilic substitution. The alkoxy group is ortho, PODA directing and activates the aromatic ring towards electrophilic substitution in the same way as in phenol. Halogenation. Phenolacyl ethers undergo usual halogenation in the benzene ring, e.g., anisole undergoes bromination with bromine and ethanoic acid even in the absence of iron-3 bromide catalyst. It is due to the activation of benzene ring by the methoxy group. PODA isomer is obtained in 90 yield. 350 Chemistry in text questions 11.10 Write the reactions of Williamson synthesis of 2-ethoxy-3-methylpentane starting from ethanol and 3-methylpentane-2-ol. 11.11 Which of the following is an appropriate set of reactants for the preparation of 1-methoxy-4-nitrobenzene and why? I22 Friedel-Crafts reaction. Anisole undergoes Friedel-Crafts reaction. That is, the alkyl and acyl groups are introduced at ortho and PODA positions by reaction with alkyl halide and acyl halide in the presence of anhydrous aluminium chloride Lewis acid as catalyst. 3. Nitration. Anisole reacts with a mixture of concentrated sulfuric and nitric acids to yield a mixture of ortho and PODA nitronisole. 11.12 Predict the products of the following reactions. 3223CHCHCHO, CHHBrCHCOCH-3325325 alcohols and phenols are classified I on the basis of the number of hydroxyl groups and 2 according to the hybridization of the carbon atom, sp3 or sp2 to which the O group is attached. Ethers are classified on the basis of groups attached to the oxygen atom. Alcohols may be prepared 1 by hydration of alkenes I in presence of an acid and 2 by hydroboration oxidation reaction 2 from carbonyl compounds by I catalytic reduction and to the action of Grignard reagents. Phenols may be prepared by 1 substitution of I halogen atom in haloarenes and 2 sulfonic acid group in aryl sulfonic acids. Biogroup 2 by hydrolysis of diazonium salts and 3 industrially from cumene. Alcohols are higher boiling than other classes of compounds, namely hydrocarbons, ethers and haloalkanes of comparable molecular masses. The ability of alcohols, phenols and ethers to form intermolecular hydrogen bonding with water makes them soluble in it. Alcohols and phenols are acidic in nature. Electron withdrawing groups in phenol increase its acidic strength and electron releasing groups decrease it. Alcohols undergo nucleophilic substitution with hydrogen halides to yield alkyl halides. Dehydration of alcohols gives alkenes. On oxidation, primary alcohols yield aldehydes with mild oxidizing agents and carboxylic acids with strong oxidizing agents while secondary alcohols yield ketones.
Tertiary alcohols are resistant to oxidation. The presence of O group in phenols activates the aromatic ring towards electrophilic substitution and directs the incoming group to ortho and pod oppositions due to resonance effect. Reimer-Tiemann reaction of phenol yields salicylaldehyde. In presence of sodium hydroxide, phenol generates phenoxide ion, which is even more reactive than phenol. Thus, in alkaline medium, phenol undergoes Kolbe's reaction. Ethers may be prepared by dehydration of alcohols and 2-Williamson synthesis. The boiling points of ethers resemble those of alkanes while their solubility is comparable to those of alcohols having same molecular mass. The CO bond in ethers can be cleaved by hydrogen halides. In electrophilic substitution, the alkoxy group activates the aromatic ring and directs the incoming group to ortho and pod oppositions. Summary I. 352 Chemistry Exercises 11.1 Write IUPAC names of the following compounds: I23IVV789XC6H50, C2H5CC6H50, C7H15 and 12. 11.2 Write structures of the compounds whose IUPAC names are as follows: I2-methylbutanturol 2,1-phenylpropanturol 3,3, 5-dimethylhexane-1, 3, 5-triol-IVE2, 3-dethylphenyl V1-ethoxypropane V2-ethoxy 3-methylpentane 7-cyclohexylmethanolate 3-cyclohexylpentan 3-ol-9-cyclopen 3-N1-ol-X4-chloro 3-ethylbutan-1-ol. 11.3 I draw the structures of all isomeric alcohols of molecular formula C5H12O and give their IUPAC names. 2. Classify the isomers of alcohols in question. 11.3 I as primary, secondary and tertiary alcohols. 11.4 Explain why propanol has higher boiling point than that of the hydrocarbon. Butane. 11.5 Alcohols are comparatively more soluble in water than hydrocarbons of comparable molecular masses. Explain this fact. 11.6 What is meant by hydroboration oxidation reaction? Illustrate it with an example. 11.7 Give the structures and IUPAC names of monohydric phenols of molecular formula C7H8O. 11.8 While separating a mixture of ortho and pod on the trophenols by steam distillation, name the isomer which will be steam volatile. Give reason. 11.9 Give the equations of reactions for the preparation of phenol from cumene. 11.10 Write chemical reaction for the preparation of phenol from chlorobenzene. 11.11 Write the mechanism of hydration of ethene to yield ethanol. 11.12 You are given benzene, conc, H2SO4 and NaO. Write the equations for the preparation of phenol using these reagents. 11.13 Show how will you synthesize I1-phenylethanol from a suitable alkene 2-cyclohexylmethanol using an alkyl halide by an SN2 reaction. 3-pentan-1-ol using a suitable alkyl halide. 11.14 Give two reactions that show the acidic nature of phenol. Compare acidity of phenol with that of ethanol. 11.15 Explain why is orthonitrophenol more acidic than orthomethoxyphenol. 11.16 Explain how does the O group attached to a carbon of benzene ring activate it towards electrophilic substitution. 11.17 Give equations of the following reactions: I-oxidation of propan-1-ol with alkaline KMNO4 solution. 2-bromine and CS2 with phenol 3 dilute HNO3 with phenol IV treating phenol with chloroform in presence of aqueous NaO. 11.18 Explain the following with an example: I-Kolbe's reaction to Reimer-Tiemann reaction. 3 Williamson ether synthesis IV unsymmetrical ether. 11.19 Write the mechanism of acid dehydration of ethanol to yield ethene. 11.20 How are the following conversions carried out: I-propene propanturol to benzyl chloride benzyl alcohol. 3 ethyl magnesium chloride propan-1-ol IV methyl magnesium bromide to methylpropan-2-ol. 11.21 Name the reagents used in the following reactions: I-oxidation of a primary alcohol to carboxylic acid. 2 Oxidation of a primary alcohol to aldehyde. 3 Bromination of phenol to 2,4,6-tribromethanol. IV-benzyl alcohol to benzoic acid. V Dehydration of propanturol to propene V-butan-2,1 to butan-2-ol. 11.22 Give reason for the higher boiling point of ethanol in comparison to methoxymethane. 354 Chemistry. 11.23 Give IUPAC names of the following ethers. 11.24 Write the names of reagents and equations for the preparation of the following ethers by Williamson's synthesis: I1-propoxypropane 2-ethoxybenzene 3,2-methoxy-2-methylpropane IV1-methoxyethane. 11.25 Illustrate with examples the limitations of Williamson's synthesis for the preparation of certain types of ethers. 11.26 How is 1-propoxypropane synthesized from propan-1-ol? Write mechanism of this reaction. 11.27 Preparation of ethers by acid dehydration of secondary or tertiary alcohols is not a suitable method. Give reason. 11.28 Write the equation of the reaction of hydrogen iodide with I1-propoxypropane 2-methoxybenzene and 3-benzyl ethyl ether.
11.29 Explain the fact that in aryl alkyl etherside the alkoxy group activates the benzene ring towards electrophilic substitution and 2 it directs the incoming substituents to ortho and pod oppositions in benzene ring. 11.30 Write the mechanism of the reaction of high with methoxymethane. 11.31 Write equations of the following reactions. I. Friedel-Crafts reaction, alkylation of anisole. 2. Nitration of anisole. 3. Bromination of anisole in ethanoic acid medium. I. Friedel-Crafts acetylation of anisole. 11.32 Show how would you synthesize the following alcohols from appropriate alkenes. CH3OOOI23 IV. 11.33 When 3-methylbutanol is treated with HBr, the following reaction takes place. Give a mechanism for this reaction. Hint: the secondary carbocation formed in step 2 rearranges to a more stable tertiary carbocation by a hydride ion shift from third carbon atom. 355 Alcohols, phenols and ethers. Answers to some in-text questions. 11.1 Primary alcohols I, 2. 3 secondary alcohols IV and V. Tertiary alcohols V. 11.2 Allylic alcohols 2 and V. 11.3 I4 chloro 3 ethyl 2 1 methylethylbutane 1 al 2 2. 5 dimethylhexane 1. 3 diol 3 3 bromocyclohexanol IV hex 1 and 3 al V2 bromo 3 methylbut 2 and 1 al 11.4 11.5 CH3 CH3 CHIOO2 CH2 COC3 O CH3 CHO2 CH3 CH3 CH2 11.7 I1 methylcyclohexene 2A mixture of but 1 ene and but 2 ene. But 2 ene is the major product formed due to rearrangement to give secondary carbocation. 11.10 CHO2 5 CH3 CH2 CH3CH, and Na CH3HBr CHBr2 5 CHBr2 5 CH3CH2CH, CH3CH, OCH2 5 CH3 2 ethoxy 3 methylpentane. 356 Chemistry. 11.11 to 11.12 I3223 CHCH CHOCHBr23 I3253 CHCI After studying this unit, you will be able to write the common and IUPAC names of aldehydes, ketones and carboxylic acids. Write the structures of the compounds containing functional groups, namely carbonyl and carboxyl groups. Describe the important methods of preparation and reactions of these classes of compounds. Correlate physical properties and chemical reactions of aldehydes, ketones and carboxylic acids, with their structures. Explain the mechanism of a few selected reactions of aldehydes and ketones. Understand various factors affecting the acidity of carboxylic acids and their reactions. Describe the uses of aldehydes, ketones and carboxylic acids. Objectives. Carbonyl compounds are of utmost importance to organic chemistry. They are constituents of fabrics, flavorings, plastics and drugs. 12 Unit 12. Capital A, L, D, E, H, Y, D, E, S, capital A, L, D, E, H, Y, D, E, S, capital A, L, D, E, H, Y, D, E, S, capital A, L, D. Ketones, tonastones and carboxylic AAA acids aldehydes Ketones, tonastones and carboxylic AAA acids. In the previous unit, you have studied organic compounds with functional groups containing carbon-oxygen single bond. In this unit, we will study about the organic compounds containing carbon-oxygen double bond, called carbonyl group, which is one of the most important functional groups in organic chemistry. In aldehydes, the carbonyl group is bonded to a carbon and hydrogen, while in the ketones, it is bonded to 2 carbon atoms. The carbonyl compounds in which carbon of carbonyl group is bonded to carbon or hydrogen and oxygen of hydroxyl moiety are known as carboxylic acids. While in compounds where a carbon is attached to carbon or hydrogen and nitrogen of NH2 moiety or to halogens are called amides and acyl halides respectively. Esters and anhydrides are derivatives of carboxylic acids. The general formulas of these classes of compounds are given below. 2019-2. 358 Chemistry. Aldehydes, ketones and carboxylic acids are widespread in plants and animal kingdom. They play an important role in biochemical processes of life. They add fragrance and flavor to nature. For example, vanillin from vanilla beans, salicylaldehyde from meadowsweet and cinnamaldehyde from cinnamon have very pleasant fragrances. 1 Nomenclature. Aldehydes and ketones. Aldehydes and ketones are the simplest and most important carbonyl compounds. There are 2 systems of nomenclature of aldehydes and ketones of common names. Aldehydes and ketones are often called by their common names instead of IUPAC names. The common names of most aldehydes are derived from the common names of the corresponding carboxylic acids section 1, 2, 6, 1 by replacing the ending -ic of acid with aldehyde. At the same time, the names reflect the Latin or Greek term for the original source of the acid or aldehyde. The location of the substituent in the carbon chain is indicated by Greek letters, Greek letter alpha, Greek letter beta, Greek letter gamma, Greek letter delta, etc. The Greek letter alpha carbon being the one directly linked to the aldehyde group, Greek letter beta carbon the next, and so on. For example, 1,2, 1,1,2, 1,1,2, 1,1,2, 1,1,2, 1 nomenclature and structure of carbonyl group, 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 nomenclature and structure of carbonyl group. They are used in many food products and pharmaceuticals to add flavors. Some of these families are manufactured for use as solvents, that is, acetone, and for preparing materials like adhesives, paints, resins, perfumes, plastics, fabrics, etc. 359 Aldehydes, ketones and carboxylic acids. The common names of ketones are derived by naming two alkyl or aryl groups bonded to the carbonyl group. The locations of substituents are indicated by Greek letters, Greek letter alpha, Greek letter alpha, Greek letter beta, and so on, beginning with the carbon atoms next to the carbonyl group, indicated as Greek letter alpha, Greek letter alpha. Some ketones have historical common names. The simplest dimethyl ketone is called acetone. Alkyl phenyl ketones are usually named by adding the name of acyl group as prefix to the word phenone. For example, BIUPAC names. The IUPAC names of open-chain aliphatic aldehydes and ketones are derived from the names of the corresponding alkanes by replacing the ending E with al and 1 respectively. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehyde group, while in case of ketones the numbering begins from the end nearer to the carbonyl group. The substituents are prefixed in alphabetical order along with numerals indicating their positions in the carbon chain. The same applies to cyclic ketones, where the carbonyl carbon is numbered 1. When the aldehyde group is attached to a ring, the suffix carbaldehyde is added after the full name of the cycloalkane. The numbering of the ring carbon atoms start from the carbon atom attached to the aldehyde group. The name of the simplest aromatic aldehyde carrying the aldehyde group on a benzene ring is benzenic carbaldehyde. However, the common name benzaldehyde is also accepted by IUPAC. Other aromatic aldehydes are hence named as substituted benzaldehydes. 360 Chemistry aldehydes. HCHO formaldehyde, methanol, CH3CHO acetaldehyde, ethanol, CH3,2-CHCHO isobutyraldehyde, 2-methylpropanol, Greek letter gamma, methylcyclohexanicarbaldehyde, 3-methylcyclohexanicarbaldehyde, CH3CHO 3CHO, Greek letter alpha, methoxypropionylaldehyde, 2-methoxypropanol, CH3CH2CH2CH2 chovaloraldehyde, pentanol, CH2CHCHO acrolein prop, 2-enolphtaldehyde, benzene 1. 2-decarbaldehyde and bromobenzaldehyde, 3-bromobenzaldehyde ketone, CH3-COC2CH2CH3 methyl and propyl ketone, pentan 2,1-CH3,2-CHCO, CH3,2-diisopropyl ketone 2. 4-dimethyl-pentan 3,1 Greek letter alpha, methylcyclohexanone, 2-methylcyclohexanone, CH3,2-CCHCO, CH3-mecytyloxide, 4-methylpent 3N2,1 Table 12.1. Common and IUPAC names of some aldehydes and ketones. Structure. Common name, IUPAC name. A common and IUPAC names of some aldehydes and ketones are given in Table 12.1. Or 3-bromobenzenicarbaldehyde. 361 Aldehydes, ketones and carboxylic acids. The carbonyl carbon atom is sp2 hybridized and forms 3 sigma Greek letter sigma bonds. The fourth valence electron of carbon remains in its p orbital and forms a Greek letter pi bond with oxygen by overlap with p orbital of an oxygen. In addition, the oxygen atom also has 2 non-bonding electron pairs. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane, and the Greek letter pi electron cloud is above and below this plane. The bond angles are approximately 120 degrees as expected of a trigonal coplanar structure. Figure 12.1. 1,2,1,2 Structure of the carbonyl group, Greek letter pi. Figure 12.1 Orbital diagram for the formation of carbonyl group. The carbon-oxygen double bond is polarized due to higher electronegativity of oxygen relative to carbon. Hence, the carbonyl carbon is an electrophilic Lewis acid, and carbonyl oxygen, a nucleophilic Lewis base center. Carbonyl compounds have substantial dipole moments and are polar than ethers. The high polarity of the carbonyl group is explained on the basis of resonance involving a neutral A and a dipolar B structures as shown. In text questions 12.1 write the structures of the following compounds. A Greek letter alpha, methoxypropionylaldehyde, 2,3-hydroxybutanol, 3,2-hydroxycyclopentane carbaldehyde, I,4-oxypentanol, VD-sec. Butyl ketone V4-fluoroacetophenone. Some important methods for the preparation of aldehydes and ketones are as follows. 1. By oxidation of alcohols. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols, respectively. Unit 11, Class 12. 2. By dehydrogenation of alcohols. This method is suitable for volatile alcohols and is of industrial application. In this method, alcohol vapors are passed over heavy metal catalysts. Agar-Q. Primary and secondary alcohols give aldehydes and ketones, respectively. Unit 11, Class 12. 3. From hydrocarbons. Iosonolysis of alkenes. As we know, ozonolysis of alkenes followed by reaction with ink dust and water gives aldehydes. 1-2. 1. Preparation of aldehydes and ketones. 12.212. 212. 212. 212. 2. Preparation of aldehydes. Preparation of aldehydes. Preparation of aldehydes. Preparation of aldehydes. Preparation of aldehydes and ketones and ketones and ketones and ketones and ketones. 362. Chemistry. Ketones or a mixture of both depending on the substitution pattern of the alkene. Unit 13, Class I. 2. By hydration of alkynes. Addition of water to ethene in the presence of H2SO4 and HexO4 gives acetaldehyde. All other alkynes give ketones in this reaction. Unit 13, Class I1. From acyl chloride. Acid chloride. Acyl chloride. Acid chloride is hydrogenated over catalyst, palladium on barium sulfate. This reaction is called Rosenman reduction. 2. From nitriles and esters. Nitriles are reduced to corresponding imine with stannous chloride in the presence of hydrochloric acid, which on hydrolysis give corresponding aldehyde. This reaction is called Stevin reaction. Alternatively, nitriles are selectively reduced by diisobutyl aluminium hydride. Dibyl H2 imines followed by hydrolysis to aldehydes. 1-2. Preparation of aldehydes. Similarly, esters are also reduced to aldehydes with dibyl H3. From hydrocarbons. Aromatic aldehydes. Benzaldehyde and its derivatives are prepared from aromatic hydrocarbons by the following methods. I. By oxidation of methylbenzene. Strong oxidizing agents oxidize toluene and its derivatives to benzoic acids. However, it is possible to stop the oxidation at the aldehyde stage with suitable reagents that convert the methyl group to an intermediate that is difficult to oxidize further. The following methods are used for this purpose. A use of chromyl chloride Cro2Cl2. Chromyl chloride oxidizes methyl group to a chromium complex, which on hydrolysis gives corresponding benzaldehyde. 363. Aldehydes, ketones and carboxylic acids. This reaction is called Eddard reaction. By use of chromic oxide Cro3, toluene or substituted toluene is converted to benzylidene diacetate on treating with chromic oxide and acetic anhydride. The benzylidene diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. 3. By Gattermann, Koch reaction. When benzene or its derivative is treated with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminium chloride or cuprous chloride, it gives benzaldehyde or substituted benzaldehyde. 2. By side chain chlorination followed by hydrolysis. Side chain chlorination of toluene gives benzol chloride, which on hydrolysis gives benzaldehyde. This is a commercial method of manufacture of benzaldehyde. This reaction is known as Gattermann-Koch reaction. 1. From acyl chlorides. Treatment of acyl chlorides with dialkyl cadmium, prepared by the reaction of cadmium chloride with Grignard reagent, gives ketones. 1-2. 3. Preparation of ketones. 364. Chemistry. 2. From nitriles. Treating a nitrile with Grignard reagent followed by hydrolysis yields a ketone. Give names of the reagents to bring about the following transformations. Ihexan 1 aldohexanol 2 cyclohexanol 2 cyclohexanone 3 p-fluorotoluene 2 ivethanonetrol 2 ethanol p-fluorobenzaldehyde v allyl alcohol to propanol v but 2 eani 2 ethanol IC5H5NH Cro 3 ClPCC2 anhydrous Cro 3 3 Cro 3 in the presence of diisobutyl aluminium of acetic anhydride dibyl H1 Cro 2 Cl2 2 HOVPCCBO3 H2OZN dust. Example 12.1 Example 12.1 Example 12.1 Example 12.1 Example 12.1 Solution C6HCHCD2CH5223 Cockle CH3 number 21 Cro Cl222H3O3CCHHG2 HSO24HC3 IV in text question 12. To write the structures of products of the following reactions. I-2-3. From benzene or substituted benzenes. When benzene or substituted benzene is treated with acid chloride in the presence of anhydrous aluminium chloride, it affords the corresponding ketone. This reaction is known as Friedel-Crafts acylation reaction. 365. Aldehydes, ketones and carboxylic acids. The physical properties of aldehydes and ketones are described as follows. Methanol is a gas at room temperature. Ethanol is a volatile liquid. Other aldehydes and ketones are liquid or solid at room temperature. The boiling points of aldehydes and ketones are higher than hydrocarbons and ethers of comparable molecular masses. It is due to weak molecular association in aldehydes and ketones arising out of the dipole-dipole interactions. Also, their boiling points are lower than those of alcohols of similar molecular masses due to absence of intermolecular hydrogen bonding. The following compounds of molecular masses 58 and 60 are ranked in order of increasing boiling points. BPK molecular mass N-butane 273 58 methoxyethane 281 60 propanol 322 58 acetone 329 58 propan 1 al 370 60. The lower members of aldehydes and ketones such as methanol, ethanol and propanone are miscible with water in all proportions, because they form hydrogen bond with water. However, the solubility of aldehydes and ketones decreases rapidly on increasing the length of alkyl chain. All aldehydes and ketones are fairly soluble in organic solvents like benzene, ether, methanol, chloroform, etc. The lower aldehydes have sharp pungent odors. As the size of the molecule increases, the odor becomes less pungent and more fragrant. In fact, many naturally occurring aldehydes and ketones are used in the blending of perfumes and flavoring agents. 12.3 Physical 12.3 Physical 12.3 Physical 12.3 Physical 12.3 Physical properties Arrange the following compounds in the increasing order of their boiling points: CH3CH2CH2CHO, CH3CH2CH2CH2O, H5C2OC2H5, CH3CH2CH2CH3. The molecular masses of these compounds are in the range of 72 to 74. Since only butanol molecules are associated due to extensive intermolecular hydrogen bonding, therefore, the boiling point of butanol would be the highest. Butanol is more polar than ethoxyethane, therefore, the intermolecular dipole-dipole attraction is stronger in the former. N-pentane molecules have only weak van der Waals forces. Hence increasing order of boiling points of the given compounds is as follows: CH3CH2CH2CH3, H5C2OC2H5, CH3CH2CH2CHO, CH3CH2CH2CH2O. Example 12.2 Example 12.2 Example 12.2 Example 12.2 Example 12.2 Solution. Since aldehydes and ketones both possess the carbonyl functional group, they undergo similar chemical reactions. 1. Nucleophilic addition reactions. Contrary to electrophilic addition reactions observed in alkenes refer Unit 13, Class Xi, the aldehydes and ketones undergo nucleophilic addition reactions. A mechanism of nucleophilic addition reactions: a nucleophile attacks the electrophilic carbon atom of the polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbitals of carbonyl carbon Fig. 12.2. The hybridization of carbon changes from sp2 to sp3 in this process, and a tetrahedral alkoxide intermediate is produced. This intermediate captures a proton from the reaction medium to give the electrically neutral product. The net result is addition of Nu and H across the carbon-oxygen double bond as shown in Figure 12.2. In text question 12.3 arrange the following compounds in increasing order of their boiling points: CH3CHO, CH3CH2O, CH3OC3, CH3CH2CH3. Figure 12.2, nucleophilic attack on carbonyl carbon. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reactions than propanol? Explain your answer. The carbon atom of the carbonyl group of benzaldehyde is less electrophilic than carbon atom of the carbonyl group present in propanol. The polarity of the carbonyl group is reduced in benzaldehyde due to resonance as shown below, and hence it is less reactive than propanol. Example 12.3 Example 12.3 Example 12.3 Example 12.3 Example 12.3 Solution 2. Reactivity. Aldehydes are generally more reactive than ketones in nucleophilic addition reactions due to steric and electronic reasons. Sterically, the presence of two relatively large substituents in ketones hinders the approach of nucleophile to carbonyl carbon than in aldehydes having only one such substituent. Electronically, aldehydes are more reactive than ketones because two alkyl groups reduce the electrophilicity of the carbonyl carbon more effectively than in former. 12.4 Chemical 12.4 Chemical 12.4 Chemical 12.4 Chemical 12.4 Chemical reactions. Capital R E A C T I O N S. Capital R E A C T I O N S. Capital R E A C T I O N S. Capital R E A 3. Some important examples of nucleophilic addition and nucleophilic addition elimination reactions. Addition of hydrogen cyanide HCN. Aldehydes and ketones react with hydrogen cyanide HCN to yield cyanohydrins. This reaction occurs very slowly with pure HCN, therefore, it is catalyzed by a base and the generated cyanide ion CN, being a stronger nucleophile, readily adds to carbonyl compounds to yield corresponding cyanohydrin. Cyanohydrins are useful synthetic intermediates. B. Addition of sodium hydrogen sulfite. Sodium hydrogen sulfite adds to aldehydes and ketones to form the addition products. The position of the equilibrium lies largely to the right-hand side for most aldehydes and to the left for most ketones due to steric reasons. The hydrogen sulfite addition compound is water-soluble and can be converted back to the original carbonyl compound by treating it with dilute mineral acid or alkali. Therefore, these are useful for separation and purification of aldehydes. The addition of Grignard reagents. Refer Unit 11, Class 12. The addition of alcohols. Aldehydes react with one equivalent of monohydric alcohol in the presence of dry hydrogen chloride to yield alkoxy alcohol intermediate, known as hemiacetyls, which further react with one more molecule of alcohol to give a gem dialkoxy compound known as acetal, as shown in the reaction. Ketones react with ethylene glycol under similar conditions to form cyclic products known as ethylene glycol kettles. Dry hydrogen chloride protonates the oxygen of the carbonyl compounds and therefore increases the electrophilicity of the carbonyl, carbon facilitating. 368 Chemistry. The nucleophilic attack of ethylene glycol. Acetyls and kettles are hydrolyzed with aqueous mineral acids to yield corresponding aldehydes and ketones respectively. Addition of ammonia and its derivatives. Nucleophiles, such as ammonia and its derivatives H2 and Z, add to the carbonyl group of aldehydes and ketones. The reaction is reversible and catalyzed by acid. The equilibrium favors the product formation due to rapid dehydration of the intermediate to form CnZC alkyl, aryl, O, NH2, C6H5NH, NHCONH2, etc. Table 12.2. Some N-substituted derivatives of aldehydes and ketones. CnCH ammonia imine R amineo hydroxylamine oxymen H2 hydrazine hydrazone phenylhydrazine Z reagent name carbonyl derivative product name substituted imine. Shift space 2. 4-DNP derivatives are yellow, orange or red solids, useful for characterization of aldehydes and ketones. 2. 4-dinitrophenyl 2. 4-dinitrophenyl semicarbazide 2. Reduction I. Reduction to alcohols. Aldehydes and ketones are reduced to primary and secondary alcohols respectively by sodium borohydride NAD4 or lithium aluminium hydride LiAlH4 as well as by catalytic hydrogenation. Unit 11, Class 12. 2. Reduction to hydrocarbons. The carbonyl group of aldehydes and ketones is reduced to CH2 group on treatment with zinc amalgam and concentrated hydrochloric acid clemenzine hydrazine. Reduction or with hydrazine followed by heating with sodium or potassium hydroxide and high boiling solvents such as ethylene glycol. Wolff-Kishner reduction. 3. Oxidation. Aldehydes differ from ketones in their oxidation reactions. Aldehydes are easily oxidized to carboxylic acids on treatment with common oxidizing agents like nitric acid, potassium permanganate, potassium dichromate, etc. Even mild oxidizing agents, mainly Tollens reagent and Fellings reagent, also oxidize aldehydes. Ketones are generally oxidized under vigorous conditions, that is, strong oxidizing agents and at elevated temperatures. Their oxidation involves carbon-carbon bond cleavage to afford a mixture of carboxylic acids having lesser number of carbon atoms than the parent ketone. The mild oxidizing agents given below are used to distinguish aldehydes from ketones. Tollens test. On warming an aldehyde with freshly prepared ammoniacal silver nitrate solution Tollens reagent, a bright silver mirror is produced due to the formation of silver metal. The aldehydes are oxidized to corresponding carboxylate anion. The reaction occurs in alkaline medium. 2. Fellings test. Felling reagent comprises of two solutions, Felling solution A and Felling solution B. Felling solution A is aqueous copper sulfate and Felling solution B is alkaline sodium potassium tartarate Rochelle salt. These two solutions are mixed in equal amounts before test. On heating an aldehyde with Fellings reagent, a reddish-brown precipitate is obtained. Aldehydes are oxidized to corresponding carboxylate anion. Aromatic aldehydes do not respond to this test. Bernhard Tollens 1841–1918 was a professor of chemistry at the University of Göttingen, Germany. 370 Chemistry. Example 12.4 Example 12.4 Example 12.4 Example 12.4 Example 12.4 An organic compound A with molecular formula C8H8O forms an orange-red precipitate with 2,4-DNP reagent and gives yellow precipitate on heating with iodine in the presence of sodium hydroxide. It neither reduces Tollens or Fellings reagent, nor does it dechlorase bromine water or Bayer's reagent. On drastic oxidation with chromic acid, it gives a carboxylic acid B having molecular formula C7H6O2. Identify the compounds A and B and explain the reactions involved. A forms 2,4-DNP derivative. Therefore, it is an aldehyde or a ketone. Since it does not reduce Tollens or Felling reagent, A must be a ketone. A responds to iodoform test. Therefore, it should be a methyl ketone. The molecular formula of A indicates high degree of unsaturation, yet it does not dechlorase bromine water or Bayer's reagent. This indicates the presence of unsaturation due to an aromatic ring. Compound B, being an oxidation product of a ketone, should be a carboxylic acid. The molecular formula of B indicates that it should be benzoic acid and compound A should, therefore, be a monosubstituted aromatic methyl ketone. The molecular formula of A indicates that it should be phenylmethylketone acetophenone. Reactions are as follows: solution 3 oxidation of methyl ketones by haloform reaction. Aldehydes and ketones having at least one methyl group linked to the carbonyl carbon atom. Methyl ketones are oxidized by sodium hypohalite to sodium salts of corresponding carboxylic acids having one carbon atom less than that of carbonyl compound. The methyl group is converted to haloform. This oxidation does not affect a carbon-carbon double bond, if present in the molecule. Iodoform reaction with sodium hypoiodide is also used for detection of CH3CO group or CH3CHO group, which produces CH3CO group on oxidation. 4. Reactions due to a hydrogen acidity of Greek letter alpha hydrogens of aldehydes and ketones. The aldehydes and ketones undergo a number of reactions due to the acidic nature of Greek letter alpha hydrogen. The acidity of Greek letter alpha hydrogen atoms of carbonyl compounds is due to the strong electron withdrawing effect of the carbonyl group and resonance stabilization of the conjugate base. Aldol condensation. Aldehydes and ketones having at least one Greek letter alpha hydrogen undergo a reaction in the presence of dilute alkali as catalyst to form Greek letter beta hydroxyaldehydes. Aldol or Greek letter beta hydroxyketones ketol, respectively. This is known as aldol reaction. The name aldol is derived from the names of the two functional groups, aldehyde and alcohol, present in the products. The aldol and ketol readily lose water to give Greek letter alpha, Greek letter beta unsaturated carbonyl compounds, which are aldol condensation products, and the reaction is called aldol condensation. Though ketones give ketose compounds containing a keto and alcohol groups, the general name aldol condensation still applies to the reactions of ketones due to their similarity with aldehydes. 372 Chemistry 2 Cross-aldol condensation. When aldol condensation is carried out between two different aldehydes and or ketones, it is called cross-aldol condensation. If both of them contain Greek letter alpha hydrogen atoms, it gives a mixture of four products. This is illustrated below by aldol reaction of a mixture of ethanol and propanol. Ketones can also be used as one component in the cross-aldol reactions. 5. Other reactions. Alkanes reaction. Aldehydes which do not have a Greek letter alpha hydrogen atom, undergo self-oxidation and reduction disproportionation reaction on heating with concentrated alkali. In this reaction, one molecule of the aldehyde is reduced to alcohol while another is oxidized to carboxylic acid salt. 373 Aldehydes. Ketones and carboxylic acids. 2 Electrophilic substitution reaction. Aromatic aldehydes and ketones undergo electrophilic substitution at the ring in which the carbonyl group acts as a deactivating and meta-directing group. In text questions 12.4 arrange the following compounds in increasing order of their reactivity in nucleophilic addition reactions. Ethanol, propanol, propanone, butanone 2-benzaldehyde, p-tolualdehyde, p-nitrobenzaldehyde, acetophenone. Hint: consider steric effect and electronic effect. 12.5 Predict the products of the following reactions. I2,3-IV in chemical industry. Aldehydes and ketones are used as solvents. Starting materials and reagents for the synthesis of other products. Formaldehyde is well known as formalin 40 solution used to preserve biological specimens and to prepare bakelite of phenol formaldehyde resin. Urea formaldehyde glues and other polymeric products. Acetaldehyde is used primarily as a starting material in the manufacture of acetic acid, ethyl acetate, vinyl acetate, polymers and drugs. Benzaldehyde is used in perfumery and in dye industries. Acetone and ethyl methylketone are common industrial solvents. Many aldehydes and ketones, e.g., butyraldehyde, vanillin, acetophenone, camphor, etc. are well known for their odors and flavors. 12.512, 512, 5, 12, 512, 5. Uses of aldehydes and ketones and ketones. 374 Chemistry structure. Common name IUPAC name HCOOH. Formic acid, methanoic acid, CH3 CoO, acetic acid, ethanoic acid, CH3 CH2 CoO, propionic acid, propanoic acid, CH3 CH2 CH2 CoO, butyric acid, butanoic acid, CH3 2 CHCOOH, isobutyric acid 2 methylpropanoic acid hook, chloroxylic acid, ethanedioic acid hook, CH2 CoO, malonic acid, propanedioic acid hook, CH2 2 CoO, succinic acid, butanedioic acid hook, CH2 3 CoO, glutaric acid, pentanedioic acid hook, CH2 4 CoO, adipic acid, hexane dioic acid hook, CH2 CH CoO, CH2 CoO, tercarboxylic acid, propane 1 2 3 or carboxylic acid, tricarboxylic acid. Carboxylic acids. Carbon compounds containing a carboxyl functional group, CoO, are called carboxylic acids. The carboxyl group consists of a carbonyl group attached to a hydroxyl group, hence its name carboxyl. Carboxylic acids may be aliphatic RCOOH or aromatic RCOO depending on the group, alkyl or aryl, attached to carboxylic carbon. Large number of carboxylic acids are found in nature. Some higher members of aliphatic carboxylic acid C12C18 known as fatty acids, occur in natural fats as esters of glycerol. Carboxylic acids serve as starting material for several other important organic compounds such as anhydrides, esters, acid chlorides, amides, etc. Since carboxylic acids are amongst the earliest organic compounds to be isolated from nature, a large number of them are known by their common names. The common names end with the suffix -ic acid and have been derived from Latin or Greek names of their natural sources. For example, formic acid HCOOH was first obtained from red ants Latin, formica means and, acetic acid CH3 CoO from vinegar Latin, acetum, means vinegar, butyric acid CH3 CH2 CH2 CoO from rancid butter Latin, butyrum, means butter. In the IUPAC system, aliphatic carboxylic acids are named by replacing the ending E in the name of the corresponding alkane with oic acid. In numbering the carbon chain, the carboxylic carbon is numbered 1, for naming compounds containing more than one carboxyl group. The alkyl chain leaving carboxyl groups is numbered and the number of carboxyl groups is indicated by adding the multiplicative prefix, dicarboxylic acid, tricarboxylic acid, etc. To the name of parent alkyl chain, the position of CoO groups are indicated by the Arabic numeral before the multiplicative prefix. Some of the carboxylic acids along with their common and IUPAC names are listed in Table 12.3. 12.612, 612, 612, 612, 6. Nomenclature and structure of carboxyl group. 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 Table 12.3 Names and structures of some carboxylic acids. 1 2 6 1 Nomenclature. Benzoic acid, benzenic carboxylic acid, benzoic acid, phenylacetic acid, 2 phenylethanoic acid, phthalic acid, benzene 1 2 dicarboxylic acid. In carboxylic acids, the bonds to the carboxyl carbon lie in one plane and are separated by about 120 degrees. The carboxylic carbon is less electrophilic than carbonyl carbon because of the possible resonance structure shown below. 1 2 6 2 Structure of carboxyl group. In text question. In text question. In text question. In text question. In text question 12.6 Give the IUPAC names of the following compounds: IPHCH2CH2 CoO2CH3 2CCHCOOH3 CoCH3 IV. Some important methods of preparation of carboxylic acids are as follows. 1. From primary alcohols and aldehydes. Primary alcohols are readily oxidized to carboxylic acids with common oxidizing agents such as potassium permanganate KMNO4 and neutral. Acidic or alkaline media or by potassium dichromate K2Cr2O7 and chromium trioxide Cro3 in acidic media. Jones reagent. 12.712, 712, 712, 712, 7. Methods of preparation of carboxylic acids. Jones reagent. 376 Chemistry. Carboxylic acids are also prepared from aldehydes by the use of mild oxidizing agents. Section 12.4. 2. From alkyl benzenes. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic or alkaline potassium permanganate. The entire side chain is oxidized to the carboxyl group irrespective of length of the side chain. Primary and secondary alkyl groups are oxidized in this manner while tertiary group is not affected. Suitably substituted alkenes are also oxidized to carboxylic acids with these oxidizing reagents. Refer Unit 13, Class I. 3. From nitriles and amides, nitriles are hydrolyzed to amides and then to acids in the presence of HRO as catalyst. Mild reaction conditions are used to stop the reaction at the amide stage 4. From Grignard reagents react with carbon dioxide dry ice to form salts of carboxylic acids, which in turn give corresponding carboxylic acids after acidification with mineral acid. As we know, the Grignard reagents and nitriles can be prepared from alkyl halides. Refer Unit 10, Class 12. The above methods. 377 Aldehydes. Ketones and carboxylic acids 3 and 4 are useful for converting alkyl halides into corresponding carboxylic acids having one carbon atom more than that present in alkyl halides ascending the series. 5. From acyl halides and anhydrides, acid chlorides when hydrolyzed with water give carboxylic acids, or more readily hydrolyzed with aqueous base to give carboxylate ions, which on acidification provide corresponding carboxylic acids. Anhydrides on the other hand are hydrolyzed to corresponding acid S with water. 6. From esters, acidic hydrolysis of esters gives directly carboxylic acids, while basic hydrolysis gives carboxylates, which on acidification give corresponding carboxylic acids. Example 12.5 Example 12.5 Example 12.5 Example 12.5 Example 12.5 Write chemical reactions to effect the following transformations: ibutane 1-ol to butanoic acid 2 benzyl alcohol to phenylethanoic acid 3 nitrobromobenzene to 3 nitrobenzoic acid I4 methylacetophenone to benzene 1 dicarboxylic acid V cyclohexene to hexane 1 dioic acid V butanol to butanoic acid. 378 Chemistry in text question 12.7 Show how each of the following compounds can be converted to benzoic acid. Ethylbenzene 2-acetophenone 3-bromobenzene I-phenylethene styrene solution I2,3-IVV. 379 Aldehydes, ketones and carboxylic acids. Aliphatic carboxylic acids up to 9 carbon atoms are colorless liquids at room temperature with unpleasant odors. The higher acids are wax-like solids and are practically odorless due to their low volatility. Carboxylic acids are higher boiling liquids than aldehydes, ketones and even alcohols of comparable molecular masses. This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acids exist as dimer in the vapor phase or in the aprotic solvents. Simple aliphatic carboxylic acids having up to 4 carbon atoms are miscible in water due to the formation of hydrogen bonds with water. The solubility decreases with increasing number of carbon atoms. Higher carboxylic acids are practically insoluble in water due to the increased hydrophobic interaction of hydrocarbon part. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform, etc. The reaction of carboxylic acids are classified as follows: acidity reactions with metals and alkalis. The carboxylic acids, like alcohols, evolve hydrogen with electropositive metals and form salts with alkalis similar to phenols. However, unlike phenols, they react with weaker bases such as carbonates and hydrogen carbonates to evolve carbon dioxide. This reaction is used to detect the presence of carboxyl group in an organic compound. Carboxylic acids dissociate in water to give resonance-stabilized carboxylate anions and hydronium ion. 1,2,9, 1 reactions involving cleavage of OH bond 12.812, 812, 8, 12, 812, 8, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C. Properties 12.912, 912, 9, 12, 912, 9. Chemical reactions Chemical reactions in vapor state or in a product solvent. Hydrogen bonding of RCOOH with H2O. 380 Chemistry, where K is equilibrium constant and Ka is the acid dissociation constant. For convenience, the strength of an acid is generally indicated by its pK value rather than its Ka value. pK log Ka. The pK of hydrochloric acid is -7.0, whereas pK of trifluoroacetic acid, the strongest carboxylic acid, benzoic acid and acetic acid, are 0.23, 4.19 and 4.76, respectively. Smaller the pK, the stronger the acid, the better it is as a proton donor. Strong acids have pK values 1. The acids with pK values between 1 and 5 are considered to be moderately strong acids. Weak acids have pK values between 5 and 15, and extremely weak acids have pK values 15. Carboxylic acids are weaker than mineral acids, but they are stronger acids than alcohols and many simple phenols. pKa is 16 for ethanol and 10 for phenol. In fact, carboxylic acids are amongst the most acidic organic compounds you have studied so far. You already know why phenols are more acidic than alcohols. The higher acidity of carboxylic acids as compared to phenols can be understood similarly. The conjugate base of carboxylic acid, a carboxylate ion, is stabilized by two equivalent resonance structures in which the negative charge is at the more electronegative oxygen atom. The conjugate base of phenol, a phenoxide ion, has non-equivalent resonance structures in which the negative charge is at the less electronegative carbon atom. Therefore, resonance in phenoxide ion is not as important as it is in carboxylate ion. Further, the negative charge is delocalized over two electronegative oxygen atoms in carboxylate ion, whereas it is less effectively delocalized over one oxygen atom and less electronegative carbon atoms in phenoxide ion. Unit 11, Class 12. Thus, the carboxylate ion is more stabilized than phenoxide ion, so carboxylic acids are more acidic than phenols. Effect of substituents on the acidity of carboxylic acids. Substituents may affect the stability of the conjugate base and thus, also affect the acidity of the carboxylic acids. Electron withdrawing groups increase the acidity of carboxylic acids by stabilizing the conjugate base through delocalization of the negative charge by inductive and/or resonance effects. Conversely, electron donating groups decrease the acidity by destabilizing the conjugate base. Electron withdrawing group EWG stabilizes the carboxylate anion and strengthens the acid. Electron donating group EDG destabilizes the carboxylate anion and weakens the acid. The effects of the following groups in increasing acidity order is pH, I, BrCl, F, Cn, number 2, CF3. Thus, the following acids are arranged in order of increasing acidity based on pKa values: CF3Cu, CCl3Cu, CHCl2Cu, number 2 CH2Cu, NCCH2Cu, FCH2Cu, ClCH2Cu, BrCH2Cu, HCOOH, ClCH2CH2Cu, continue C6H5Cu, C6H5CH2Cu, CH3Cu, CH3CH2Cu. Continue. Direct attachment of groups such as phenyl or vinyl to the carboxylic acid increases the acidity of corresponding carboxylic acid, contrary to the decrease expected due to resonance effect shown below. This is because of greater electronegativity of sp2 hybridized carbon to which carboxyl carbon is attached. The presence of electron withdrawing group on the phenyl of aromatic carboxylic acid increases their acidity while electron donating groups decrease their acidity. CuOC3Cu number 2 4-methoxybenzoic acid P4.46 Ca benzoic acid P4.19 Ca 4 nitrobenzoic acid P3.41 Ca 1. Formation of anhydride carboxylic acids on heating with mineral acids such as H2SO4 or with P2O5 give corresponding anhydride. 2. Esterification. Carboxylic acids are esterified with alcohols or phenols in the presence of a mineral acid such as concentrated H2SO4 or HCl gas as a catalyst. 1-2-9. 2 reactions involving cleavage of CO bond. 382 Chemistry mechanism of esterification of carboxylic acids. The esterification of carboxylic acids with alcohols is a kind of nucleophilic acyl substitution. Protonation of the carbonyl oxygen activates the carbonyl group towards nucleophilic addition of the alcohol. Proton transfer in the tetrahedral intermediate converts the hydroxyl group into O2 group, which, being a better leaving group, is eliminated as neutral water molecule. The protonated ester so formed finally loses a proton to give the ester 3. Reactions with PCl5, PCl3 and Soc2. The hydroxyl group of carboxylic acids behaves like that of alcohols and is easily replaced by chlorine atom on treating with PCl5, PCl3 or Soc2. Thionyl chloride Soc2 is preferred because the other two products are gaseous and escape the reaction mixture, making the purification of the products easier. 4. Reaction with ammonia. Carboxylic acids react with ammonia to give ammonium salt, which on further heating at high temperature give amides. For example, 383 aldehydes, ketones and carboxylic acids. 1-2-9. 3 reactions involving Cu group 1. Reduction. Carboxylic acids are reduced to primary alcohols by lithium aluminium hydride or better with diborane. Diborane does not easily reduce functional groups such as ester, nitro, halo, etc. Sodium borohydride does not reduce the carboxyl group. 2. Decarboxylation. Carboxylic acids lose carbon dioxide to form hydrocarbons when their sodium salts are heated with salt-lime NaOH in the ratio of 3:1. The reaction is known as decarboxylation. Alkali metal salts of carboxylic acids also undergo decarboxylation on electrolysis of their aqueous solutions and form hydrocarbons having twice the number of carbon atoms present in the alkyl group of the acid. The reaction is known as Kolbe electrolysis Unit 13, Class Psi1. Halogenation. Carboxylic acids having in Greek letter alpha hydrogen are halogenated at the Greek letter alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus to give Greek letter alpha halocarboxylic acids. The reaction is known as Haloarenes reaction 1,2,9, 4 substitution reactions in the hydrocarbon part. 384 Chemistry 12.10 1012 1012 1012 10 Uses of carboxylic acids. Summary. Aldehydes, ketones and carboxylic acids are some of the important classes of organic compounds containing carbonyl group. These are highly polar molecules, therefore, they boil at higher temperatures than the hydrocarbons and weakly polar compounds such as ethers of comparable molecular masses. The lower members are more soluble in water because they form hydrogen bonds with water. The higher members, because of large size of hydrophobic chain of carbon atoms, are insoluble in water but soluble in common organic solvents. Aldehydes are prepared by dehydrogenation or controlled oxidation of primary alcohols and controlled or selective reduction of acyl halides. Aromatic aldehydes may also be prepared by oxidation of imethylbenzene with chromyl chloride or Cro3 in the presence of acetic anhydride. 2. Formulation of arenes with carbon monoxide and hydrochloric acid in the presence of anhydrous aluminium chloride, and 3. Cuprous chloride or by hydrolysis of benzoyl chloride. Ketones are prepared by oxidation of secondary alcohols and hydration of alkynes. Ketones are also prepared by reaction of acyl chloride with dialkyl cadmium. A good method for the preparation of aromatic ketones is the Friedel-Crafts acylation of aromatic hydrocarbons with acyl chlorides or anhydrides. Both aldehydes and ketones can be prepared by ozonolysis of alkenes. Aldehydes and ketones undergo nucleophilic addition reactions onto the carbonyl group with a number of nucleophiles such as HCN, NaSO3, alcohols or diols. 2. Ring substitution. Aromatic carboxylic acids undergo electrophilic substitution reactions in which the carboxyl group acts as a deactivating and meta-directing group. They, however, do not undergo Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst aluminium chloride Lewis acid gets bonded to the carboxyl group. In text question 12.8 Which acid of each pair shown here would you expect to be stronger? ICH3CO2H or CH2FCO2H2CH2FCO2H or CH2COCO2H3CH2FCH2CH2CO2H or CH3CHFCH2CO2H. Methanoic acid is used in rubber, textile, dyeing, leather and electroplating industries. Ethanoic acid is used as solvent and as vinegar in food industry. Hexane-dioic acid is used in the manufacture of nylon 6. Esters of benzoic acid are used in perfumery. Sodium benzoate is used as a food preservative. Higher fatty acids are used for the manufacture of soaps and detergents. 385 Aldehydes, ketones and carboxylic acids, ammonia derivatives, and Grignard reagents. The Greek letter alpha hydrogens in aldehydes and ketones are acidic. Therefore, aldehydes and ketones having at least one Greek letter alpha hydrogen undergo aldol condensation in the presence of a base to give Greek letter alpha hydroxyaldehydes aldol and Greek letter alpha hydroxyketones ketol, respectively. Aldehydes having no Greek letter alpha hydrogen undergo Cannizzaro reaction in the presence of concentrated alkali. Aldehydes and ketones are reduced to alcohols with NAD4, LiAlH4, or by catalytic hydrogenation. The carbonyl group of aldehydes and ketones can be reduced to a methylene group by Clemmensen reduction or Wolff-Kishner reduction. Aldehydes are easily oxidized to carboxylic acids by mild oxidizing reagents such as Tollens reagent and Fellings reagent. These oxidation reactions are used to distinguish aldehydes from ketones. Carboxylic acids are prepared by the oxidation of primary alcohols, aldehydes and alkenes by hydrolysis of nitriles, and by treatment of Grignard reagents with carbon dioxide. Aromatic carboxylic acids are also prepared by side chain oxidation of alkylbenzenes. Carboxylic acids are considerably more acidic than alcohols and most of simple phenols. Carboxylic acids are reduced to primary alcohols with LiAlH4, or better with diborane in ether solution, and also undergo Greek letter alpha halogenation with Cl2 and Br2 in the presence of red phosphorus Haloarenes reaction. Methanol, ethanol, propanone, benzaldehyde, formic acid, acetic acid and benzoic acid are highly useful compounds in industry. Exercises 12.1 What is meant by the following terms? Give an example of the reaction in each case. Icyanohydrin 2 acid al 3 semicarbazonide aldol v hemiacetyl v oxime 7 ketyl 7 imine 9 2. 4-DNP derivative X shift space 12.2 Name the following compounds according to IUPAC system of nomenclature. ICH3CH2CH2 CH2CH2 CH3CH2 CH2CH3CH2 CH3CH3CH2 Page 12.3 Draw the structures of the following compounds. I3-methylbutanol 2p-nitropropiophenone 3p-methylbenzaldehyde I4-methylpent3N21V4 chloropentan 21V3 bromo 4-phenylpentanoic acid 7p. P-dehydroxybenzophenone 8-hex2N4 anoic acid 12.4 Write the IUPAC names of the following ketones and aldehydes. Wherever possible, give also common names ICH3COCH2 4CH3CH2CH3CH3CH2 CH3CH3CH2 5CHOIV CHOV 12.5 Draw structures of the following derivatives. I2. 4-dinitrophenylhydrazone of benzaldehyde 2-cyclopropanone oxime 3-acetaldehydimethylacetyl the semicarbazone of cyclobutanone V the ethylene kettle of hexane 3,1V the methylhemiacetal of formaldehyde. 386 Chemistry 12.6 Predict the products formed when cyclohexanicarbaldehyde reacts with following reagents. IPHMGBr and NH3O2 Tollens reagent 3 semicarbazide and weak acid IV excess ethanol and acid V zinc amalgam and dilute hydrochloric acid 12.7 Which of the following compounds would undergo aldol condensation, which the Cannizzaro reaction and which neither? Write the structures of the expected products of aldol condensation and Cannizzaro reaction. I-methanol 2,2-methylpentanol 3-benzaldehyde I-benzophenone V-cyclohexanone V1-phenylpropanone 7-phenylacetaldehyde 8-butanol 9,2. 2-dimethylbutanol 12.8 How will you convert ethanol into the following compounds? Ibutane 1,3-diol-2-but-2-anyl 3-but-2 anoic acid 12.9 Write structural formulas and names of 4 possible aldol condensation products from propanol and butanol. In each case, indicate which aldehyde acts as nucleophile and which as electrophile. 12.10 An organic compound with the molecular formula C9H10O forms 2,4-DNP derivative, reduces Tollens reagent and undergoes Cannizzaro reaction. On vigorous oxidation, it gives 1,2-benzene-carboxylic acid. Identify the compound. 12.11 An organic compound A molecular formula CH16O2 was hydrolyzed with dilute sulfuric acid to give a carboxylic acid B and an alcohol C. Oxidation of C with chromic acid produced B. C on dehydration gives but 1 ENE. Write equations for the reactions involved. 12.12 Arrange the following compounds in increasing order of their property as indicated. I-acetaldehyde. Acetone, D-terc-butylketone, methyl-terc-butylketone reactivity towards HCN2CH3CH2CHBr-Cu. CH3CHBr-CH2-Cu, CH3-2CHCOOH, CH3CH2CH2-Cu acid strength 3-benzoic acid, 4-nitrobenzoic acid, 3,4-dinitrobenzoic acid, 4-methoxybenzoic acid strength 12.13 Give simple chemical tests to distinguish between the following pairs of compounds. I-propanol and propanone 2-acetophenone and benzophenone 3-phenol and benzoic acid I-benzoic acid and ethyl benzoate V-pentan 2,1 and pentan 3,1 V-benzaldehyde and acetophenone 7-ethanol and propanol 12.14 How will you prepare the following compounds from benzene? You may use any inorganic reagent and any organic reagent having not more than one carbon atom. I-methyl benzoate 2 meters nitrobenzoic acid 3p nitrobenzoic acid I-phenylacetic acid VP nitrobenzaldehyde. 12.15 How will you bring about the following conversions in not more than 2 steps? I-propanone to propene 2-benzoic acid to benzaldehyde 3-ethanol to 3-hydroxybutanol I-benzene to M-nitrosatophenone V-benzaldehyde to benzophenone V-bromobenzene to 1-phenylethanol 7-benzaldehyde to 3-phenylpropan-1-ol 8-benazaldehyde to Greek letter alpha hydroxyphenylacetic acid 9-benzoic acid to M-nitrobenzyl alcohol 12.16 Describe the following. I-acetylation 2 Cannizzaro reaction 3 cross-aldol condensation IV decarboxylation. 12.17 Complete each synthesis by giving missing starting material, reagent or products. 12.18 Give plausible explanation for each of the following. I-cyclohexanone forms cyanohydrin in good yield but 2,6-trimethylcyclohexanone does not. 2 There are 2 NH2 groups in semicarbazide, however, only one is involved in the formation of semicarbazones. 3 During the preparation of esters from a carboxylic acid and an alcohol in the presence of an acid catalyst, the water or the ester should be removed as soon as it is formed. 12.19 An organic compound contains 69.77 carbon, 11.63 hydrogen and rest oxygen. The molecular mass of the compound is 86. It does not reduce Tollens reagent but forms an addition compound with sodium hydrogen sulfide and give positive iodoform test. On vigorous oxidation it gives ethanoic and propanoic acid. Write the possible structure of the compound. 12.20 Although phenoxide ion has more number of resonating structures than carboxylate ion, carboxylic acid is a stronger acid than phenol. Y answers to some in-text questions 12.1 IV2V3V 388 Chemistry 12.3 CH3CH2CH3, CH3OC3, CH3CHO, CH3CH2O 12.4 Ibutanone, propanone, propanol, ethanol 2-acetophenone, P-tolualdehyde, benzaldehyde, P-nitrobenzaldehyde. 12.5 12.6 I3 phenylpropanoic acid 2,3-methylbut-2-anoic acid 3,2-methylcyclopentanoic carboxylic acid. IV2, 4, 6 trinitrobenzoic acid 12.7 12.8 12.2 I3 2 IV I3 2 IV I2 3 IV. Amines constitute an important class of organic compounds derived by replacing one or more hydrogen atoms of ammonia molecule by alkyl aryl group S. In nature, they occur among proteins, vitamins, alkaloids and hormones. Synthetic examples include polymers, dyestuffs and drugs. Two biologically active compounds, namely adrenaline and ephedrine, both containing secondary amino group, are used to increase blood pressure. Novocaine, a synthetic amino compound, is used as an anesthetic in dentistry. Benadryl, a well-known antihistaminic drug, also contains tertiary amino group. Quaternary ammonium salts are used as surfactants. Diazonium salts are intermediates in the preparation of a variety of aromatic compounds including dyes. In this unit, you will learn about amines and diazonium salts. Amines can be considered as derivatives of ammonia, obtained by replacement of one, two or all the three hydrogen atoms by alkyl and or aryl groups. For example, like ammonia, nitrogen atom of amines is trivalent and carries an unshared pair of electrons. Nitrogen orbitals in amines are therefore sp3 hybridized and the geometry of amines is pyramidal. Each of the three sp3 hybridized orbitals of nitrogen overlap with orbitals of hydrogen or carbon depending upon the composition of the amines. The fourth orbital of nitrogen in all amines contains an unshared pair of electrons, due to the presence of unshared pair of electrons. The angle CNE, whereas after studying this unit, you will be able to describe amines as derivatives of ammonia having a pyramidal structure, classify amines as primary, secondary and tertiary, name amines by common names and IUPAC system, describe some of the important methods of preparation of amines, explain the properties of amines, distinguish between primary, secondary and tertiary amines, describe the method of preparation of diazonium salts and their importance in the synthesis of a series of aromatic compounds including azo-dyes. Objectives: the chief commercial use of amines is as intermediates in the synthesis of medicines and fibers. Unit 13A amines means 13A amines means 13.1 Structure of amines 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 390 Chemistry CRH is less than 109.5 degrees. For instance, it is 108.0 in case of trimethylamine as shown in Fig. 13.1. Amines are classified as primary 1O, secondary 2O and tertiary 3O depending upon the number of hydrogen atoms replaced by alkyl or aryl groups in ammonia molecule. If one hydrogen atom of ammonia is replaced by R or R, we get RNH2 or ARN2, a primary amine A1O. If two hydrogen atoms of ammonia or one hydrogen atom of RNH2 are replaced by another alkyl aryl R group, what would you get? You get RNHR, secondary amine A. The second alkyl aryl group may be same or different. Replacement of another hydrogen atom by alkyl aryl group leads to the formation of tertiary amine A. Amines are said to be simple when all the alkyl or aryl groups are the same, and mixed when they are different. In common system, an aliphatic amine is named by prefixing alkyl group to amine A, that is, alkylamine as one word, e.g., methylamine. In secondary and tertiary amines, when two or more groups are the same, the prefix di or tri is appended before the name of alkyl group. In IUPAC system, primary amines are named as alkanamines. The name is derived by replacement of E of alkane by the word amine A. For example, CH3NH2 is named as methanamine, in case more than one amino group is present at different positions in the parent chain. Their positions are specified by giving numbers to the carbon atoms bearing NH2 groups and suitable prefix such as D, tri, etc. is attached to the amine, the letter E of the suffix of the hydrocarbon part is retained. For example, H2N, CH2, CH2, NH2 is named as ethane 1,2-diamine. To name secondary and tertiary amines, we use locant N to designate substituent attached to a nitrogen atom. For example, CH3NHCH2CH3 is 13.213, 213, 213, 213, 2, capital C, L, A, S, S, I, F, I, C, A, T, I, O, N, capital C, L, A, S, S, I, F, I, C, A, T, I, O, N, capital C, L, Fig. 13.1 Pyramidal shape of trimethylamine 13.313, 313, 313, 313, 3, capital N, O, M, E, N, C, L, A, T, U, R, E, capital N, O, M, E, N, C, L, A, T, U, R, E, capital N, O, M, E, N, C. Named as N-methylethanamine and CH3CH23N is named as N-ethylethanamine. More examples are given in Table 13.1. In arylamines, NH2 group is directly attached to the benzene ring. C6H5NH2 is the simplest example of arylamine. In common system, it is known as aniline. It is also an accepted IUPAC name. While naming arylamines according to IUPAC system, suffix E of arine is replaced by amine. Thus in IUPAC system, C6H5, NH2 is named as benzenamine. Common and IUPAC names of some alkylamines and arylamines are given in Table 13.1. Amine common name IUPAC name CH3CH2NH2 ethylamine ethanamine CH3, CH2, CH2, NH2N propylamine propan 1 amine isopropylamine propan 2 amine ethylmethylamine N-methylethanamine trimethylamine N. N-dimethylmethanamine N, N-dethylbutylamine N, N-dethylbutane 1 amine allylamine prop 2 and 1 amine hexamethylanidiamine hexane 1, 6-diamine aniline aniline or benzenamine O2-luidine 2-methylaniline P-bromonyline 4-bromobenzenamine or 4-bromonyline N, N-dimethylaniline N, N-dimethylbenzenamine Table 13.1, Nomenclature of some alkylamines and arylamines. 392 Chemistry amines are prepared by the following methods. 1. Reduction of nitrocompounds. Nitrocompounds are reduced to amines by passing hydrogen gas in the presence of finely divided nickel, palladium or platinum, and also by reduction with metals in acidic medium. Nitroalkanes can also be similarly reduced to the corresponding alkanamines. Reduction with iron scrap and hydrochloric acid is preferred because FeCl2 form gets hydrolyzed to release hydrochloric acid during the reaction. Thus, only a small amount of hydrochloric acid is required to initiate the reaction. 2. Ammonolysis of alkyl halides. You have read Unit 10, Class 12 that the carbon-halogen bond in alkyl or benzyl halides can be easily cleaved by a nucleophile. Hence, an alkyl or benzyl halide on reaction with an ethanolic solution of ammonia undergoes nucleophilic substitution reaction in which the halogen atom is replaced by an amino NH2 group. This process of cleavage of the CX bond by ammonia molecule is known as ammonolysis. The reaction is carried out in a sealed tube at 373 K. The primary amine thus obtained behaves as a nucleophile and can further react with alkyl halide to form secondary and tertiary amines. And finally quaternary ammonium salt 13.413, 413, 413, 413, 4. Preparation. Capital P R E P A R A T I O N, capital P R E P A R A T I O N, capital P R E P A R A T of amines of amines 13.1. Classify the following amines as primary, secondary or tertiary. 13.2. I write structures of different isomeric amines corresponding to the molecular formula. C4H11N2. Write IUPAC names of all the isomers. 3. What type of isomerism is exhibited by different pairs of amines? In text questions, in text questions, in text questions, in text questions, in text questions. 393 Amines. The free amine can be obtained from the ammonium salt by treatment with a strong base. Ammonolysis has the disadvantage of yielding a mixture of primary, secondary and tertiary amines and also a quaternary ammonium salt. However, primary amine is obtained as a major product by taking large excess of ammonia. The order of reactivity of halides with amines is Ri, RBr, RCl3, reduction of nitriles. Nitriles on reduction with lithium aluminium hydride LiAlH4 or catalytic hydrogenation produce primary amines. This reaction is used for ascent of amine series, that is, for preparation of amines containing one carbon atom more than the starting amine. 4. Reduction of amides. The amides on reduction with lithium aluminium hydride yield amines. Example 13.1 Example 13.1 Example 13.1 Example 13.1 Example 13.1 Solution Write chemical equations for the following reactions. A reaction of ethanolic NH3 with C2H5Cl. 2-ammo analysis of benzyl chloride and reaction of amine so formed with 2 moles of CH3Cl. 394 Chemistry 5. Gabriel phthalimide synthesis. Gabriel synthesis is used for the preparation of primary amines. Phthalimide on treatment with ethanolic potassium hydroxide forms potassium salt of phthalimide, which on heating with alkyl halide followed by alkaline hydrolysis produces the corresponding primary amine. Aromatic primary amines cannot be prepared by this method because aryl halides do not undergo nucleophilic substitution with the anion formed by phthalimide. 6. Hofmann-bromamide degradation reaction. Hofmann developed a method for preparation of primary amines by treating an amide with bromine in an aqueous or ethanolic solution of sodium hydroxide. In this degradation reaction, migration of an alkyl or aryl group takes place from carbonyl carbon of the amide to the nitrogen atom. The amine so formed contains 1 carbon less than that present in the amide. Write chemical equations for the following conversions. ICH3, CH2Cl into CH3, CH2, CH2, NH2 2C6H5, CH2Cl into C6H5, CH2, CH2, NH2. Example 13.2 Example 13.2 Example 13.2 Example 13.2 Example 13.2 Solution 395 Amines. The lower aliphatic amines are gases with fishy odor. Primary amines with 3 or more carbon atoms are liquid and still higher ones are solid. Aniline and other arylamines are usually colorless but get colored on storage due to atmospheric oxidation. Lower aliphatic amines are soluble in water because they can form hydrogen bonds with water molecules. However, solubility decreases with increase in molar mass of amines due to increase in size of the hydrophobic alkyl part. Higher amines are essentially insoluble in water, considering the electronegativity of nitrogen of amine and oxygen of alcohol as 3.0 and 3.5 respectively. You can predict the pattern of solubility of amines and alcohols in water. Out of butan-1-ol and butan-1-amine, which will be more soluble in water, and why amines are soluble in organic solvents like alcohol, ether and benzene. You may remember that alcohols are more polar than amines and form stronger intermolecular hydrogen bonds than amines. Primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen of one and hydrogen of another molecule. This intermolecular association is more in primary amines than in secondary amines, as there are 2 hydrogen atoms available for hydrogen bond formation in it. Tertiary amines do not have intermolecular association due to the absence of hydrogen atom available for hydrogen bond formation. Therefore, the order of boiling points of isomeric amines is as follows: 13.513, 513, 513, 513, 5, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C, A, L, capital P, H, Y, S, I, C. Properties 13.3 How will you convert ibenzene into aniline 2-benzene into N-dimethylanilane 3ClCH24Cl into hexane 1,6-diamine in text question Write structures and IUPAC names of the amide which gives propanamine by Hofmann-bromamide reaction. 2. The amine produced by the Hofmann degradation of benzamide ipropanamine contains 3 carbons. Hence, the amide molecule must contain 4 carbon atoms. Structure and IUPAC name of the starting amide with 4 carbon atoms are given below. Butanamide 2-benzamide is an aromatic amide containing 7 carbon atoms. Hence, the amine formed from benzamide is aromatic primary amine containing 6 carbon atoms. Aniline or benzenamine. Example 13.3 Example 13.3 Example 13.3 Example 13.3 Example 13.3 Solution. Capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I. 396 Chemistry. Primary, secondary, tertiary intermolecular hydrogen bonding in primary amines is shown in Fig. 13.2. Boiling points of amines, alcohols and alkanes of almost the same molar mass are shown in Table 13.2. Figure 13.2 Intermolecular hydrogen bonding in primary amines. Table 13.2. Comparison of boiling points of amines, alcohols and alkanes of similar molecular masses. SAO. No. Compound molar mass BPK1NC4H9NH273, 350, 8, 2. C2H52NH73, 329, 3, 3, C2H5NCH3273, 310, 5, 4. C2H5CHCH3272, 300, 8, 5. NC4H9074 390.3 Difference in electronegativity between nitrogen and hydrogen atoms and the presence of unshared pair of electrons over the nitrogen atom makes amines reactive. The number of hydrogen atoms attached to nitrogen atom also decides the course of reaction of amines. That is why primary NH2, secondary NH and tertiary amines N differ in many reactions. Moreover, amines behave as nucleophiles due to the presence of unshared electron pair. Some of the reactions of amines are described below. 1. Basic character of amines. Amines, being basic in nature, react with acids to form salts 13.613, 613, 6, 13, 613, 6, capital C, H, E, M, I, C, A, L, capital C, H, E, M, I, C, A, L, capital C, H, E, M, I, C, A, L, capital C, H, E, M, I, C. Reactions. 397 Amines. Amine salts on treatment with a base like NaO regenerate the parent amine. Amine salts are soluble in water but insoluble in organic solvents like ether. This reaction is the basis for the separation of amines from the non-basic organic compounds insoluble in water. The reaction of amines with mineral acids to form ammonium salts shows that these are basic in nature. Amines have an unshared pair of electrons on nitrogen atom due to which they behave as Lewis base. Basic character of amines can be better understood in terms of their Kb and pKb values as explained below. K322RORHNHNHO2 or HOK320HNHHRRN or BK321HNHHRR pKb log Kb. Larger the value of Kb or smaller the value of pKb, stronger is the base. The pKb values of few amines are given in table 13.3. pKb value of ammonia is 4.75. Aliphatic amines are stronger bases than ammonia due to I effect of alkyl groups leading to high electron density on the nitrogen atom. Their pKb values lie in the range of 3 to 4.22. On the other hand, aromatic amines are weaker bases than ammonia due to the electron withdrawing nature of the aryl group. Name of amine pKb methanamine 3.38 N-methylmethanamine 3.27 N, N-dimethylmethanamine 4.22 ethanamine 3.29 N ethylethanamine 3.00 N. N-ethylethanamine 3.25 benzenamine 9.38 phenylmethanamine 4.70 N methylaniline 9.30 N, N-dimethylanilin 8.92 Table 13.3, pKb values of amines in aqueous phase. 398 Chemistry. You may find some discrepancies while trying to interpret the Kb values of amines on the basis of I or I effect of the substituents present in amines. Besides inductive effect, there are other effects like solvation effect, steric hindrance, etc., which affect the basic strength of amines. Just ponder over. You may get the answer in the following paragraphs. Structure. Basicity. Relationship of amines. Basicity of amines is related to their structure. Basic character of an amine depends upon the ease of formation of the cation by accepting a proton from the acid. The more stable the cation is relative to the amine, more basic is the amine. Alkanamines versus ammonia. Let us consider the reaction of an alkanamine and ammonia with a proton to compare their basicity. Due to the electron-releasing nature of alkyl group, it pushes electrons towards nitrogen and thus makes the unshared electron pair more available for sharing with the proton of the acid. Moreover, the substituted ammonium ion formed from the amine gets stabilized due to dispersal of the positive charge by the I effect of the alkyl group. Hence, alkylamines are stronger bases than ammonia. Thus, the basic nature of aliphatic amines should increase with increase in the number of alkyl groups. This trend is followed in the gaseous phase. The order of basicity of amines in the gaseous phase follows the expected order: tertiary amine, secondary amine, primary amine, NH3. The trend is not regular in the aqueous state as evident by their pKb values given in table 13.3. In the aqueous phase, the substituted ammonium cations get stabilized not only by electron-releasing effect of the alkyl group I but also by solvation with water molecules. The greater the size of the ion, lesser will be the solvation and the less stabilized is the ion. The order of stability of ions are as follows: decreasing order of extent of H bonding in water and order of stability of ions by solvation. 399 Amines. Greater is the stability of the substituted ammonium cation, stronger should be the corresponding amine as a base. Thus, the order of basicity of aliphatic amines should be primary, secondary, tertiary, which is opposite to the inductive effect-based order. Secondly, when the alkyl group is small, like CH3 group, there is no steric hindrance to H bonding. In case the alkyl group is bigger than CH3 group, there will be steric hindrance to H bonding. Therefore, the change of nature of the alkyl group, e.g., from CH3 to C2H5 results in change of the order of basic strength. Thus, there is a subtle interplay of the inductive effect, solvation effect and steric hindrance of the alkyl group which decides the basic strength of alkylamines in the aqueous state. The order of basic strength in case of methyl substituted amines and ethyl substituted amines in aqueous solution is as follows: C2H52NH, C2H53N, C2H5NH2, NH3CH32NH, CH3NH2, CH33N, NH3Biomolecules versus ammonia pKb value of aniline is quite high. Why is it so? It is because in aniline or other arylamines, the NH2 group is attached directly to the benzene ring. It results in the unshared electron pair on nitrogen atom to be in conjugation with the benzene ring and thus making it less available for protonation. If you write different resonating structures of aniline, you will find that aniline is a resonance hybrid of the following 5 structures. On the other hand, an alinium ion obtained by accepting a proton can have only 2 resonating structures cacyl. We know that greater the number of resonating structures, greater is the stability, thus you can infer that aniline 5 resonating structures is more stable than an alinium ion. Hence, the proton acceptability or the basic nature of aniline or other aromatic amines would be less than that of ammonia. In case of substituted aniline, it is observed that electron-releasing groups like OC3, CH3 increase basic strength whereas electron-withdrawing groups like number 2, SO3H, Cu, X decrease it. 2. Alkylation amines undergo alkylation on reaction with alkyl halides. Refer Unit 10, Class 12. 3. Acylation aliphatic and aromatic primary and secondary amines react with acid chlorides, anhydrides and esters by nucleophilic substitution reaction. This reaction is known as acylation. You can consider this reaction as the replacement of hydrogen atom of NH2 or NH group by the acyl group. The products obtained by acylation reaction are known as amides. The reaction is carried out in the presence of a base stronger than the amine, like pyridine, which removes HCl so formed and shifts the equilibrium to the right-hand side. Amines also react with benzoyl chloride C6H5 cocyl. This reaction is known as benzoylation 3,6,5,6,52,3-methanamine benzoyl chloride N-methylbenzamide NHC coc CHCHCHHL and HLCCO. What do you think is the product of the reaction of amines with carboxylic acids? They form salts with amines at room temperature. Arrange the following in decreasing order of their basic strength: C6H5NH2, C2H5NH2, C2H52NH. NH3. The decreasing order of basic strength of the above amines and ammonia follows the following order: C2H52NH, C2H5NH2, NH3, C6H5NH2. Example 13.4 Example 13.4 Example 13.4 Example 13.4 Example 13.4 Solution: capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I. 401 amines SOOCLHNCH25SOONCH25HClN, N-dethylbenzene sulfonamide CH25CH254. Carbolamine reaction aliphatic and aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide form isocyanides or carbolamines which are foul-smelling substances. Secondary and tertiary amines do not show this reaction. This reaction is known as carbolamine reaction or isocyanide test and is used as a test for primary amines. 5. Reaction with nitrous acid. 3 classes of amines react differently with nitrous acid which is prepared in situ from a mineral acid and sodium nitrite. A primary aliphatic amines react with nitrous acid to form aliphatic diazonium salts which being unstable, liberate nitrogen gas quantitatively and alcohols. Quantitative evolution of nitrogen is used in estimation of amino acids and proteins. B. Aromatic amines react with nitrous acid at low temperatures 273–278 K to form diazonium salts. A very important class of compounds used for synthesis of a variety of aromatic compounds discussed in section 13.7. Secondary and tertiary amines react with nitrous acid in a different manner. 6. Reaction with aryl sulfonyl chloride benzene sulfonyl chloride C6H5SO2Cl, which is also known as Hensberg's reagent, reacts with primary and secondary amines to form sulfonamides. The reaction of benzene sulfonyl chloride with primary amine yields N-ethylbenzene sulfonylamide. The hydrogen attached to nitrogen in sulfonamide is strongly acidic due to the presence of strong electron-withdrawing sulfonyl group. Hence, it is soluble in alkali B. In the reaction with secondary amine, N, and diethylbenzenesulfonamide is formed. 402 Chemistry. Since N-dethylbenzene sulfonamide does not contain any hydrogen atom attached to nitrogen atom, it is not acidic and hence insoluble in alkali. C. Tertiary amines do not react with benzenesulfonyl chloride. This property of amines reacting with benzenesulfonyl chloride in a different manner is used for the distinction of primary, secondary and tertiary amines and also for the separation of a mixture of amines. However, these days benzenesulfonyl chloride is replaced by pedalenesulfonyl chloride. 7. Electrophilic substitution. You have read earlier that aniline is a resonance hybrid of 5 structures. Where do you find the maximum electron density in these structures? Ortho and pod oppositions to the NH2 group become centers of high electron density. Thus NH2 group is ortho and pod, a directing and a powerful activating group. Of bromination, aniline reacts with bromine water at room temperature to give a white precipitate of 2,4,6-tribromonoline. The main problem encountered during electrophilic substitution reactions of aromatic amines is that of their very high reactivity. Substitution tends to occur at ortho and pod oppositions, if we have to prepare monosubstituted aniline derivative. How can the activating effect of NH2 group be controlled? This can be done by protecting the NH2 group by acetylation with acetic anhydride. Then carrying out the desired substitution followed by hydrolysis of the substituted amide to the substituted amine. The lone pair of electrons on nitrogen of acetanilide interacts with oxygen atom due to resonance as shown below. Hence, the lone pair of electrons on nitrogen is less available for donation to benzene ring by resonance. Therefore, activating effect of NHCOCH3 group is less than that of amino group B. Nitration. Direct nitration of aniline yields trioxidation products in addition to the nitro derivatives. Moreover, in the strongly acidic medium, aniline is protonated to form the anilinium ion, which is metadirecting. That is why besides the ortho and pod derivatives, significant amount of metaderivative is also formed. However, by protecting the NH2 group by acetylation reaction with acetic anhydride, the nitration reaction can be controlled and the p-nitro derivative can be obtained as the major product. C. Sulfonation. Aniline reacts with concentrated sulfuric acid to form an aluminium hydrogen sulfate, which on heating with sulfuric acid at 453-473 K produces p-aminobenzene sulfonic acid, commonly known as sulfonylic acid, as the major product. Aniline does not undergo Friedel-Crafts reaction alkylation and acetylation due to salt formation with aluminium chloride, the Lewis acid, which is used as a catalyst. Due to this, nitrogen of aniline acquires positive charge and hence acts as a strong deactivating group for further reaction. 404 Chemistry 2. Diazonium salts. The diazonium salts have the general formula 2RNX, where R stands for an aryl group and X ion may be ClBr, 4HSO, 4BF, etc. They are named by suffixing diazonium to the name of the parent hydrocarbon from which they are formed, followed by the name of anion such as chloride, hydrogen sulfate, etc. The 2N group is called diazonium group. For example, 26,5-CHNCl is named as benzene-diazonium chloride and C6H5N2HSO4 is known as benzene-diazonium hydrogen sulfate. Primary aliphatic amines form highly unstable alkyl diazonium salts referred to section 13.6. Primary aromatic amines form uranidiazonium salts which are stable for a short time in solution at low temperatures 273-278 K. The stability of the uranidiazonium ion is explained on the basis of resonance. Benzene-diazonium chloride is prepared by the reaction of aniline with nitrous acid at 273-278 K. Nitrous acid is produced in the reaction mixture by the reaction of sodium nitrite with hydrochloric acid. The conversion of primary aromatic amines into diazonium salts is known as diazonization. Due to its instability, the diazonium salt is not generally stored and is used immediately after its preparation. 273-278 K652652CH902HCHNACLCLCLHN2HNO in text questions 13.4 Arrange the following in increasing order of their basic strength. IC2H5NH2, C6H5NH2, NH3, C6H5CH2NH2 and C2H52NH2 C2H5NH2, C2H52NH, C2H53N, C6H5NH2 3CH3NH2, CH32NH, CH33N, C6H5NH2, C6H5CH2NH2. 13.5 Complete the following acid-base reactions and name the products. ICH3CH2CH2NH2HCl2C2H53NHCl 13.6 Right reactions of the final alkylation product of aniline with excess of methyl iodide in the presence of sodium carbonate solution. 13.7 Write chemical reaction of aniline with benzoyl chloride and write the name of the product obtained. 13.8 Write structures of different isomers corresponding to the molecular formula, C3H9N. Write IUPAC names of the isomers which will liberate nitrogen gas on treatment with nitrous acid. 13.713, 713, 713, 713, 7. Method of capital P R E P A R A T I O N capital P R E P A R A T I O N capital P R E P A R A T. Preparation of diazonium salts. 405 Amines benzene-diazonium chloride is a colorless crystalline solid. It is readily soluble in water and is stable in cold but reacts with water when warmed. It decomposes easily in the dry state. Benzene-diazonium fluoroborate is water insoluble and stable at room temperature. The reactions of diazonium salts can be broadly divided into two categories, namely A reactions involving displacement of nitrogen and B reactions involving retention of diazo group. A reactions involving displacement of nitrogen diazonium group being a very good leaving group, is substituted by other groups such as Cl, Bri, Cn, and O, which displace nitrogen from the aromatic ring. The nitrogen formed escapes from the reaction mixture as a gas 1, replacement by halide or cyanide ion. The Cl, Br and Cn nucleophiles can easily be introduced in the benzene ring in the presence of Cu ion. This reaction is called Sandmeyer reaction. Alternatively, chlorine or bromine can also be introduced in the benzene ring by treating the diazonium salt solution with corresponding halogen acid in the presence of copper powder. This is referred as Gattermann reaction. The yield in Sandmeyer reaction is found to be better than Gattermann reaction. 2. Replacement by iodide ion. Iodine is not easily introduced into the benzene ring directly, but, when the diazonium salt solution is treated with potassium iodide, iodobenzene is formed. 3. Replacement by fluoride ion. When arene-diazonium chloride is treated with fluoroboric acid, arene diazonium fluoroborate is precipitated which on heating decomposes to yield aryl fluoride. 4. Replacement by H. Certain mild reducing agents like hypophosphorus acid, phosphinic acid or ethanol reduce diazonium salts to arenes and themselves get oxidized to phosphorus acid and ethanol, respectively. 13.813, 813, 813, 813, 8. Capital P H Y S I C A L capital P H Y S I C A L capital P H Y S I C A L capital P H Y S I C. Properties 13.913, 913, 913, 913, 9. Chemical reactions 2222. 406 Chemistry 5. Replacement by hydroxyl group. If the temperature of the diazonium salt solution is allowed to rise up to 283 K, the salt gets hydrolyzed to phenol. 6. Replacement by number 2 group. When diazonium fluoroborate is heated with aqueous sodium nitrite solution in the presence of copper, the diazonium group is replaced by number 2 group. B reactions involving retention of diazo group coupling reactions. The azo products obtained have an extended conjugate system having both the aromatic rings joined through the NN bond. These compounds are often colored and are used as dyes. Benzene diazonium chloride reacts with phenol in which the phenol molecule at its pod opposition is coupled with the diazonium salt to form p-hydroxyiazobenzene. This type of reaction is known as coupling reaction. Similarly, the reaction of diazonium salt with aniline yields p-aminozobenzene. This is an example of electrophilic substitution reaction. From the above reactions, it is clear that the diazonium salts are very good intermediates for the introduction of F, Cl, Br, I, Cn, O, number 2 groups into the aromatic ring. Aryl fluorides and iodides cannot be prepared by direct halogenation. The cyano group cannot be introduced by nucleophilic substitution of chlorine and chlorobenzene, but cyanobenzene can be easily obtained from diazonium salt. Thus, the replacement of diazo group by other groups is helpful in 13.1013, 1013, 1013, 1013,
10. Importance. Capital I M P O R T A N C E. Capital I M P O R T A N C E. Capital I M P O R T A N C E. Off of diazonium salts and synthesis. Synthesis of aromatic compounds. 407 Amines preparing those substituted aromatic compounds which cannot be prepared by direct substitution in benzene or substituted benzene. 13.9 Convert I3-methylaniline into 3-nitrotoluene 2-aniline into 1,3,5-tribromobenzyne. In text question, how will you convert 4-nitrotoluene to 2-bromobenzoic acid? Example 13.5 Example 13.5 Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. Amines can be considered as derivatives of ammonia obtained by replacement of hydrogen atoms with alkyl or aryl groups. Replacement of one hydrogen atom of ammonia gives rise to structure of the type RNH2, known as primary amine. Secondary amines are characterized by the structure R2NH or RNHR and tertiary amines by R3N, RNRR or R2NR. Secondary and tertiary amines are known as simple amines if the alkyl or aryl groups are the same and mixed amines if the groups are different. Like ammonia, all the three types of amines have one unshared electron pair on nitrogen atom due to which they behave as Lewis bases. Amines are usually formed from nitro compounds, halides, amides, imides, etc. They exhibit hydrogen bonding which influence their physical properties. In alkylamines, a combination of electron-releasing, steric and H-bonding factors influence the stability of the substituted ammonium cations in product polar solvents and thus affect the basic nature of amines. Alkyl amines are found to be stronger bases than ammonia. In aromatic amines, electron-releasing and withdrawing groups, respectively increase and decrease their basic character. Aniline is a weaker base. Summary. 408 Chemistry than ammonia. Reactions of amines are governed by availability of the unshared pair of electrons on nitrogen. Influence of the number of hydrogen atoms at nitrogen atom on the type of reactions and nature of products is responsible for identification and distinction between primary, secondary and tertiary amines. Pedalene sulfonyl chloride is used for the identification of primary, secondary and tertiary amines. Presence of amino group in aromatic ring enhances reactivity of the aromatic amines. Reactivity of aromatic amines can be controlled by acylation process, that is, by treating with acetyl chloride or acetic anhydride. Tertiary amines like trimethylamine are used as insect attractants. Aryl diazonium salts, usually obtained from arylamines, undergo replacement of the diazonium group with a variety of nucleophiles to provide advantageous methods for producing aryl halides. Cyanides, phenols and arenes by reductive removal of the diazo group. Coupling reaction of aryl diazonium salts with phenols or arylamines give rise to the formation of azodies. 13.1 Write IUPAC names of the following compounds and classify them into primary, secondary and tertiary amines. ICH3 2CH&H2 2CH3CH3CH3CH3CH3CH2CH3CH3CH4NH2 13.2 Give one chemical test to distinguish between the following pairs of compounds. Imethylamine and dimethylamine. 2 Secondary and tertiary amines. 3 Ethylamine and aniline. Aniline and benzylamine. V-aniline and N-methylaniline. 13.3 Account for the following. IPKB of aniline is more than that of methylamine. 2 Ethylamine is soluble in water whereas aniline is not. 3 Methylamine in water reacts with ferric chloride to precipitate hydrated ferric oxide IV. Although amino group is O and P directing in aromatic electrophilic substitution reactions, aniline on nitration gives a substantial amount of M-nitroaniline. V-aniline does not undergo Friedel-Crafts reaction. V-diazonium salts of aromatic amines are more stable than those of aliphatic amines. 7 Gabriel phthalimide synthesis is preferred for synthesizing primary amines. 13.4 Arrange the following, I in decreasing order of the pKb values, C2H5NH2, C6H5NHCH3, C2H52NH and C6H5NH22 in increasing order of basic strength, C6H5NH2, C6H5NCH32.
C2H52NH and CH3NH23 in increasing order of basic strength, A-aniline, P-nitroaniline and P-toluidine exercises. BC6H5NH2, C6H5NHCH3, C6H5CH2NH2 in decreasing order of basic strength in gas phase, C2H5NH2, C2H52NH, C2H53N and NH3V in increasing order of boiling point, C2H50, CH32NH, C2H5NH2V in increasing order of solubility in water, C6H5NH2, C2H52NH, C2H5NH2. 13.5 How will you convert I-ethanoic acid into methanamine 2-hexanenitrile into 1-aminopentane 3-methanol to ethanoic acid I-vithanamine into methanamine V-ethanoic acid into propanoic acid V-methanamine into ethanamine 7-nitromethane into dimethylamine 8, propanoic acid into ethanoic acid 13.6 Describe a method for the identification of primary, secondary and tertiary amines. Also write chemical equations of the reactions involved. 13.7 Write short notes on the following: I-carbolamine reaction 2-diazotization 3 Hoffman's bromamide reaction IV coupling reaction V ammonolysis V acetylation 7 Gabriel phthalimide synthesis. 13.8 Accomplish the following conversions: I-nitrobenzene to benzoic acid 2 benzene to ambromophenols 3 benzoic acid 2 aniline IV aniline to 2. 4. 6-tetrabromophluorobenzene V benzyl chloride to 2-phenylethanamine V chlorobenzene to p-chloroniline 7 aniline to p-bromoniline 8 benzamide to toluene 9 aniline to benzyl alcohol. 13.9 Give the structures of A, B and C in the following reactions: I2-NaOBr-NaCNO3 partial hydrolysis CH652NHHOHC-652CHNCLABC342LEALHHNOKCN320CCHBrABC degrees IV22 nano-HClHOHFEHCl 652-273 kCH no ABCV32NH nano HCl naober 3CH Clu ABCV 652 CHOHHNOFHCl 652-273 kCH no ABC. 410 Chemistry 13.10 An aromatic compound A on treatment with aqueous ammonia and heating forms compound B, which on heating with Br2 and Co forms a compound C of molecular formula C6H7N. Write the structures and IUPAC names of compounds A, B and C. 13.11 Complete the following reactions: I652-3CHNHCHClALCCO2-652-322-CHNCLHPOHO36522-4CHNHH SOCONC 652-2-5CHNCl-CHOV652-2-CHNHBRAC V3652-2-CHCOCHNHO742 V652 2-CHNCl 13.12 Why cannot aromatic primary amines be prepared by Gabriel phthalimide synthesis 13.13 Write the reactions of I-aromatic and 2-aliphatic primary amines with nitrous acid. 13.14 Give plausible explanation for each of the following: Why are amines less acidic than alcohols of comparable molecular masses? 2. Why do primary amines have higher boiling point than tertiary amines? 3. Why are aliphatic amines stronger bases than aromatic amines? Answers to some in-text questions. 13.4 IC6H5NH2, NH3, C6H5CH2NH2, C2H5NH2, C2H52NH2 C6H5NH2, C2H5NH2, C2H53N, C2H52NH3 C6H5NH2, C6H5CH2NH2, CH33N, CH3NH2, CH32NH. A living system grows, sustains and reproduces itself. The most amazing thing about a living system is that it is composed of non-living atoms and molecules. The pursuit of knowledge of what goes on chemically within a living system falls in the domain of biochemistry. Living systems are made up of various complex biomolecules like carbohydrates, proteins, nucleic acids, lipids, etc. Proteins and carbohydrates are essential constituents of our food. These biomolecules interact with each other and constitute the molecular logic of life processes. In addition, some simple molecules like vitamins and mineral salts also play an important role in the functions of organisms. Structures and functions of some of these biomolecules are discussed in this unit. Capital B, I, O, M, O, L, E, C, U, L, E, S. Capital B, I, O, M, O, L, E, C, U, L, E, S. Capital B, I, O, M, O, L. After studying this unit, you will be able to explain the characteristics of biomolecules like carbohydrates, proteins and nucleic acids and hormones, classify carbohydrates
proteins, nucleic acids and vitamins on the basis of their structures, explain the difference between DNA and RNA, describe the role of biomolecules in biosystem. Objectives: it is the harmonious and synchronous progress of chemical reactions in body which leads to life. 14 Unit 14 Carbohydrates are primarily produced by plants and form a very large group of naturally occurring organic compounds. Some common examples of carbohydrates are cane sugar, glucose, starch, etc. Most of them have a general formula, CxH2OY, and were considered as hydrates of carbon from where the name carbohydrate was derived. For example, the molecular formula of glucose C6H12O6 fits into this general formula, C6H2O6. But all the compounds which fit into this formula may not be classified as carbohydrates. For example, acetic acid CH3CoO fits into this general formula, C2H2O2, but is not a carbohydrate. Similarly, rhamnose, C6H12O5 is a carbohydrate but does not fit in this definition. A large number of their reactions have shown that they contain specific functional groups. Chemically, the carbohydrates may be defined as optically active polyhydroxyaldehydes or ketones are the compounds which produce such units on hydrolysis. Some of the carbohydrates, which are sweet in taste, are also called sugars. The most common sugar used in our homes is named as sucrose, whereas the sugar present 14.114, 114, 1, 14, 114, 1, capital C, A, R, B, O, H, Y, D, R, A, T, E, S, capital C, A, R, B, O, H, Y, D, R, A, T, E, S, capital C, A, R, B. 412 Chemistry and milk is known as lactose. Carbohydrates are also called saccharides. Greek, saccharin means sugar. Carbohydrates are classified on the basis of their behavior on hydrolysis. They have been broadly divided into following three groups. Monosaccharides, a carbohydrate that cannot be hydrolyzed further to give simpler unit of polyhydroxyaldehyde or ketone is called a monosaccharide. About 20 monosaccharides are known to occur in nature. Some common examples are glucose, fructose, ribose, etc. 2 oligosaccharides, carbohydrates that yield 2 to 10 monosaccharide units, on hydrolysis, are called oligosaccharides. They are further classified as disaccharides, trisaccharides, tetrasaccharides, etc., depending upon the number of monosaccharides they provide on hydrolysis. Amongst these the most common are disaccharides. The 2 monosaccharide units obtained on hydrolysis of a disaccharide may be same or different. For example, 1 molecule of sucrose on hydrolysis gives 1 molecule of glucose and 1 molecule of fructose, whereas maltose gives 2 molecules of only glucose. 3 polysaccharides, carbohydrates which yield a large number of monosaccharide units on hydrolysis are called polysaccharides. Some common examples are starch, cellulose, glycogen, gums, etc. Polysaccharides are not sweet in taste, hence they are also called non-sugars. The carbohydrates may also be classified as either reducing or non-reducing sugars. All those carbohydrates which reduce failing solution and Tollens reagent are referred to as reducing sugars. All monosaccharides, whether aldose or ketose, are reducing sugars. Monosaccharides are further classified on the basis of number of carbon atoms and the functional group present in them. If a monosaccharide contains an aldehyde group, it is known as an aldose, and if it contains a keto group, it is known as a ketose. Number of carbon atoms constituting the monosaccharide is also introduced in the name, as is evident from the examples given in table 14.114. 1 classification of carbohydrates 1 2 monosaccharides 3 triose aldotriose cototriose 4 tetros aldotetrose cototetrose 5 pentose aldopentose cotopentose 6 hexose aldohexose ketohexose 7 heptose aldoheptose cotoheptose. Carbon atoms general term aldehyde ketone table 14.1. Different types of monosaccharides. Glucose occurs freely in nature as well as in the combined form. It is present in sweet fruits and honey. Ripe grapes also contain glucose in large amounts. It is prepared as follows. 1. From sucrose cane sugar. If sucrose is boiled with dilute HCl or H2SO4 in alcoholic solution, glucose and fructose are obtained in equal amounts. Preparation of glucose 1 2 1 glucose. 413 Biomolecules H12 22 11 2 6 12 6 6 12 6 CHO sucrose glucose fructose 2. From starch. Commercially, glucose is obtained by hydrolysis of starch by boiling it with dilute H2SO4 at 393 K under pressure. H610 5N2612 6393 K, 23 ATM CHO starch or cellulose glucose. Glucose is an aldohexose and is also known as dextrose. It is the monomer of many of the larger carbohydrates.
namely starch, cellulose. It is probably the most abundant organic compound on Earth. It was assigned the structure given below on the basis of the following evidences. 1. Its molecular formula was found to be C6H12O6. 2. On prolonged heating with high, it forms N-hexane, suggesting that all the 6 carbon atoms are linked in a straight chain. 3. Glucose reacts with hydroxylamine to form an oxime and adds a molecule of hydrogen cyanide to give cyanohydrin. These reactions confirm the presence of a carbonyl group, CO in glucose 4. Glucose gets oxidized to 6-carbon carboxylic acid gluconic acid on reaction with a mild oxidizing agent like bromine water. This indicates that the carbonyl group is present as an aldehydic group, CHOCH4OCH4OCH2OCH2OBr water 2-gluconic acid 5. Acetylation of glucose with acetic anhydride gives glucose pentacetate, which confirms the presence of 5 O groups. Since it exists as a stable compound, 5 O groups should be attached to different carbon atoms. Structure of glucose CHOCH4OCH2O glucose. 414 Chemistry 6. On oxidation with nitric acid, glucose as well as gluconic acid both yield a dicarboxylic acid, saccharic acid. This indicates the presence of a primary alcoholic O group in glucose. CHOCH4OCHO2 oxidation CH4OCHO2 CH4O cuckoo oxidation saccharic acid gluconic acid. The exact spatial arrangement of different O groups was given by Fischer after studying many other properties. Its configuration is correctly represented as isogluconic acid is represented as 2 and saccharic acid as 3. CHOHOHHOHCH2O-IQ-HOOHCH2O-2-CHOOH-CH2O-2-CHOOH-CHOOH-3 glucose is correctly named as D-glucose. D before the name of glucose represents the configuration, whereas represents dextrorotatory nature of the molecule. It should be remembered that D and L have no relation with the optical activity of the compound. They are also not related to letter D and L. See Unit 10. The meaning of D and L notations is as follows. The letters D or L before the name of any compound indicate the relative configuration of a particular stereoisomer of a compound with respect to configuration of some other compound, configuration of which is known. In the case of carbohydrates, this refers to their relation with a particular isomer of glyceraldehyde. Glyceraldehyde contains one asymmetric carbon atom and exists in 2 enantiomeric forms as shown below. Isomer of glyceraldehyde has D configuration. It means that when its structural formula is written on paper following specific conventions which you will study in higher classes, the O group lies on right-hand side in the structure. All those compounds which can be chemically correlated to D isomer of glyceraldehyde are said to have D configuration, whereas those which can be correlated to L isomer of glyceraldehyde are said to have L configuration. In L isomer O group is on left-hand side as you can see in the structure. For assigning 415 biomolecules the configuration of monosaccharides, it is the lowest asymmetric carbon atom as shown below, which is compared. As in glucose, O on the lowest asymmetric carbon is on the right side, which is comparable to glyceraldehyde, so glucose is assigned D configuration. Other asymmetric carbon atoms of glucose are not considered for this comparison. Also, the structure of glucose and glyceraldehyde is written in a way that most oxidized carbon, in this case CHO, is at the top. CHOHOOHHOHOCH2OD glucose CHOCH2OHOD glyceraldehyde. The structure I of glucose explained most of its properties, but the following reactions and facts could not be explained by this structure. 1. Despite having the aldehyde group, glucose does not give Schiff's test and it does not form the hydrogen sulfite addition product with NaSO3. 2. The pentacetate of glucose does not react with hydroxylamine, indicating the absence of free CHO group. 3. Glucose is found to exist in 2 different crystalline forms which are named as Greek letter alpha and Greek letter beta. The Greek letter alpha form of glucose MP 419 K is obtained by crystallization from concentrated solution of glucose at 303 K, while the Greek letter beta form MP 423 K is obtained by crystallization from hot and saturated aqueous solution at 371 K. This behavior could not be explained by the open chain structure I for glucose. It was proposed that one of the O groups may add to the CHO group and form a cyclic hemiacetal structure. It was found that glucose forms a 6-membered ring in which O at C5 is involved in ring formation. This explains the absence of CHO group and also existence of glucose in 2 forms as shown below. These 2 cyclic forms exist in equilibrium with open chain structure. The 2 cyclic hemiacetal forms of glucose differ only in the configuration of the hydroxyl group at C1, called anomeric carbon cyclic structure of glucose. 416 Chemistry. The aldehyde carbon before cyclization, such isomers, that is, Greek letter alpha form and Greek letter beta form, are called anomers. The six-membered cyclic structure of glucose is called pyranose structure, Greek letter alpha or Greek letter beta, in analogy with pyran. Pyran is a cyclic organic compound with one oxygen atom and 5 carbon atoms in the ring. The cyclic structure of glucose is more correctly represented by Haworth structure as given below. Fructose is an important ketohexose. It is obtained along with glucose by the hydrolysis of disaccharide, sucrose. It is a natural monosaccharide found in fruits, honey and vegetables. In its pure form it is used as a sweetener. It is also an important ketohexose. Fructose also has the molecular formula C6H12O6 and on the basis of its reactions it was found to contain a ketonic functional group at carbon number 2 and 6 carbons in straight chain as in the case of glucose. It belongs to D series and is a levorotatory compound. It is appropriately written as D-fructose. Its open chain structure is as shown. It also exists in 2 cyclic forms which are obtained by the addition of O at C5 to the group. The ring, thus formed, is a 5-membered ring and is named as furanose with analogy to the compound furan. Furan is a 5-membered cyclic compound with 1 oxygen and 4 carbon atoms. Structure of fructose. The cyclic structures of 2 anomers of fructose are represented by Haworth structures as given. 1,4, 1, 2, 2 fructose. 417 biomolecules. You have already read that disaccharides on hydrolysis with dilute acids or enzymes yield 2 molecules of either the same or different monosaccharides. The 2 monosaccharides are joined together by an oxide linkage formed by the loss of a water molecule. Such a linkage between 2 monosaccharide units through oxygen atom is called glycosidic linkage. In disaccharides, if the reducing groups of monosaccharides, that is, aldehydic or ketonic groups, are bonded, these are non-reducing sugars, e.g., sucrose. On the other hand, sugars in which these functional groups are free, are called reducing sugars, for example, maltose and lactose. Isucrose, one of the common disaccharides, is sucrose, which on hydrolysis gives equimolar mixture of D-glucose and D-fructose. 1,4, 1, 3 disaccharides. These 2 monosaccharides are held together by a glycosidic linkage between C1 of Greek letter alpha D-glucose and C2 of Greek letter beta D-fructose. Since the reducing groups of glucose and fructose are involved in glycosidic bond formation, sucrose is a non-reducing sugar. Sucrose is dextrorotatory, but after hydrolysis gives dextrorotatory glucose and levorotatory fructose. Since the levorotation of fructose minus 92.4 degrees is more than dextrorotation of glucose 52.5 degrees, the mixture is levorotatory. Thus, hydrolysis of sucrose brings about a change in the sign of rotation, from dextro to levo, and the product is named as invert sugar. 2 maltose, another disaccharide. Maltose is composed of 2 Greek letter alpha D-glucose units in which C1 of one glucose I is linked to C4 of another glucose unit 2. The free aldehyde group can be produced at C1 of second glucose in solution and it shows reducing properties, so it is a reducing sugar. 418 Chemistry. 3 lactose. It is more commonly known as milk sugar since this disaccharide is found in milk. It is composed of Greek letter beta D-galactose and Greek letter beta D-glucose. The linkage is between C1 of galactose and C4 of glucose. Free aldehyde group may be produced at C1 of glucose unit, hence it is also a reducing sugar. Polysaccharides contain a large number of monosaccharide units joined together by glycosidic linkages. These are the most commonly encountered carbohydrates in nature. They mainly act as the food storage or structural materials. Starch. Starch is the main storage polysaccharide of plants. It is the most important dietary source for human beings. High content of starch is found in cereals, roots, tubers and some vegetables. It is a polymer of Greek letter alpha glucose and consists of 2 components, amylose and amylopectin. Amylose is water-soluble component which constitutes about 15-20 of starch. Chemically, amylose is a long unbranched chain with 2,0,0,10,0,0 Greek letter alpha D-glucose units held together by C1-C4 glycosidic linkage. Amylopectin is insoluble in water and constitutes about 80-85 of starch. It is a branched chain polymer of Greek letter alpha D-glucose units in which chain is formed by C1, C4 glycosidic linkage, whereas branching occurs by C1, C6 glycosidic linkage. 1,4, 1, 4 polysaccharides. 419 biomolecules. 2 cellulose. Cellulose occurs exclusively in plants and it is the most abundant organic substance in plant kingdom. It is a predominant constituent of cell wall of plant cells. Cellulose is a straight-chain polysaccharide composed only of Greek letter beta D-glucose units which are joined by glycosidic linkage between C1 of one glucose unit and C4 of the next glucose unit. 3 glycogen. The carbohydrates are stored in animal body as glycogen. It is also known as animal starch because its structure is similar to amylopectin and is rather more highly branched. It is present in liver, muscles and brain. When the body needs glucose, enzymes break the glycogen down to glucose. Glycogen is also found in yeast and fungi. Carbohydrates are essential for life in both plants and animals. They form a major portion of our food. Honey has been used for a long time as an instant source of energy by Veds in Ayurvedic system of medicine. Carbohydrates are used as storage molecules as starch in plants and glycogen in animals. Cell wall of bacteria and plants is made up of cellulose. We build furniture, etc. from cellulose in the form 1,4,1,5 Importance of carbohydrates. 420 Chemistry of wood and clothe ourselves with cellulose in the form of cotton fiber. They provide raw materials for many important industries like textiles, paper, lacquers and breweries. 2 aldopentoses bis D-ribose and 2-deoxy-D-ribose section 1,4,5,1, class 12 are present in nucleic acids. Carbohydrates are found in biosystem in combination with many proteins and lipids. 14.1 Glucose or sucrose are soluble in water, but cyclohexane or benzene simple 6-membered ring compounds are insoluble in water. Explain 14.2 What are the expected products of hydrolysis of lactose? 14.3 How do you explain the absence of aldehyde group in the pentacetate of D-glucose? In text questions. Proteins are the most abundant biomolecules of the living system. Chief sources of proteins are milk, cheese, pulses, peanuts, fish, meat, etc. They occur in every part of the body and form the fundamental basis of structure and functions of life. They are also required for growth and maintenance of body. The word protein is derived from Greek word, proteus, which means primary or of prime importance. All proteins are polymers of Greek letter alpha amino acids. Amino acids contain amino NH2 and carboxyl CoO functional groups. Depending upon the relative position of amino group with respect to carboxyl group, the amino acids can be classified as Greek letter alpha, Greek letter beta, Greek letter gamma, Greek letter delta and so on. Only Greek letter alpha amino acids are obtained on hydrolysis of proteins. They may contain other functional groups also. All Greek letter alpha amino acids have trivial names, which usually reflect the property of the compound or its source. Glycine is so named since it has sweet taste in Greek. Glykos means sweet and tyrosine was first obtained from cheese in Greek. Tyros means cheese. Amino acids are generally represented by a 3-letter symbol. Sometimes 1-letter symbol is also used. Structures of some commonly occurring amino acids along with their 3-letter and 1-letter symbols are given in Table 14.2. 1. Glycine H-Gly-G2, alanine, CH3-ALA-A3, valine H3C2CH val V4, leucine H3C2CH-CH2 LUL. Name of the characteristic feature 3-letter 1-letter amino acids of side chain. R symbol code Table 14.2, natural amino acids 1,4,2, 1 amino acids are CH-CoONH2 amino acid R side chain CoH2NH R14.214, 214, 2, 14, 214, 2. Proteins, capital P, R, O, T, E, I, N, S, capital P, R, O, T, E, I, N, S, capital P, R, O, T, E, I, N, S, capital P, R, O, T, E, I. 421 Biomolecules 5, isoleucine H3CCH2CHELICH36, arginine HNCNHCH23 ArgRNH27. Lysine H2NCH24 Lys K8, glutamic acid hook CH2CH2 Glue9, aspartic acid hook CH2 AspDO10. Glutamine H2NCCH2CH2 GLNQO11, asparagine H2NCCH2 ASNN12, threonine H3C-THRT13. Serine HOCH2 SET-S14, cysteine HSCH2 Cy-C15, methionine H3CSCH2 MET-M16, phenylalanine C6H5CH2 FF17. Tyrosine PHOC6H4CH2 TERY18, tryptophan CH2NHTRPW19, histidine is H20. Proline Pro-P essential amino acid. The entire structure amino acids are classified as acidic, basic or neutral depending upon the relative number of amino and carboxyl groups in their molecule. Equal number of amino and carboxyl groups makes it neutral, more number of amino than carboxyl groups makes it basic, and more carboxyl groups as compared to amino groups makes it acidic. The amino acids, which can be synthesized in the body, are known as non-essential amino acids. On the other hand, those which cannot be synthesized in the body and must be obtained through diet, are known as essential amino acids marked with asterisk in Table 14.2. 1.4.2. Classification of amino acids. 422 Chemistry. Amino acids are usually colorless, crystalline solids. These are water-soluble, high-melting solids and behave like salts rather than simple amines or carboxylic acids. This behavior is due to the presence of both acidic carboxyl group and basic amino groups in the same molecule. In aqueous solution, the carboxyl group can lose a proton and amino group can accept a proton, giving rise to a dipolar ion known as Zwitter ion. This is neutral but contains both positive and negative charges. In Zwitter ionic form, amino acids show amphoteric behavior as they react both with acids and bases. Except glycine, all other naturally occurring Greek letter alpha amino acids are optically active, since the Greek letter alpha carbon atom is asymmetric. These exist both in D and L forms. Most naturally occurring amino acids have L configuration. L-aminoacids are represented by writing the NH2 group on left-hand side. You have already read that proteins are the polymers of Greek letter alpha amino acids and they are connected to each other by peptide bond or peptide linkage. Chemically, peptide linkage is an amide formed between Q group and NH2 group. The reaction between two molecules of similar or different amino acids proceeds through the combination of the amino group of one molecule with the carboxyl group of the other. This results in the elimination of a water molecule and formation of a peptide bond CONH. The product of the reaction is called a dipeptide because it is made up of two amino acids. For example, when carboxyl group of glycine combines with the amino group of alanine we get a dipeptide, glycosalanine. If a third amino acid combines to a dipeptide, the product is called a tripeptide. A tripeptide contains three amino acids linked by two peptide linkages. Similarly, when 4, 5 or 6 amino acids are linked, the respective products are known as tetrapeptide, pentapeptide or hexapeptide, respectively. When the number of such amino acids is more than 10, then the products are called polypeptides. A polypeptide with more than 100 amino acid residues, having molecular mass higher than 10,000 U is called a protein. However, the distinction between a polypeptide and a protein is not very sharp. Polypeptides with fewer amino acids are likely to be called proteins if they ordinarily have a well-defined conformation of a protein such as insulin which contains 51 amino acids. Proteins can be classified into two types on the basis of their molecular shape of fibrous proteins. When the polypeptide chains run parallel and are held together by hydrogen and disulfide bonds, then fiber-like structure is formed. Such proteins are generally insoluble in water. Some common examples are keratin present in hair, wool, silk and myosin present in muscles, etc. 1.4.2.3 Structure of proteins. Figure 14.1, Greek letter alpha helix structure of proteins. Figure 14.2, Greek letter beta pleated sheet structure of proteins. B globular proteins. This structure results when the chains of polypeptides coil around to give a spherical shape. These are usually soluble in water. Insulin and albumins are the common examples of globular proteins. Structure and shape of proteins can be studied at 4 different levels, that is, primary, secondary, tertiary and quaternary, each level being more complex than the previous one. Primary structure of proteins. Proteins may have one or more polypeptide chains. Each polypeptide in a protein has amino acids linked with each other in a specific sequence, and it is this sequence of amino acids that is said to be the primary structure of that protein. Any change in this primary structure, that is, the sequence of amino acids, creates a different protein. 2. Secondary structure of proteins. The secondary structure of protein refers to the shape in which a long polypeptide chain can exist. They are found to exist in 2 different types of structures, viz. Greek letter alpha helix and Greek letter beta pleated sheet structure. These structures arise due to the regular folding of the backbone of the polypeptide chain due to hydrogen bonding between and NH groups of the peptide bond. Greek letter alpha helix is one of the most common ways in which a polypeptide chain forms all possible hydrogen bonds by twisting into a right-handed screw helix with the NH group of each amino acid residue hydrogen bonded to the CO of an adjacent turn of the helix as shown in figure 14.1. In Greek letter beta pleated sheet structure, all peptide chains are stretched out to nearly maximum extension and then lay side by side, which are held together by intermolecular hydrogen bonds. The structure resembles the pleated folds of drapery and therefore is known as Greek letter beta pleated sheet. 3. Tertiary structure of proteins. The tertiary structure of proteins represents overall folding of the polypeptide chains, that is, further folding of the secondary structure. It gives rise to 2 major molecular shapes, viz. Fibrous and globular. The main forces which stabilize the 2 degrees and 3 degrees structures of proteins are hydrogen bonds, disulfide linkages, van der Waals and electrostatic forces of attraction. Quaternary structure of proteins. Some of the proteins are composed of 2 or more polypeptide chains referred to as subunits. The spatial arrangement of these subunits with respect to each other is known as quaternary structure. 424 Chemistry. Fig. 14.3. Diagrammatic representation of protein structure. 2 subunits of 2 types in quaternary structure. A diagrammatic representation of all these 4 structures is given in figure 14.3, where each colored ball represents an amino acid. Figure 14.4. Primary, secondary, tertiary and quaternary structures of hemoglobin protein found in a biological system with a unique 3-dimensional structure and biological activity is called a native protein. When a protein in its native form is subjected to physical change like change in temperature or chemical change like change in pH, the hydrogen bonds are disturbed. Due to this, globules unfold and helix get uncoiled and protein loses its biological activity. This is called denaturation of 1,4,2,4 denaturation of proteins. 425. Biomolecules. Protein. During denaturation, secondary and tertiary structures are destroyed but primary structure remains intact. The coagulation of egg white on boiling is a common example of denaturation. Another example is curdling of milk, which is caused due to the formation of lactic acid by the bacteria present in milk. In text questions 14.4, the melting points and solubility in water of amino acids are generally higher than that of the corresponding haloacids. Explain 14.5. Where does the water present in the egg go after boiling? The egg life is possible due to the coordination of various chemical reactions in living organisms. An example is the digestion of food, absorption of appropriate molecules and ultimately production of energy. This process involves a sequence of reactions, and all these reactions occur in the body under very mild conditions. This occurs with the help of certain biocatalysts called enzymes. Almost all the enzymes are globular proteins. Enzymes are very specific for a particular reaction and for a particular substrate. They are generally named after the compound or class of compounds upon which they work. For example, the enzyme that catalyses hydrolysis of maltose into glucose is named as maltase 1222-11,6-12,6 maltase glucose CHO2-CHO. Sometimes enzymes are also named after the reaction where they are used. For example, the enzymes which catalyze the oxidation of one substrate with simultaneous reduction of another substrate are named as oxidoreductase enzymes. The ending of the name of an enzyme is ASE. Enzymes are needed only in small quantities for the progress of a reaction. Similar to the action of chemical catalysts, enzymes are said to reduce the magnitude of activation energy. For example, activation energy for acid hydrolysis of sucrose is 6.22 kJ/mol1, while the activation energy is only 2.15 kJ/mol1 when hydrolyzed by the enzyme sucrase. Mechanism for the enzyme action has been discussed in Unit 5. It has been observed that certain organic compounds are required in small amounts in our diet, but their deficiency causes specific diseases. These compounds are called vitamins. Most of the vitamins cannot be synthesized in our body, but plants can synthesize almost all of them, so they are considered as essential food factors. However, the bacteria of the gut can produce some of the vitamins required by us. All the vitamins are generally available in our diet. Different vitamins belong to various chemical classes, and it is difficult to define them on the basis of structure. They are generally regarded as organic compounds required in the diet in small amounts to perform specific biological functions for normal maintenance of optimum growth. 1.4.3. 1 Mechanism of enzyme action. 14.4 Vitamins. 14.4 Vitamins. 14.4 Vitamins. 14.4 Vitamins. 14.4 Vitamins. 14.3 Enzymes. 14.3 Enzymes. 14.3 Enzymes. 14.3 Enzymes. 14.3 Enzymes. 426 Chemistry and health of the organism. Vitamins are designated by alphabets A, B, C, D, etc. Some of them are further named as subgroups, e.g. B1, B2, B6, B12, etc. Excess of vitamins is also harmful, and vitamin pills should not be taken without the advice of doctor. The term vitamin was coined from the word vital amine, since the earlier identified compounds had amino groups. Later work showed that most of them did not contain amino groups, so the letter E was dropped and the term vitamin is used these days. Vitamins are classified into 2 groups depending upon their solubility in water or fat. Fat-soluble vitamins. Vitamins which are soluble in fat and oils but insoluble in water are kept in this group. These are vitamins A, D, E and K. They are stored in liver and adipose fat-storing tissues. 2 Water-soluble vitamins. B group vitamins and vitamin C are soluble in water, so they are grouped together. Water-soluble vitamins must be supplied regularly in diet because they are readily excreted in urine and cannot be stored, except vitamin B12 in our body. Some important vitamins, their sources and diseases caused by their deficiency are listed in Table 14.3. 1.4.4. 1 Classification of vitamins. Fish liver oil, carrots, butter and milk. Yeast, milk, green vegetables and cereals. Milk, egg white, liver, kidney. Yeast, milk, egg yolk, cereals and ground meat, fish, egg and curd. Citrus fruits. amla and green leafy vegetables exposure to sunlight, fish and egg yolks xerophthalmia hardening of cornea of eye night blindness beriberi loss of aptitude. Retarded growth chylosis fissuring at corners of mouth and lips, digestive disorders and burning sensation of the skin. Convulsions pernicious anemia RBC deficient in hemoglobin scurvy bleeding gums rickets bone deformities in children and osteomalacia soft bones and joint pain in adults 1. Vitamin A2, vitamin B1 thiamine 3, vitamin B2 riboflavin 4, vitamin B6 pyridoxine 5, vitamin B12 6. Vitamin C ascorbic acid 7, vitamin D SL, name of sources deficiency disease is no, vitamins table 14.3, some important vitamins. Their sources and their deficiency diseases. 427 Biomolecules 8, vitamin E9, vitamin K vegetable oils like wheat germ oil, sunflower oil, etc. Green leafy vegetables increased fragility of RBCs and muscular weakness increased blood clotting time every generation of each and every species resembles its ancestors in many ways. How are these characteristics transmitted from one generation to the next? It has been observed that nucleus of a living cell is responsible for this transmission of inherent characters. Also called heredity, the particles and nucleus of the cell, responsible for heredity, are called chromosomes which are made up of proteins and another type of biomolecules called nucleic acids. These are mainly of two types, the deoxyribonucleic acid DNA and ribonucleic acid RNA. Since nucleic acids are long-chain polymers of nucleotides, so they are also called polynucleotides. 14.514, 514, 514, 514, 5. Nucleic acids nucleic acids nucleic acids nucleic acids nucleic acids James Dewey Watson born in Chicago, Illinois, in 1928, Dr. Watson received his Ph.D. 1950 from Indiana University in zoology. He is best known for his discovery of the structure of DNA for which he shared with Francis Crick and Maurice Wilkins the 1962 Nobel Prize in Physiology and Medicine. They proposed that DNA molecule takes the shape of a double helix, an elegantly simple structure that resembles a gently twisted ladder. The rails of the ladder are made of alternating units of phosphate and the sugar deoxyribose. The rungs are each composed of a pair of purine pyrimidine bases. This research laid the foundation for the emerging field of molecular biology. The complementary pairing of nucleotide bases explains how identical copies of parental DNA pass on to two daughter cells. This research launched a revolution in biology that led to modern recombinant DNA techniques. Complete hydrolysis of DNA or RNA yields a pentose sugar, phosphoric acid and nitrogen-containing heterocyclic compounds called bases. In DNA molecules, the sugar moiety is Greek letter beta D2-deoxyribose, whereas in RNA molecule, it is Greek letter beta D-ribose. 1,4,5. 1 chemical composition of nucleic acids. 428 Chemistry uracil-U-thymine T cytosine C DNA contains 4 bases viz adenine A, guanine G, cytosine C and thymine T. RNA also contains 4 bases. The first 3 bases are same as in DNA but the fourth one is uracil-U. A unit formed by the attachment of a base to one position of sugar is known as nucleoside. In nucleosides, the sugar carbons are numbered as 1, 2, 3, etc. In order to distinguish these from the bases figure 14.5a, when nucleoside is linked to phosphoric acid at 5 position of sugar moiety, we get a nucleotide fig. 14.514, 5. 2 Structure of nucleic acids figure 14.5, structure of a nucleoside and B. A nucleotide. Nucleotides are joined together by phosphodiester linkage between 5 and 3 carbon atoms of the pentose sugar. The formation of a typical dinucleotide is shown in figure 14.6. 429 Biomolecules. A simplified version of nucleic acid chain is as shown below, figure 14.6, formation of a dinucleotide fig. 14.7, double-strand helix structure for DNA. Information regarding the sequence of nucleotides in the chain of a nucleic acid is called its primary structure. Nucleic acids have a secondary structure also. James Watson and Francis Crick gave a double-strand helix structure for DNA fig. 14.7, 2 nucleic acid chains are wound about each other and held together by hydrogen bonds between pairs of bases. The 2 strands are complementary to each other because the hydrogen bonds are formed between specific pairs of bases. Adenine forms hydrogen bonds with thymine whereas cytosine forms hydrogen bonds with guanine. In secondary structure of RNA single-stranded helix is present which sometimes folds back on itself. RNA molecules are of 3 types and they perform different functions. They are named as messenger RNA mRNA, ribosomal RNA rRNA and transfer RNA tRNA. Sugar phosphate base sugar base and base. 430 Chemistry Hargobindkorana DNA fingerprinting. It is known that every individual has unique fingerprints. These occur at the tips of the fingers and have been used for identification for a long time, but these can be altered by surgery. A sequence of bases on DNA is also unique for a person, and information regarding this is called DNA fingerprinting. It is same for every cell and cannot be altered by any known treatment. DNA fingerprinting is now used in forensic laboratories for identification of criminals. 2. To determine paternity of an individual. 3. To identify the dead bodies in any accident by comparing the DNAs of parents or children. 5. To identify racial groups. To rewrite biological evolution. DNA is the chemical basis of heredity and may be regarded as the reserve of genetic information. DNA is exclusively responsible for maintaining the identity of different species of organisms over millions of years. A DNA molecule is capable of self-duplication during cell division, and identical DNA strands are transferred to daughter cells. Another important function of nucleic acids is the protein synthesis in the cell. Actually, the proteins are synthesized by various RNA molecules in the cell, but the message for the synthesis of a particular protein is present in DNA. Hormones are molecules that act as intercellular messengers. These are produced by endocrine glands in the body and are poured directly in the bloodstream, which transports them to the site of action. In terms of chemical nature, some of these are steroids, e.g., estrogens and androgens. Some are polypeptides, for example insulin and endorphins, and some others are amino acid derivatives such as epinephrine and norepinephrine. Hormones have several functions in the body. They help to maintain the balance of biological activities in the body. The role of insulin in keeping the blood glucose level within the narrow limit is an example of this function. Insulin is released in response to the rapid rise in blood glucose level. On the other hand, hormone glucagon tends to increase the glucose level in the blood. The two hormones together regulate the glucose level in the blood. Epinephrine and norepinephrine mediate responses to external stimuli. Growth hormones and sex hormones play a role in growth and development. Thyroxine produced in the thyroid gland is an iodinated derivative of amino acid tyrosine. Abnormally low level of thyroxine leads 1,4,5,3 biological functions of nucleic acids. Hargobind Khurana was born in 1922. He obtained his MSc degree from Punjab University in Lahore. He worked with Professor Vladimir Prelog, who molded Khurana's thought and philosophy towards science, work and effort. After a brief stay in India in 1949, Khurana went back to England and worked with Professor G. W. Kenner and Professor A. R. Todd. It was at Cambridge, UK, that he got interested in both proteins and nucleic acids. Dr. Khurana shared the Nobel Prize for Medicine and Physiology in 1968 with Marshall Nirenberg and Robert Halley for cracking the genetic code. 14614614614614614 capital H-O-R-M-O-N-E-S, capital H-O-R-M-O-N-E-S, capital H-O-R-M-O-N-E-S, capital H-O-R-M-O-N. 431 biomolecules to hypothyroidism, which is characterized by letharginess and obesity. Increased level of thyroxine causes hyperthyroidism. Low level of iodine in the diet may lead to hypothyroidism and enlargement of the thyroid gland. This condition is largely being controlled by adding sodium iodide to commercial table salt iodized salt. Steroid hormones are produced by adrenal cortex and gonads, testes in males and ovaries in females. Hormones released by the adrenal cortex play a very important role in the functions of the body. For example, glucocorticoids control the carbohydrate metabolism, modulate inflammatory reactions, and are involved in reactions to stress. The mineralocorticoids control the level of excretion of water and salt by the kidney. If adrenal cortex does not function properly, then one of the results may be Addison's disease, characterized by hypoglycemia, weakness and increased susceptibility to stress. The disease is fatal unless it is treated by glucocorticoids and mineralocorticoids. Hormones released by gonads are responsible for development of secondary sex characters. Testosterone is the major sex hormone produced in males. It is responsible for development of secondary male characteristics: deep voice, facial hair, general physical constitution, and estradiol is the main female sex hormone. It is responsible for development of secondary female characteristics and participates in the control of menstrual cycle. Progesterone is responsible for preparing the uterus for implantation of fertilized egg. In text questions 14.6 Why cannot vitamin C be stored in our body? 14.7 What products would be formed when a nucleotide from DNA containing thymine is hydrolyzed? 14.8 When RNA is hydrolyzed? There is no relationship among the quantities of different bases obtained. What does this fact suggest about the structure of RNA? Summary. Carbohydrates are optically active polyhydroxyaldehydes or ketones, or molecules which provide such units on hydrolysis. They are broadly classified into three groups: monosaccharides, disaccharides and polysaccharides. Glucose, the most important source of energy for mammals, is obtained by the digestion of starch. Monosaccharides are held together by glycosidic linkages to form disaccharides or polysaccharides. Proteins are the polymers of about 20 different Greek letter alpha amino acids which are linked by peptide bonds. 10 amino acids are called essential amino acids because they cannot be synthesized by our body, hence must be provided through diet. Proteins perform various structural and dynamic functions in the organisms. Proteins which contain only Greek letter alpha amino acids are called simple proteins. The secondary or tertiary structure of proteins get disturbed on change of pH or temperature and they are not able to perform their functions. This is called denaturation of proteins. Enzymes are biocatalysts which speed up the reactions in biosystems. They are very specific and selective in their action, and chemically all enzymes are proteins. Vitamins are accessory food factors required in the diet. They are classified as fat-soluble A, D, E and K and water-soluble Greek letter beta group and C. Deficiency of vitamins leads to many diseases. 432 Chemistry. Nucleic acids are the polymers of nucleotides which in turn consist of a base, a pentose sugar and phosphate moiety. Nucleic acids are responsible for the transfer of characters from parents to offsprings. There are two types of nucleic acids, DNA and RNA. DNA contains a 5-carbon sugar molecule called 2-deoxyribose, whereas RNA contains ribose. Both DNA and RNA contain adenine, guanine and cytosine. The fourth base is thymine in DNA and uracil in RNA. The structure of DNA is a double strand, whereas RNA is a single strand molecule. DNA is the chemical basis of heredity and had the coded message for proteins to be synthesized in the cell. There are three types of RNA: mRNA, RNA and tRNA, which actually carry out the protein synthesis in the cell. 14.1 What are monosaccharides? 14.2 What are reducing sugars? 14.3 Write two main functions of carbohydrates in plants. 14.4 Classify the following into monosaccharides and disaccharides: ribose, 2-deoxyribose, maltose, galactose, fructose and lactose. 14.5 What do you understand by the term glycosidic linkage? 14.6 What is glycogen? How is it different from starch? 14.7 What are the hydrolysis products of isosucrose and 2-lactose? 14.8 What is the basic structural difference between starch and cellulose? 14.9 What happens when D-glucose is treated with the following reagents: I2-bromine water 3HNO3? 14.10 Enumerate the reactions of D-glucose which cannot be explained by its open chain structure. 14.11 What are essential and non-essential amino acids? Give two examples of each type. 14.1 To define the following as related to proteins: I peptide linkage, 2 primary structure, 3 denaturation. 14.13 What are the common types of secondary structure of proteins? 14.14 What type of bonding helps in stabilizing the Greek letter alpha helix structure of proteins? 14.15 Differentiate between globular and fibrous proteins. 14.16 How do you explain the amphoteric behavior of amino acids? 14.17 What are enzymes? 14.18 What is the effect of denaturation on the structure of proteins? 14.19 How are vitamins classified? Name the vitamin responsible for the coagulation of blood. 14.20 Why are vitamin A and vitamin C essential to us? Give their important sources. 14.21 What are nucleic acids? Mention their two important functions. 14.22 What is the difference between a nucleoside and a nucleotide? 14.23 The two strands in DNA are not identical but are complementary. Explain. 14.24 Write the important structural and functional differences between DNA and RNA. 14.25 What are the different types of RNA found in the cell? Exercises. Capital E, X, E, R, C, I, S, E, S, capital E, X, E, R, C, I, S, E, S, capital E, X, E, R, C, I, S, E, S, capital E, X, E. Do you think that daily life would have been easier and colorful without the discovery and varied applications of polymers? The use of polymers in the manufacture of plastic buckets, cups and saucers, children's toys, packaging bags, synthetic clothing materials, automobile tires, gears and seals, electrical insulating materials and machine parts has completely revolutionized the daily life as well as the industrial scenario. Indeed, the polymers are the backbone of 4 major industries: viz. plastics, elastomers, fibers and paints and varnishes. The word polymer is coined from 2 Greek words. Poly means many and mer means unit or part. The term polymer is defined as very large molecules having high molecular mass 103-107 U. These are also referred to as macromolecules, which are formed by joining of repeating structural units on a large scale. The repeating structural units are derived from some simple and reactive molecules known as monomers and are linked to each other by covalent bonds. The process of formation of polymers from respective monomers is called polymerization. After studying this unit, you will be able to explain the terms monomer, polymer and polymerization and appreciate their importance, distinguish between various classes of polymers and different types of polymerization processes, appreciate the formation of polymers from mono and bifunctional monomer molecules, describe the preparation of some important synthetic polymers and their properties, appreciate the importance of polymers in daily life. Objectives. Copolymerization has been used by nature in polypeptides which may contain as many as 20 different amino acids. Chemists are still far behind. Unit 15 polymers 15 polymers 15.115 capital C L A S S I F I C A T I O N capital C L A S S I F I C A T I O N capital C L of polymers of polymers. There are several ways of classification of polymers based on some special considerations. One of the common classifications of polymers is based on source from which polymer is derived. Under this type of classification, there are three subcategories. 1. Natural polymers. These polymers are found in plants and animals. Examples are proteins, cellulose, starch, some resins and rubber. 434 Chemistry 2. Semi-synthetic polymers. Cellulose derivatives as cellulose acetate rayon and cellulose nitrate, etc. are the usual examples of this subcategory. 3. Synthetic polymers. A variety of synthetic polymers is plastic polythene, synthetic fibers nylon 6 and synthetic rubbers Bunas are examples of man-made polymers extensively used in daily life as well as in industry. Polymers can also be classified on the basis of their structure, molecular forces or modes of polymerization. There are two broad types of polymerization reactions, that is, the addition or chain growth polymerization and condensation or step growth polymerization. In this type of polymerization, the molecules of the same monomer or different monomers add together on a large scale to form a polymer. The monomers used are unsaturated compounds, e.g., alkenes, alkadenes and their derivatives. This mode of polymerization leads to an increase in chain length, and chain growth can take place through the formation of either free radicals or ionic species. However, the free radical governed addition or chain growth polymerization is the most common mode. 1. Free radical mechanism. A variety of alkenes or dienes and their derivatives are polymerized in the presence of a free radical generating initiator catalyst like benzoyl peroxide, acetyl peroxide, tert-butyl peroxide, etc. For example, the polymerization of ethene to polythene consists of heating or exposing to light a mixture of ethene with a small amount of benzoyl peroxide initiator. The process starts with the addition of phenyl free radical formed by the peroxide to the ethene double bond, thus generating a new and larger free radical. This step is called chain initiating step. As this radical reacts with another molecule of ethene, another bigger sized radical is formed. The repetition of this sequence with new and bigger radicals carries the reaction forward, and the step is termed as chain propagating step. Ultimately, at some stage the product radical thus formed reacts with another radical to form the polymerized product. This step is called the chain terminating step. The sequence of steps involved in the formation of polythene are depicted as follows. Chain initiation steps 1 5, 2, 1, 1 mechanism of addition polymerization 15.215, 215, 2, 15, 215, 2, types of capital P O L Y M E R I S A T I O N capital P O L Y M E R I S A T I O N capital P O reactions 1 5, 2, 1 addition polymerization or chain growth polymerization 15.1 What are polymers? In text questions 435 Polymers. Chain propagating step, chain terminating step. For termination of the long chain, these free radicals can combine in different ways to form polythene. One mode of termination of chain is shown as under. The addition polymers formed by the polymerization of a single monomeric species are known as homopolymers. For example, polythene discussed above is a homopolymer. The polymers made by addition polymerization from two different monomers are termed as copolymers. Bunas, which is formed by polymerization of 1,3-butadiene and styrene, is an example of copolymer formed by addition polymerization. 1,5,2,1,2 2. Some important addition polymers of polythene. Polythenes are linear or slightly branched long-chain molecules. These are capable of repeatedly softening on heating and hardening on cooling and are thus thermoplastic polymers. There are 2 types of polythene as given below. Low-density polythene. It is obtained by the polymerization of ethene under high pressure of 1000 to 2000 atmospheres at a temperature of 350 K to 570 K in the presence of traces of dioxygen or a peroxide initiator catalyst. The low-density polythene LDP is obtained through the free radical addition and H-atom abstraction. It has highly branched structure. These polymers have straight chain structure with some branches as shown below. Low-density polythene is chemically inert and tough but flexible and a poor conductor of electricity. Hence, it is used in the insulation of electricity-carrying wires and manufacture of squeeze bottles, toys and flexible pipes. 2. High-density polythene. It is formed when addition polymerization of ethene takes place in a hydrocarbon solvent in the presence of a catalyst such as triethylaluminium and titanium tetrachloride Ziegler-Naudot catalyst at a temperature of 333 K to 343 K and under a pressure of 6-7 atmospheres. High-density polythene HDP thus produced, consists of linear molecules as shown below and has a high density due to close packing. Such polymers are also called linear polymers. High-density polymers are also chemically inert and more tough and hard. It is used for manufacturing buckets, dustbins, bottles, pipes, etc. Tetrafluoroethene Teflon. Teflon is manufactured by heating tetrafluoroethene with a free radical or persulfate catalyst at high pressures. It is chemically inert and resistant to attack by corrosive reagents. It is used in making oil seals and gaskets and also used for non-stick surface-coated utensils. See polyacrylonitrile. The addition polymerization of acrylonitrile in presence of a peroxide catalyst leads to the formation of polyacrylonitrile. Polyacrylonitrile is used as a substitute for wool in making commercial fibers as Orlan or acrylan. Is a homopolymer or a copolymer. It is a homopolymer and the monomer from which it is obtained is styrene C6H5CHCH2. Example 15.1 Example 15.1 Example 15.1 Example 15.1 Example 15.1 Solution. This type of polymerization generally involves a repetitive condensation reaction between two bifunctional or trifunctional monomeric units. These polycondensation reactions may result in the loss of some simple molecules as water, alcohol, hydrogen chloride, etc., and led to the formation of high molecular mass condensation polymers. In these reactions, the product of each step is again a bifunctional species and the sequence of condensation goes on. Since each step produces a distinct functional yeast species and is independent of each other, this process is also called a step growth polymerization. The formation of pterylene or dacron by the interaction of ethylene glycol and terephthalic acid is an example of this type of polymerization. Polyamides. These polymers possessing amide linkages are important examples of synthetic fibers and are termed as nylons. The general method of preparation consists of the condensation polymerization of diamines with dicarboxylic acids or condensation of amino acids or their lactams. Nylons. Nylon 6. It is prepared by the condensation polymerization of hexamethylonadiamine with adipic acid under high pressure and at high temperature. Nylon 6 is fiber-forming solid. It possesses high tensile strength. This characteristic can be attributed to the strong intermolecular forces like hydrogen bonding. These strong forces also led to close packing of chains and thus impart crystalline nature. Nylon 6 is used in making sheets, bristles for brushes and in textile industry. 2. Nylon 6. It is obtained by heating caprolactam with water at a high temperature 1,5,2. 2. Condensation polymerization or step growth polymerization NCHNQ2 HOCO hook 2 ethylene glycol ethane 1. 2. Diol terephthalic acid benzene 1. 4. Decarboxylic acid pterylene or dacron CCNOOxCH22015. 2. 1. Some important condensation polymers. 438 Chemistry. Nylon 6 is used for the manufacture of tire cords, fabrics and ropes. Polyesters. These are the polycondensation products of dicarboxylic acids and diols. Dacron or pterylene is the best known example of polyesters. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid at 420 to 460 K in the presence of zinc acetate antimony trioxide catalyst as per the reaction given earlier. Dacron fiber pterylene is crease resistant and is used in blending with cotton and wool fibers and also as glass reinforcing materials in safety helmets, etc. Novolac on heating with formaldehyde undergoes cross-linking to form an infusible solid mass called bakelite. It is thermosetting polymer which cannot be reused or remolded. Thus, bakelite is formed by cross-linking of linear chains of the polymer Novolac. Bakelite is used for making combs, phonograph records, electrical switches and handles of various utensils. See phenol, formaldehyde polymer, bakelite and related polymers. Phenol, formaldehyde polymers are the oldest synthetic polymers. These are obtained by the condensation reaction of phenol with formaldehyde in the presence of either an acid or a base catalyst. The reaction starts with the initial formation of O and or p-hydroxymethylphenol derivatives, which further react with phenol to form compounds having rings joined to each other through CH2 groups. The initial product could be a linear product Novolac used in paints. 439 Polymers. D-melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by the condensation polymerization of melamine and formaldehyde. It is used in the manufacture of unbreakable crockery. Bakelite CH2CH2OOHC2CH2CH2CH2CH2CH2OOOCH2 15. To write the names of monomers of the following polymers. 15.3 Classify the following as addition and condensation polymers: terylene, bakelite, polythene, Teflon. In text questions. Copolymerization is a polymerization reaction in which a mixture of more than one monomeric species is allowed to polymerize and form a copolymer. The copolymer can be made not only by chain growth polymerization but by step growth polymerization also. It contains multiple units of each monomer used in the same polymeric chain. 1,5,2,3 copolymerization. 440 Chemistry. For example, a mixture of 1,3-butadiene and styrene can form a copolymer. Copolymers have properties quite different from homopolymers. For example, butadiene-styrene copolymer is quite tough and is a good substitute for natural rubber. It is used for the manufacture of auto tires, floor tiles, footwear components, cable insulation, etc. 1. Natural rubber. Rubber is a natural polymer and possesses elastic properties. It is also termed as elastomeric polymer. In elastomeric polymers, the polymer chains are held together by the weak intermolecular forces. These weak binding forces permit the polymer to be stretched. A few crosslinks are introduced in between the chains, which help the polymer to retract to its original position after the force is released. Rubber has a variety of uses. It is manufactured from rubber latex, which is a colloidal dispersion of rubber in water. This latex is obtained from the rubber tree, which is found in India, Sri Lanka, Indonesia, Malaysia and South America. Natural rubber may be considered as a linear polymer of isoprene 2-methyl-1,3-butadiene and is also called a cis-1,4-polyisoprene. The cis-polyisoprene molecule consists of various chains held together by weak van der Waals interactions and has a coiled structure. Thus, it can be stretched like a spring and exhibits elastic properties. Vulcanization of rubber. Natural rubber becomes soft at high temperature, 335 K, and brittle at low temperatures, 283 K, and shows high water absorption capacity. It is soluble in nonpolar solvents and is non-resistant to attack by oxidizing agents. To improve upon these physical properties, a process of vulcanization is carried out. This process consists of heating a mixture of raw rubber with sulfur and an appropriate additive 1,5,2,4 rubber. At a temperature range between 373 K to 415 K on vulcanization, sulfur forms cross-links at the reactive sites of double bonds and thus the rubber gets stiffened. In the manufacture of tire rubber, 5-sulfur is used as a cross-linking agent. The probable structures of vulcanized rubber molecules are depicted below. 2. Synthetic rubber. Synthetic rubber is any vulcanizable rubber-like polymer, which is capable of getting stretched to twice its length. However, it returns to its original shape and size as soon as the external stretching force is released. Thus, synthetic rubbers are either homopolymers of 1,3-butadiene derivatives or copolymers of 1,3-butadiene or its derivatives with another unsaturated monomer. Preparation of synthetic rubbers. 1. Neoprene. Neoprene or polychloroprene is formed by the free radical polymerization of chloroprene. It has superior resistance to vegetable and mineral oils. It is used for manufacturing conveyor belts, gaskets and hoses. 2. Buna, and you have already studied about Buna S, in section 1.5.1.3. Buna N is obtained by the copolymerization of 1,3-butadiene and acrylonitrile in the presence of a peroxide catalyst. It is resistant to the action of petrol, lubricating oil and organic solvents, is used in making oil seals, tank lining, etc. 15.315.315.315.315.3 Capital M-O-L-E-C-U-L-A-R, capital M-O-L-E-C-U-L-A-R, capital M-O-L-E-C-U-L-A-R, capital M-O-L. Massive polymers 15.415.415.415.4 capital B-I-O-D-E-G-R-A-D-A-B-L-E, capital B-I-O-D-E-G-R-A-D-A-B-L-E, capital B-I-O-D, polymers, capital P-O-L-Y-M-E-R-S, capital P-O-L-Y-M-E-R-S, capital P-O-L-Y-M-E-R-S, capital P-O-L-Y-M-E, polymer. Properties are closely related to their molecular mass, size and structure. The growth of the polymer chain during their synthesis is dependent upon the availability of the monomers in the reaction mixture. Thus, the polymer sample contains chains of varying lengths and hence its molecular mass is always expressed as an average. The molecular mass of polymers can be determined by chemical and physical methods. A large number of polymers are quite resistant to the environmental degradation processes and are thus responsible for the accumulation of polymeric solid waste materials. These solid wastes cause acute environmental problems and remain undegraded for quite a long time. In view of the general awareness and concern for the problems created by the polymeric solid wastes, certain new biodegradable synthetic polymers have been designed and developed. These polymers contain functional groups similar to the functional groups present in biopolymers. Aliphatic polyesters are one of the important classes of biodegradable polymers. Some important examples are given below. 1. Poly Greek letter beta 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 hydroxybutyrate. Co Greek letter beta 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 hydroxyvalerate PHBB. It is obtained by the copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. PHBB is used in specialty packaging, orthopedic devices and in controlled release of drugs. PHBB undergoes bacterial degradation in the environment. 2. Nylon 2 Nylon 6. It is an alternating polyamide copolymer of glycine H2N, CH2-CLU and aminocaproic acid H2N CH2-5-CLU and is biodegradable. Can you write the structure of this copolymer? 15.4 Explain the difference between BUNA-N and BUNA-S. 15.5 Arrange the following polymers in increasing order of their intermolecular forces. Nylon 6. 6. BUNA-S, polythene. In text questions, in text questions, in text questions, in text questions, in text questions. Name of polymer. Monomer structure uses polypropene. Propene manufacture of ropes, toys, pipes, fibers, etc. Polystyrene. Styrene is insulator, wrapping material, manufacture of toys, radio and television cabinets. Polyvinyl chloride. Vinyl chloride manufacture of rain PVC coats, handbags, vinyl flooring, water pipes. Urea. Formaldehyde. Urea for making unbreak resin. B. Formaldehyde able cups and laminated sheets. Glyptoethylene glycol manufacture of B. Phthalic acid paints and lacquers. Bakelite. A phenol for making combs. B. Formaldehyde electrical switches, handles of utensils and computer disks. Table 15.1. Some other commercially important polymers. Besides the polymers already discussed, some other commercially important polymers along with their structures and uses are given below in Table 15.1. 15.515, 515, 515, 515, 5. Polymers of polymers of polymers of polymers of polymers of commercial importance. Polymers are defined as high molecular mass macromolecules, which consist of repeating structural units derived from the corresponding monomers. These polymers may be of natural or synthetic origin and are classified in a number of ways. In the presence of an organic peroxide initiator, the alkenes and their derivatives undergo addition polymerization or chain growth polymerization through a free radical mechanism. Polythene, Teflon, Orlon, etc. are formed by addition polymerization of an appropriate alkene or its derivative. Condensation polymerization reactions are shown by the interaction of bi or polyfunctional monomers containing NH2ON, CU groups. This type of polymerization proceeds through the elimination of certain simple molecules as H2O, CH3O, etc. Formaldehyde reacts with phenol and melamine to form the corresponding condensation polymer products. The condensation, capital S, U, M, A, R, Y, 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 capital S, U. 15.1 Explain the terms polymer and monomer. 15.2 What are natural and synthetic polymers? Give 2 examples of each type. 15.3 Distinguish between the terms homopolymer and copolymer and give an example of each. 15.4 How do you explain the functionality of a monomer? 15.5 Define the term polymerization. 15.6 is NHCHRCON, a homopolymer or copolymer. 15.7 Why do elastomers possess elastic properties? 15.8 How can you differentiate between addition and condensation polymerization? 15.9 Explain the term copolymerization and give 2 examples. 15.10 Write the free radical mechanism for the polymerization of ethene. 15.11 Define thermoplastics and thermosetting polymers with 2 examples of each. 15.12 Write the monomers used for getting the following polymers: I polyvinyl chloride, 2 Teflon, 3 bakelite. 15.13 Write the name and structure of one of the common initiators used in free radical addition polymerization. 15.14 How does the presence of double bonds in rubber molecules influence their structure and reactivity? 15.15 Discuss the main purpose of vulcanization of rubber. 15.16 What are the monomeric repeating units of nylon 6 and nylon 6? 15.17 Write the names and structures of the monomers of the following polymers: ibuna S2 buna and 3 dacron IV neoprene. 15.18 Identify the monomer in the following polymeric structures. I exercises polymerization progresses through step-by-step and is also called a step growth polymerization. Nylon, bakelite and dacron are some of the important examples of condensation polymers. However, a mixture of 2 unsaturated monomers exhibits copolymerization and forms a copolymer containing multiple units of each monomer. Natural rubber is a cis 1,4-polyisoprene and can be made more tough by the process of vulcanization with sulfur. Synthetic rubbers are usually obtained by copolymerization of alkene and 1,3-butadiene derivatives. In view of the potential environmental hazards of synthetic polymeric wastes, certain biodegradable polymers such as PHBD and nylon 2 nylon 6 are developed as alternatives. 445 Polymers. 15.19 How is dacron obtained from ethylene glycol and terephthalic acid? 15.20 What is a biodegradable polymer? Give an example of a biodegradable aliphatic polyester. Answers of some in-text questions. 15.1 Polymers are high molecular mass substances consisting of large numbers of repeating structural units. They are also called as macromolecules. Some examples of polymers are polythene, bakelite, rubber, nylon 6, etc. 15.2 Ihexamethylene diamine and adipic acid, 2 caprolactam, 3 tetrafluoroethene. 15.3 Addition polymers: polyvinyl chloride, polythene. Condensation polymers: pterylene, bakelite. 15.4 Buna-N is a copolymer of 1,3-butadiene and acrylonitrile, and Buna-S is a copolymer of 1,3-butadiene and styrene. 15.5 In order of increasing intermolecular forces: Buna-S, polythene, nylon 6. 446 Chemistry Note. After studying this unit you will be able to visualize the importance of chemistry in daily life, explain the term chemotherapy, describe the basis of classification of drugs, explain drug-target interaction of enzymes and receptors, explain how various types of drugs function in the body, know about artificial sweetening agents and food preservatives, discuss the chemistry of cleansing agents. Objectives: from living perception to abstract thought, and from this to practice. V.I. Lenin. 16 Unit 16, capital C, H, E, M, I, S, T, R, capital C, H, E, M, I, S, T, R, capital C, H, E, M, I, S, T, R, capital C, H, E, M, I, S. Viver error chemistry Viver error By now, you have learned the basic principles of chemistry and also realized that it influences every sphere of human life. The principles of chemistry have been used for the benefit of mankind. Think of cleanliness: the materials like soaps, detergents, household bleaches, toothpastes, etc. will come to your mind. Look towards the beautiful clothes immediately. Chemicals of the synthetic fibers used for making clothes and chemicals giving colors to them will come to your mind. Food materials: again, a number of chemicals about which you have learned in the previous unit will appear in your mind. Of course, sickness and diseases remind us of medicines. Again, chemicals, explosives, fuels, rocket propellants, building and electronic materials, etc., are all chemicals. Chemistry has influenced our life so much that we do not even realize that we come across chemicals at every moment, that we ourselves are beautiful chemical creations and all our activities are controlled by chemicals. In this unit, we shall learn the application of chemistry in 3 important and interesting areas, namely, medicines, food materials and cleansing agents. Drugs are chemicals of low molecular masses 100-500 U. These interact with macromolecular targets and produce a biological response. When the biological response is therapeutic and useful, These chemicals are called medicines and are used in diagnosis, prevention and treatment of diseases. Most of the drugs used as medicines are potential poisons, if taken in doses higher than those recommended. Use of chemicals for therapeutic effect is called chemotherapy. 16.116, 116, 116, 116, 1. Drugs and drugs and drugs and drugs and drugs and ther. Capital C L A S S I F I C A T I O N. Capital C L A S S I F I C A T I O N. Capital C L. 448 Chemistry drugs can be classified mainly on criteria outlined as follows. On the basis of pharmacological effect. This classification is based on pharmacological effect of the drugs. It is useful for doctors because it provides them the whole range of drugs available for the treatment of a particular type of problem. For example, analgesics have pain-killing effect, antiseptics kill or arrest the growth of microorganisms. Beyond the basis of drug action, it is based on the action of a drug on a particular biochemical process. For example, all antihistamines inhibit the action of the compound, histamine, which causes inflammation in the body. There are various ways in which action of histamines can be blocked. You will learn about this in section 163.2. C. On the basis of chemical structure. It is based on the chemical structure of the drug. Drugs classified in this way share common structural features and often have similar pharmacological activity. For example, sulfonamides have common structural feature, given below. Structural features of sulfonamides. D. On the basis of molecular targets. Drugs usually interact with biomolecules such as carbohydrates, lipids, proteins and nucleic acids. These are called target molecules or drug targets. Drugs possessing some common structural features may have the same mechanism of action on targets. The classification based on molecular targets is the most useful classification for medicinal chemists. Macromolecules of biological origin perform various functions in the body. For example, proteins which perform the role of biological catalysts in the body are called enzymes. Those which are crucial to communication system in the body are called receptors. Carrier proteins carry polar molecules across the cell membrane. Nucleic acids have coded genetic information for the cell. Lipids and carbohydrates are structural parts of the cell membrane. We shall explain the drug-target interaction with the examples of enzymes and receptors. A catalytic action of enzymes. For understanding the interaction between a drug and an enzyme, it is important to know how do enzymes catalyze the reaction. Section 5.2.4. In their catalytic activity, enzymes perform two major functions. The first function of an enzyme is to hold the substrate for a chemical reaction. Active sites of enzymes hold the substrate molecule in a suitable position, so that it can be attacked by the reagent effectively. 161. Classification of drugs. 16.216, 216, 216, 216, 2. Drug target. Drug target. Drug target. Drug target. Drug target. Capital I N T E R A C T I O N. Capital I N T E R A C T I O N. Capital I N T E R A C T. 162. Enzymes as drug targets. 449 Chemistry in Everyday Life. Figure 16.2. Drug and substrate competing for active site. 2. The second function of an enzyme is to provide functional groups that will attack the substrate and carry out chemical reaction. B. Drug-enzyme interaction. Drugs inhibit any of the above-mentioned activities of enzymes. These can block the binding site of the enzyme and prevent the binding of substrate, or can inhibit the catalytic activity of the enzyme. Such drugs are called enzyme inhibitors. Drugs inhibit the attachment of substrate on active site of enzymes in two different ways. Drugs compete with the natural substrate for their attachment on the active sites of enzymes. Such drugs are called competitive inhibitors. Figure 16.2. Figure 16.1. Active site of an enzyme. B. Substrate. C. Substrate held in active site of the enzyme. 2. Some drugs do not bind to the enzyme's active site. These bind to a different site of enzyme which is called allosteric site. This binding of inhibitor at allosteric site. Figure 16.3 changes the shape of the active site in such a way that substrate cannot recognize it. If the bond formed between an enzyme and an inhibitor is a strong covalent bond, and substrates bind to the active site of the enzyme through a variety of interactions such as ionic bonding, hydrogen bonding, van der Waals interaction, or dipole-dipole interaction. Figure 16.1. Figure 16.3. Non-competitive inhibitor changes the active site of enzyme after binding at allosteric site. 450 Chemistry cannot be broken easily, then the enzyme is blocked permanently. The body then degrades the enzyme inhibitor complex and synthesizes the new enzyme. Receptors are proteins that are crucial to body's communication process. Majority of these are embedded in cell membranes. Fig. 16.4. Receptor proteins are embedded in the cell membrane in such a way that their small part possessing active site projects out of the surface of the membrane and opens on the outside region of the cell membrane. Fig. 16.416. 2 receptors as drug targets. Figure 16.4. Receptor protein embedded in the cell membrane. The active site of the receptor opens on the outside region of the cell. Figure 16.5. A receptor receiving chemical messenger. B. Shape of the receptor changed after attachment of messenger. C. Receptor regains structure after removal of chemical messenger. There are a large number of different receptors in the body that interact with different chemical messengers. These receptors show selectivity for one chemical messenger over the other because their binding sites have different shape, structure and amino acid composition. In the body, message between two neurons and that between neurons to muscles is communicated through certain chemicals. These chemicals, known as chemical messengers, are received at the binding sites of receptor proteins. To accommodate a messenger, shape of the receptor site changes. This brings about the transfer of message into the cell. Thus, chemical messenger gives message to the cell without entering the cell. Figure 16.5. 451. Chemistry in everyday life. Drugs that bind to the receptor site and inhibit its natural function are called antagonists. These are useful when blocking of message is required. There are other types of drugs that mimic the natural messenger by switching on the receptor. These are called agonists. These are useful when there is lack of natural chemical messenger. In this section, we shall discuss the therapeutic action of a few important classes of drugs. Overproduction of acid in the stomach causes irritation and pain. In severe cases, ulcers are developed in the stomach. Until 1970, only treatment for acidity was administration of antacids, such as sodium hydrogen carbonate or a mixture of aluminium and magnesium hydroxide. However, excessive hydrogen carbonate can make the stomach alkaline and trigger the production of even more acid. Metal hydroxides are better alternatives because of being insoluble. These do not increase the pH above neutrality. These treatments control only symptoms, and not the cause. Therefore, with these metal salts, the patients cannot be treated easily. In advanced stages, ulcers become life-threatening and its only treatment is removal of the affected part of the stomach. A major breakthrough in the treatment of hyperacidity came through the discovery according to which a chemical, histamine, stimulates the secretion of pepsin and hydrochloric acid in the stomach. The drug cimetidine Tegamet was designed to prevent the interaction of histamine with the receptors present in the stomach wall. This resulted in release of lesser amount of acid. The importance of the drug was so much that it remained the largest selling drug in the world until another drug, ranitidine Zantac, was discovered. 16.316, 316, 316, 316, 3. Therapeutic action of 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 different classes of drugs, different classes of drugs, different classes of drugs, different classes of drugs, different classes of drugs. 16.3. 1. Antacids. Histamine is a potent vasodilator. It has various functions. It contracts the smooth muscles in the bronchi and gut and relaxes other muscles, such as those in the walls of fine blood vessels. Histamine is also responsible for the nasal congestion associated with common cold and allergic response to pollen. Synthetic drugs, brompheniramine dimidicapentterphenidine celdane, act as antihistamines. They interfere with the natural action. 16.3. 2. Antihistamines. 452. Chemistry of histamine. By competing with histamine for binding sites of receptor where histamine exerts its effect. Now the question that arises is, why do above-mentioned antihistamines not affect the secretion of acid in stomach? The reason is that anti-allergic and antacid drugs work on different receptors. 16.3. 3. Neurologically active drugs. Tranquilizers and analgesics are neurologically active drugs. These affect the message transfer mechanism from nerve to receptor. Tranquilizers are a class of chemical compounds used for the treatment of stress, and mild or even severe mental diseases. These relieve anxiety, stress, irritability or excitement by inducing a sense of well-being. They form an essential component of sleeping pills. There are various types of tranquilizers. They function by different mechanisms. For example, noradrenaline is one of the neurotransmitters that plays a role in mood changes. If the level of noradrenaline is low for some reason, then the signal-sending activity becomes low, and the person suffers from depression. In such situations, antidepressant drugs are required. These drugs inhibit the enzymes which catalyze the degradation of noradrenaline. If the enzyme is inhibited, this important neurotransmitter is slowly metabolized and can activate its receptor for longer periods of time, thus counteracting the effect of depression. Iproniacid and phenelzine are two such drugs. Some tranquilizers, namely chlordiazepoxide and meprobamate, are relatively mild tranquilizers suitable for relieving tension. Equinol is used in controlling depression and hypertension. 453 Chemistry and everyday life derivatives of barbituric acid vis, veronal, amytol, nembutal, luminol and seconal constitute an important class of tranquilizers. These derivatives are called barbiturates. Barbiturates are hypnotic, that is, sleep-producing agents. Some other substances used as tranquilizers are Valium and serotonin B. Analgesics. Analgesics reduce or abolish pain without causing impairment of consciousness, mental confusion, incoordination or paralysis or some other disturbances of nervous system. These are classified as follows: I non-narcotic non-addictive analgesics. 2 narcotic drugs. I non-narcotic non-addictive analgesics. Aspirin and paracetamol belong to the class of non-narcotic analgesics. Aspirin is the most familiar example. Aspirin inhibits the synthesis of chemicals known as prostaglandins which stimulate inflammation in the tissue and cause pain. These drugs are effective in relieving skeletal pain such as that due to arthritis. These drugs have many other effects such as reducing fever, antipyretic and preventing platelet coagulation. Because of its anti-blood clotting action, aspirin finds use in prevention of heart attacks. 2 narcotic analgesics. Morphine and many of its homologs, when administered in medicinal doses, relieve pain and produce sleep. In poisonous doses, these produce stupor, coma, convulsions and ultimately death. Morphine narcotics are sometimes referred to as opiates, since they are obtained from the opium poppy. These analgesics are chiefly used for the relief of postoperative pain, cardiac pain and pains of terminal cancer, and in childbirth. 454 Chemistry. Diseases in human beings and animals may be caused by a variety of microorganisms such as bacteria, virus, fungi and other pathogens. An antimicrobial tends to destroy, prevent development or inhibit the pathogenic action of microbes such as bacteria. Antibacterial drugs, fungi antifungal agents, virus antiviral agents, or other parasites. Antiparasitic drugs selectively. Antibiotics, antiseptics and disinfectants are antimicrobial drugs. Antibiotics are used as drugs to treat infections because of their low toxicity for humans and animals. Initially, antibiotics were classified as chemical substances produced by microorganisms, bacteria, fungi and molds that inhibit the growth or even destroy microorganisms. The development of synthetic methods has helped in synthesizing some of the compounds that were originally discovered as products of microorganisms. Also, some purely synthetic compounds have antibacterial activity, and therefore, definition of antibiotic has been modified. An antibiotic now refers to a substance produced wholly or partly by chemical synthesis, which in low concentrations inhibits the growth or destroys microorganisms by intervening in their metabolic processes. The search for chemicals that would adversely affect invading bacteria but not the host began in the 19th century. Paul Ehrlich, a German bacteriologist, conceived this idea. He investigated arsenic-based structures in order to produce less toxic substances for the treatment of syphilis. He developed the medicine, arsphenamine, known as salvarsan. Paul Ehrlich got Nobel Prize for Medicine in 1908 for this discovery. It was the first effective treatment discovered for syphilis. Although salvarsan is toxic to human beings, its effect on the bacteria, spirochete, which causes syphilis is much greater than on human beings. At the same time, Ehrlich was working on azidides also. He noted that there is similarity in structures of salvarsan and 1,6,3,4 antimicrobials. The structures of salvarsan, prontosyl azidi and sulfapyridine showing structural similarity. 455 Chemistry and everyday life. Azidides. The azos linkage present in arsphenamine resembles the NN linkage present in azidides in the sense that arsenic atom is present in place of nitrogen. He also noted tissues getting colored by dyes selectively. Therefore, Ehrlich began to search for the compounds which resemble in structure to azidides and selectively bind to bacteria. In 1932, he succeeded in preparing the first effective antibacterial agent, prontosyl, which resembles in structure to the compound, salvarsan. Soon it was discovered that in the body prontosyl is converted to a compound called sulfanilamide, which is the real active compound. Thus the sulfa drugs were discovered. A large range of sulfonamide analogues was synthesized. One of the most effective is sulfapyridine. Despite the success of sulfonamides, the real revolution in antibacterial therapy began with the discovery of Alexander Fleming in 1929, of the antibacterial properties of a penicillium fungus. Isolation and purification of active compound to accumulate sufficient material for clinical trials took 13 years. Antibiotics have either cytal killing effect or a static inhibitory effect on microbes. A few examples of the two types of antibiotics are as follows: bactericidal, bacteriostatic, penicillin, erythromycin, aminoglycosides, tetracyclinofloxacin, chloramphenicol. The range of bacteria or other microorganisms that are affected by a certain antibiotic is expressed as its spectrum of action. Antibiotics which kill or inhibit a wide range of gram-positive and gram-negative bacteria are said to be broad-spectrum antibiotics. Those effective mainly against gram-positive or gram-negative bacteria are narrow-spectrum antibiotics. If effective against a single organism or disease, they are referred to as limited-spectrum antibiotics. Penicillin G has a narrow spectrum. Ampicillin and amoxicillin are synthetic modifications of penicillins. These have broad spectrum. It is absolutely essential to test the patients for sensitivity allergy to penicillin before it is administered. In India, penicillin is manufactured at the Hindustan Antibiotics in Pimpri and in private sector industry. Chloramphenicol, isolated in 1947, is a broad-spectrum antibiotic. It is rapidly absorbed from the gastrointestinal tract and hence can be given orally in case of typhoid, dysentery, acute fever, certain form of urinary infections, meningitis and pneumonia. Vancomycin and ofloxacin are the other important broad-spectrum antibiotics. The antibiotic disidazoline is supposed to be toxic towards certain strains of cancer cells. H. W. Fleury and Alexander Fleming shared the Nobel Prize for Medicine in 1945 for their independent contributions to the development of penicillin. 456 Chemistry B. Antiseptics and disinfectants. Antiseptics and disinfectants are also the chemicals which either kill or prevent the growth of microorganisms. Antiseptics are applied to the living tissue such as wounds, cuts, ulcers and diseased skin surfaces. Examples are furacane, saframycin, etc. These are not ingested like antibiotics. Commonly used antiseptic, Dettol is a mixture of chloroxylenol and terpineol. Bithionol. The compound is also called bithanol, is added to soaps to impart antiseptic properties. Iodine is a powerful antiseptic. Its 2-3% solution in alcohol water mixture is known as tincture of iodine. It is applied on wounds. Iodoform is also used as an antiseptic for wounds. Boric acid in dilute aqueous solution is weak antiseptic for eyes. Disinfectants are applied to inanimate objects such as floors, drainage system, instruments, etc. Same substances can act as an antiseptic as well as disinfectant by varying the concentration. For example, 0.2% solution of phenol is an antiseptic while its 1% solution is disinfectant. Chlorine in the concentration of 0.2 to 0.4 ppm in aqueous solution and sulfur dioxide in very low concentrations are disinfectants. Antibiotic revolution has provided long and healthy life to people. The life expectancy has almost doubled. The increased population has caused many social problems in terms of food resources, environmental issues, employment, etc. To control these problems, population is required to be controlled. This has led to the concept of family planning. Anti-fertility drugs are of use in this direction. Birth control pills essentially contain a mixture of synthetic estrogen and progesterone derivatives. Both of these compounds are hormones. It is known that progesterone suppresses ovulation. Synthetic progesterone derivatives are more potent than progesterone. Norethindrone is an example of synthetic progesterone derivative most widely used as anti-fertility drug. The estrogen derivative which is used in combination with progesterone derivative is phenylestradiol novestrol. 163. 5 Anti-fertility drugs in text questions. 16.1 Sleeping pills are recommended by doctors to the patients suffering from sleeplessness, but it is not advisable to take its doses without consultation with the doctor. Y 16.2 With reference to which classification has the statement, ranitidine is an antacid been given? Chemicals are added to food for either preservation, 2 enhancing their appeal, and 3 adding nutritive value in them. Main categories of food additives are as follows: I food colors, 2 flavors and sweeteners, 3 fat emulsifiers and stabilizing agents, I flour improvers, anti-staling agents and bleaches, V antioxidants, V preservatives, 7 nutritional supplements such as minerals, vitamins and amino acids. Except for chemicals of category 7, none of the above additives have nutritive value. These are added either to increase the shelf life of stored food or for cosmetic purposes. In this section we will discuss only sweeteners and food preservatives. Natural sweeteners, e.g., sucrose, add to calorie intake and therefore many people prefer to use artificial sweeteners. Ortosulfabenzamide, also called saccharin, is the first popular artificial sweetening agent. It has been used as a sweetening agent ever since it was discovered in 1879. It is about 550 times as sweet as cane sugar. It is excreted from the body and urine unchanged. It appears to be entirely inert and harmless when taken. Its use is of great value to diabetic persons and people who need to control intake of calories. Some other commonly marketed artificial sweeteners are given in Table 16.1. 16.416, 416, 416, 416, 4, capital C H E M I C A L S, capital C H E M I C A L S, capital C H E M I C A L S, capital C H E, in food 164. 1 Artificial sweetening agents. Table 16.1. Artificial sweeteners. Artificial structural formula. Sweetness value in sweetener comparison to cane sugar. Aspartame 100, saccharin 550, sucralose 600. 458. Chemistry 164. 2 Food preservatives. Aldehydes 2000. Aspartame is the most successful and widely used artificial sweetener. It is roughly 100 times as sweet as cane sugar. It is methyl ester of dipeptide formed from aspartic acid and phenylalanine. Use of aspartame is limited to cold foods and soft drinks because it is unstable at cooking temperature. Aldehyde is high-potency sweetener. Although it is more stable than aspartame, the control of sweetness of food is difficult while using it. Sucralose is trichloro-derivative of sucrose. Its appearance and taste are like sugar. It is stable at cooking temperature. It does not provide calories. Food preservatives prevent spoilage of food due to microbial growth. The most commonly used preservatives include table salt, sugar, vegetable oils and sodium benzoate, C6H5 CUNA. Sodium benzoate is used in limited quantities and is metabolized in the body. Salts of sorbic acid and propanoic acid are also used as preservatives. These are important and necessary food additives. These help in food preservation by retarding the action of oxygen on food. These are more reactive towards oxygen than the food material which they are protecting. The 2 most familiar antioxidants are butylated hydroxytoluene BHT and butylated hydroxyanisole BHA. The addition of BHA to butter increases its shelf life from months to years. Sometimes BHT and BHA along with citric acid are added to produce more effect. Sulfur dioxide and sulfide are useful antioxidants for wine and beer, sugar syrups and cut, peeled or dried fruits and vegetables. In text question 16.3. Why do we require artificial sweetening agents? 164. 3 Antioxidants in food. In this section, we will learn about detergents. 2 types of detergents are used as cleansing agents. These are soaps and synthetic detergents. These improve cleansing properties of water. These help in removal of fats which bind other materials to the fabric or skin. 165. 1 Soap 16.516. 516. 516. 516. Capital C L E A N S I N G, capital C L E A N S I N G, capital C L E A N S I N G, capital C L E. Agents. 459. Chemistry in everyday life. Soaps are the detergents used since long. Soaps used for cleaning purpose are sodium or potassium salts of long-chain fatty acids, e.g., stearic, oleic and palmitic acids. Soaps containing sodium salts are formed by heating fat, that is, glycerol ester of fatty acid with aqueous sodium hydroxide solution. This reaction is known as saponification. In this reaction, esters of fatty acids are hydrolyzed and the soap obtained remains in colloidal form. It is precipitated from the solution by adding sodium chloride. The solution left after removing the soap contains glycerol, which can be recovered by fractional distillation. Only sodium and potassium soaps are soluble in water and are used for cleaning purposes. Generally, potassium soaps are soft to the skin than sodium soaps. These can be prepared by using potassium hydroxide solution in place of sodium hydroxide. Types of soaps. Basically all soaps are made by boiling fats or oils with suitable soluble hydroxide. Variations are made by using different raw materials. Toilet soaps are prepared by using better grades of fats and oils and care is taken to remove excess alkali. Color and perfumes are added to make these more attractive. Soaps that float in water are made by beating tiny air bubbles before their hardening. Transparent soaps are made by dissolving the soap in ethanol and then evaporating the excess solvent. In medicated soaps, substances of medicinal value are added. In some soaps, deodorants are added. Shaving soaps contain glycerol to prevent rapid drying. A gum called rosin is added while making them. It forms sodium rosinate which lathers well. Laundry soaps contain fillers like sodium rosinate, sodium silicate, borax and sodium carbonate. Soap chips are made by running a thin sheet of melted soap onto a cool cylinder and scraping off the soaps in small broken pieces. Soap granules are dried miniature soap bubbles. Soap powders and scouring soaps contain some soap, a scouring agent, abrasives such as powdered pumice or finely divided sand, and builders like sodium carbonate and trisodium phosphate. Builders make the soaps act more rapidly. The cleansing action of soap has been discussed in Unit 5. Why do soaps not work in hard water? Hard water contains calcium and magnesium ions. These ions form insoluble calcium and magnesium soaps respectively when sodium or potassium soaps are dissolved in hard water. These insoluble soaps separate as scum in water and are useless as cleansing agent. In fact, these are a hindrance to good washing, because the precipitate adheres onto the fiber of the cloth as gummy mass. Hair washed with hard water looks dull because of this sticky precipitate. Dye does not absorb evenly on cloth washed with soap using hard water, because of this gummy mass. 460 Chemistry. Synthetic detergents are cleansing agents which have all the properties of soaps, but which actually do not contain any soap. These can be used both in soft and hard water as they give foam even in hard water. Some of the detergents give foam even in ice-cold water. Synthetic detergents are mainly classified into 3 categories: ionic detergents, 2 cationic detergents, and 3 non-ionic detergents. Ionic detergents. Anionic detergents are sodium salts of sulfonated long-chain alcohols or hydrocarbons. Alkyl hydrogen sulfates formed by treating long-chain alcohols with concentrated sulfuric acid are neutralized with alkali to form anionic detergents. Similarly, alkyl benzene sulfonates are obtained by neutralizing alkyl benzene sulfonic acids with alkali. 1,6,5. 2 synthetic detergents: CHCH3-11HSO2,4CHCH3-11SO3 NaOH CHCH3-11SO 3-dodesilbenzene sulfonic acid sodium dodesilbenzene sulfonate CHCH3-15 NCH3CH3CH3 acetyl trimethyl ammonium bromide. In anionic detergents, the anionic part of the molecule is involved in the cleansing action. Sodium salts of alkylbenzene sulfonates are an important class of anionic detergents. They are mostly used for household work. Anionic detergents are also used in toothpaste. 2 cationic detergents. Cationic detergents are quaternary ammonium salts of amines with acetates, chlorides or bromides as anions. Cationic part possess a long hydrocarbon chain and a positive charge on nitrogen atom, hence, these are called cationic detergents. Acetyl trimethylammonium bromide is a popular cationic detergent and is used in hair conditioners. Cationic detergents have germicidal properties and are expensive, therefore, these are of limited use. 3 non-ionic detergents. Non-ionic detergents do not contain any ion in their constitution. One such detergent is formed when stearic acid reacts with polyethylene glycol. Liquid dishwashing detergents are non-ionic type. Mechanism of cleansing action of this type of detergents is the same as that of soaps. These also remove grease and oil by micelle formation. 461 Chemistry in Everyday Life. In text questions. In text questions. In text questions. In text questions. In text questions 16.4. Write the chemical equation for preparing sodium soap from glyceryl oleate and glyceryl palmitate. Structural formulae of these compounds are given below. IC15H31COO3C3H5 glyceryl palmitate 2C17H32COO3C3H5 glyceryl oleate 16.5. Following type of non-ionic detergents are present in liquid detergents: emulsifying agents and wetting agents. Label the hydrophilic and hydrophobic parts in the molecule. Identify the functional group S present in the molecule. Main problem that appears in the use of detergents is that if their hydrocarbon chain is highly branched, then bacteria cannot degrade this easily. Slow degradation of detergents leads to their accumulation. Effluents containing such detergents reach the rivers, ponds, etc. These persist in water even after sewage treatment and cause foaming in rivers, ponds and streams, and their water gets polluted. These days the branching of the hydrocarbon chain is controlled and kept to the minimum. Unbranched chains can be biodegraded more easily and hence pollution is prevented. Summary. Chemistry is essentially the study of materials and the development of new materials for the betterment of humanity. A drug is a chemical agent, which affects human metabolism and provides cure from ailment. If taken in doses higher than recommended, these may have poisonous effect. Use of chemicals for therapeutic effect is called chemotherapy. Drugs usually interact with biological macromolecules such as carbohydrates, proteins, lipids and nucleic acids. These are called target molecules. Drugs are designed to interact with specific targets so that these have the least chance of affecting other targets. This minimizes the side effects and localizes the action of the drug. Drug chemistry centers around arresting microbes, destroying microbes, preventing the body from various infectious diseases, releasing mental stress, etc. Thus, drugs like analgesics, antibiotics, antiseptics, disinfectants, antacids and tranquilizers are used for specific purpose. To check the population explosion, anti-fertility drugs have also become prominent in our life. Food additives such as preservatives, sweetening agents, flavors, antioxidants, edible colors and nutritional supplements are added to the food to make it attractive, palatable and add nutritive value.
Preservatives are added to the food to prevent spoilage due to microbial growth. Artificial sweeteners are used by those who need to check the calorie intake or are diabetic and want to avoid taking sucrose. These days, detergents are much in vogue and get preference over soaps because they work even in hard water. Synthetic detergents are classified into